In 1638, a Dutch astronomer named Johannes Holwarder noticed something peculiar. A star in the constellation Cetus that had no right to be there, having faded to invisibility months before, was glowing again. That quiet observation, that patient watching of a single point of light that refused to stay constant, would eventually reshape how we understand the cosmos itself. This is a story told in long nights and careful notebooks, in the slow accumulation of data across generations, in the gentle stubbornness of those who believed the heavens held secrets worth counting. If these quiet histories help carry you toward rest, subscribing means more of them will find their way here. The stars, as it happens, have never been as unchanging as they appear, and the people who first noticed this were often working alone, in the dark, with little more than patience and wonder to guide them. We begin with them now. The story of variable stars begins, as so many stories in astronomy do, with a single patient observer gazing upward into the darkness, noticing something that others had overlooked or perhaps dismissed as unimportant. In the case of the first recognized variable star, that observer was David Fabricius, a Lutheran minister and amateur astronomer living in the small town of Resterhafe in East Frisia, which sits along the northern coast of what is now Germany. On the 3rd of August in the year 1596, Fabricius was engaged in a pursuit that occupied many of the serious astronomical observers of his time, which was tracking the position of a planet, in this case Jupiter, as it made its slow way across the constellations. To measure the position of a planet with any accuracy, one needed reference points, and so Fabricius looked for nearby stars that might serve as markers against which Jupiter's movement could be gauged. It was during this entirely practical exercise that Fabricius noticed a star in the constellation Cetus, the celestial whale, that he did not recall having seen before. This star, which we now know as Omicron Cephei, was bright enough to be easily visible to the unaided eye, perhaps of the 3rd magnitude, which is to say reasonably prominent though certainly not among the brightest stars in the sky. Fabricius noted its position and continued with his observations of Jupiter, thinking perhaps that he had simply overlooked this star on previous occasions, which would not have been unusual given the thousands of stars visible on any clear night. Over the following weeks, however, something curious happened. The star grew fainter, gradually diminishing in brightness until, by October of that same year, it had faded from view entirely. Fabricius could no longer see it at all, even on the clearest nights, even when he knew precisely where to look. For any observer of the late 16th century, this was a deeply peculiar occurrence. The disappearance of a star did not fit comfortably within the accepted understanding of the heavens. According to the philosophical framework inherited from Aristotle and refined by medieval scholars, the celestial realm was fundamentally different from the earthly one. Down here, beneath the sphere of the moon, everything was subject to change, decay, generation, and corruption. Things came into being and passed away. But up there, beyond the moon, in the realm of the stars and planets, everything was perfect, eternal, and unchanging. The stars were fixed in their crystalline spheres, and they had shone with precisely the same light since the moment of creation. They did not flicker, they did not move relative to one another, and they most certainly did not appear and disappear like candles being lit and extinguished. Fabricius, being a careful observer but also a man of his time, did not immediately conclude that he had witnessed a star changing its brightness. The more natural assumption was that he had made some sort of error, perhaps misidentifying the star's position, perhaps confusing it with something else. The instruments available to him, while reasonably precise for their era, were not sophisticated by later standards. Fabricius would have used a quadrant, which is essentially a quarter circle of wood or brass marked with degree graduations, fitted with sighting vanes that allowed the user to measure the angular height of a star above the horizon. By noting this altitude along with the time of observation, and by measuring the star's position relative to other known stars, an observer could establish coordinates that could be compared from night to night or year to year. These measurements were painstaking and subject to various errors, from the flexing of the instrument in different temperatures to the difficulty of sighting precisely on a point of light in the darkness. 13 years passed. Fabricius continued his astronomical work, observing comets, tracking planets, and corresponding with other astronomers across Europe in the manner typical of the scholarly community of his day. Then, in 1609, something remarkable happened. Fabricius was once again observing the region of Cetus, and there, in very nearly the same position where he had seen that curious star more than a decade earlier, was a star of the third magnitude. It had returned. This was the same star he had watched fade into invisibility in 1596, and now here it was again, plainly visible, as if nothing had happened. Fabricius observed it through the following weeks and watched it fade once more, growing dimmer and dimmer until it once again vanished from naked eye visibility. This rediscovery was significant because it suggested that whatever was happening to this star was not a singular event but rather something that repeated. Unfortunately, Fabricius did not live to pursue this mystery further. He died in 1617, and while he had shared his observations with other astronomers, the matter of the disappearing and reappearing star in Cetus remained something of a curiosity, noted but not systematically investigated. The times were turbulent, with religious conflicts spreading across Europe, and astronomical priorities were focused elsewhere, on questions of planetary motion and the structure of the solar system, on the new observations being made with the recently invented telescope, and on the great debates between the defenders of the old Earth-centered cosmology and the proponents of the new Sun-centered model. It was not until 1638 that a Dutch astronomer named Johannes Holwarder took up the question in a sustained and methodical way. Holwarder, who was a professor at the University of Franeker in the northern Netherlands, had become aware of the reports concerning the star in Cetus, and he set himself the task of observing it carefully over an extended period to determine whether its behavior followed any predictable pattern. This was the crucial step, the transition from noticing something odd to systematically studying it, and it marks what we might reasonably call the true beginning of variable star astronomy. Holwarder observed the star through multiple cycles of brightening and fading, carefully recording its apparent brightness at regular intervals, comparing it to other stars of known magnitude, and noting the dates when it reached maximum visibility and when it faded below the threshold of naked eye detection. What Holwarder discovered was that the star's variations were indeed periodic, meaning that they repeated in a regular cycle. He determined that the star went through a complete cycle of brightening and fading in approximately 11 months, reaching its maximum brightness roughly every 330 days. This was a revelation of considerable importance, because periodicity implied some kind of underlying mechanism, some physical process that operated in a regular and predictable manner. A star that simply flickered randomly would be one thing, strange and perhaps troubling but potentially explicable as some sort of atmospheric effect or observational artifact. But a star that varied with a precise period of 11 months was something else entirely, something that demanded explanation in terms of the star itself. 4 years after Holwarder's determination of the period, in 1642, the great Polish astronomer Johannes Hevelius turned his attention to this remarkable object. Hevelius was one of the foremost observational astronomers of his age, a wealthy brewer who had built a magnificent private observatory on the rooftops of several adjoining houses in the city of Danzig, equipping it with the finest instruments available and devoting himself to the meticulous mapping of the heavens. Hevelius observed the star in Cetus and, struck by its extraordinary behavior, gave it a name that would endure. He called it Mira, which is Latin for wonderful or astonishing, and this name captured perfectly the sense of marvel that astronomers felt when contemplating a star that defied all expectations of celestial constancy. The instruments that Hevelius and his contemporaries used for their observations were more sophisticated than those available to Fabricius, though they would seem crude by modern standards. The telescope had been invented in the early 1600s and had quickly been adopted by astronomers, but for the purposes of measuring stellar brightness, it was not necessarily superior to the naked eye. The early telescopes, with their small lenses and limited fields of view, were excellent for revealing details on the Moon and planets, for discovering the satellites of Jupiter and the phases of Venus, but they did not make faint stars appear dramatically brighter, and they introduced various optical distortions that could complicate the estimation of brightness. For the purpose of tracking a variable star like Mira, the method employed was essentially the same one that had been used since antiquity, which was to compare the star visually with other stars of known or assumed constant brightness. This method, which we might call naked eye estimation or visual photometry, relied on the observer's trained eye and careful judgment. One would look at Mira, then look at a nearby star of approximately second magnitude, then at one of third magnitude, and make a determination of where Mira fell on this scale. Was it equal to the second magnitude star, or fainter, or somewhere in between? On another night, weeks or months later, one would repeat this process, and by accumulating such estimates over time, one could build up a record of the star's changing brightness. It was subjective. It was imprecise. It was influenced by atmospheric conditions and the observer's fatigue and any number of other factors, but it was sufficient to reveal the broad pattern of variation, the slow rise to maximum and the gradual decline to minimum, the 11-month period that Holwarder had discovered. The quadrant remained an essential instrument, not for measuring brightness but for establishing positions. Hevelius constructed quadrants of remarkable size and precision, great arcs of brass with finely divided scales that allowed measurements to fractions of a degree. With such instruments, an observer could fix a star's location in the sky with considerable accuracy, which was important for keeping track of which star was which and for determining whether a newly visible star was truly new or merely a known star that had brightened. The process of observation involved patience, skill, and a willingness to spend long hours in the cold darkness, waiting for the sky to clear, waiting for the stars to rise to suitable heights above the horizon, recording measurements by the light of a dim lamp that would not ruin one's night vision. As the 17th century progressed, astronomers began to grapple with the philosophical implications of stellar variability. If stars could change their brightness, what did that say about the nature of the heavens? The old Aristotelian picture of an unchanging celestial realm had already been damaged by the observations of comets, which clearly moved through the supposedly crystalline spheres, and by the appearance of new stars, or novae, in 1572 and 1604, which had blazed forth in regions of the sky where no star had been seen before. But those events could be dismissed, with some difficulty, as exceptional occurrences, divine interventions perhaps, or phenomena confined to the upper atmosphere. A star that varied regularly, predictably, with an 11-month period, was harder to explain away. It suggested that change was not merely possible in the heavens but was built into the normal operation of at least some celestial bodies. In 1667, a French astronomer named Ismael Boulieu published a work in which he attempted to provide a physical explanation for Mira's variability. Boulieu, also known by the Latinized form of his name as Bullialdus, was a scholar of wide-ranging interests who had made contributions to mathematics, physics, and astronomy. His explanation for Mira's changing brightness was, by modern standards, incorrect, but it was a genuine attempt to understand the phenomenon in physical rather than purely descriptive terms. Boulieu proposed that Mira was a star with a surface that was not uniformly bright, that one side or portion of the star was luminous while another was dark, and that the star rotated on its axis in such a way that it presented different aspects to us at different times, sometimes showing its bright face and sometimes its dark one. This was a reasonable hypothesis given the state of knowledge at the time, analogous to the way that the Moon shows us different amounts of its illuminated surface as it orbits the Earth, and it had the virtue of providing a mechanism that could naturally produce periodic variation. We now know that Boulieu's explanation was not correct, that Mira's variations are caused by pulsations in the star itself, great expansions and contractions that cause the star to swell and shrink, to heat and cool, and thereby to vary in its output of light. But Boulieu's attempt was significant nonetheless, because it represented a shift in astronomical thinking, a willingness to seek physical explanations for celestial phenomena rather than simply accepting them as mysteries beyond human comprehension. This was the spirit of the new science that was emerging in the 17th century, the conviction that the universe operated according to natural laws that could, with sufficient observation and thought, be understood. 2 years after Boulieu's publication, in 1669, another discovery was made that would eventually prove to be of comparable importance, though its true nature would not be understood for more than a century. An Italian astronomer named Geminiano Montanari, working at the University of Bologna, noticed that the star Algol in the constellation Perseus was not always of the same brightness. Algol, unlike Mira, had been known since ancient times and had always been considered a star of the second magnitude, visible on any clear night and unremarkable in its appearance. But Montanari observed that it sometimes faded noticeably, dropping to perhaps the third magnitude before returning to its normal brightness. This was peculiar, and Montanari reported his observations, but the matter did not receive the same attention as Mira's variations, perhaps because Algol's changes were more subtle and less dramatic, perhaps because they seemed to occur irregularly rather than in a clear periodic pattern. What Montanari had discovered, though he did not and could not have known it, was an eclipsing binary star, 2 stars orbiting around their common center of gravity, so aligned with our line of sight that one periodically passes in front of the other, blocking its light and causing the combined brightness of the pair to decrease. This is a fundamentally different mechanism from the pulsations of Mira, and it produces a different pattern of variation, with relatively abrupt dips in brightness separated by longer intervals of constant light. But in the 17th century, the idea that stars might occur in orbiting pairs was barely conceivable, and the concept of an eclipse involving two stars rather than a moon and a planet was simply not part of the astronomical vocabulary. Montanari's observations were noted, filed away, and would have to wait many decades before their full significance was appreciated. The discovery of these two variable stars, Mira and Algol, in the span of less than a century, raised the possibility that stellar variability might not be as rare as initially supposed. Perhaps there were many stars whose brightness changed, stars that had simply not been watched carefully enough or for long enough for their variations to be detected. The heavens, which had seemed so stable and eternal, might in fact be full of subtle changes, rhythms and cycles playing out over timescales that dwarfed human lifetimes but that could, with patience and diligence, be discerned. This was a humbling thought in some ways, a reminder that the universe was larger and more complex than any single observer could comprehend, but it was also an inspiring one, an invitation to future generations of astronomers to continue the work of watching, measuring, and recording, building up over time a picture of the cosmos that no single night's observation could provide. The instruments of this era, the quadrants and sextants and early telescopes, were tools of patience rather than power. They did not reveal their secrets quickly or easily. An astronomer wishing to understand a star like Mira had to commit to years of observation, clear night after clear night, recording the star's brightness by comparison with its neighbors, noting the dates when it reached maximum and minimum, building up the data that would eventually reveal the period and the pattern. This was not glamorous work, and it did not produce dramatic discoveries in the manner of Galileo's first glimpses of Jupiter's moons or the craters of the Moon. But it was essential work, the slow accumulation of facts that would eventually make possible the great theoretical advances of later centuries. As the 17th century drew to a close, the study of variable stars remained in its infancy. Only two objects, Mira and Algol, were widely recognized as variable, and the mechanisms behind their variations were matters of speculation rather than understanding. The philosophical implications of stellar variability were still being absorbed into astronomical thinking, and the old certainties about the unchanging heavens were giving way, slowly and sometimes reluctantly, to a new appreciation of cosmic change. But the foundation had been laid. Fabricius had noticed something peculiar. Holwarder had established its periodicity. Hevelius had given it a name that captured its wonder. And Boulio had shown that physical explanations could be sought and proposed. The dawn of variable star astronomy had arrived, and though much remained to be discovered, the first light of understanding was beginning to illuminate a universe far more dynamic than anyone had previously imagined. In the decades following the discovery of Mira, that first wonderful variable star in the constellation Cetus, astronomers across Europe began to look at the night sky with a new kind of attention, a patient and wondering curiosity about whether other stars might also exhibit these strange and gradual changes in brightness. The discovery of Mira had opened a door, you see, into a previously unimagined aspect of stellar behavior. And now careful observers with their modest telescopes and their handwritten logbooks were beginning to peer through that door, hoping to find that Mira was not alone in its peculiar pulsations. And indeed, it was not alone, though it would take nearly 4 decades of watching and waiting before the second long-period variable star would be identified and added to the astronomical catalogue. A discovery that would come from the Berlin Observatory through the dedicated work of Gottfried Kirch, a man whose life was devoted to the patient accumulation of astronomical knowledge. Gottfried Kirch was born in 1639 in Guben, a small town in what is now eastern Germany, and from an early age he demonstrated that particular temperaments so well suited to astronomical observation, a calm persistence and a willingness to repeat the same measurements night after night, year after year, without growing weary of the work. He came to astronomy through his studies with the famous Johannes Hevelius in Danzig, learning from that master observer the techniques of precise positional measurement and the importance of maintaining detailed records of every observation. Koch understood, as his teacher had taught him, that the value of any single night's observation lay not in itself alone but in its relationship to all the observations that came before and would come after, a principle that would prove especially important in the study of variable stars, where changes unfold across timescales measured in months rather than hours. By the 1680s, Koch had established himself in Berlin, where he worked initially as a private astronomer and calendar maker before eventually being appointed as the first astronomer of the Berlin Academy of Sciences, a position he would hold until his death in 1710. His observatory was modest by the standards of some European institutions, but it was well equipped for the kind of systematic observation that Koch preferred, with good quality telescopes and careful attention to the maintenance of accurate timekeeping. It was from this observatory, in the year 1686, that Koch made the observation that would secure his place in the history of variable star astronomy, when he noticed something unusual about a star in the constellation Cygnus, the Swan, that graceful pattern of stars stretching along the summer Milky Way. The star that caught Koch's attention was one that had been catalogued before but had never been noted as remarkable, a modest point of light that should have remained constant in its brightness from one observation to the next. But Koch, with his habit of careful comparison and his excellent memory for the appearance of star fields, realized that this particular star was not behaving as a well-mannered fixed star should behave. Over a period of weeks and months, he watched as the star grew gradually brighter, reaching a maximum visibility where it could be seen clearly with the naked eye, and then slowly dimming again until it faded from view entirely, disappearing into the darkness between the other stars of Cygnus as though it had never existed at all. This star would come to be known as Chi Cygni, and it was, after Mira itself, only the second long-period variable star to be recognized and documented. The observation of Chi Cygni required all of Koch's patience and skill, for this star proved to be even more challenging to track than Mira had been for earlier observers. Chi Cygni has a period of approximately 408 days, over a year from one maximum brightness to the next, and its range of variation is truly remarkable, changing by a factor of nearly 10,000 in brightness between its brightest and faintest states. At maximum, Chi Cygni can be seen easily without optical aid, a modest but visible presence in the rich star fields of the Milky Way, but at minimum it fades to such dimness that even with the telescopes available to Koch it could barely be detected, hovering at the very edge of visibility. This extreme range of variation meant that for much of its cycle, Chi Cygni simply was not there to be observed, a circumstance that created significant difficulties for anyone trying to maintain continuous records of its behavior. In his work at the Berlin Observatory, Gottfried Koch was not alone, for he was assisted and supported by his wife, Maria Margarethe Koch, a woman whose contributions to astronomy deserve to be remembered with the same respect accorded to her husband. Maria Margarethe, born Maria Margarethe Winkelmann in 1670, had studied astronomy before her marriage and continued her observations after becoming Koch's wife in 1692, some years after his discovery of Chi Cygni. She was a skilled observer in her own right, capable of making precise measurements and maintaining the detailed records upon which variable star research depended. Her most famous discovery would come in 1702, when she identified a previously unknown comet, making her the first woman to discover a comet in the modern era, though the credit for this discovery was initially given to her husband rather than to her, a common injustice of the time. Maria Margarethe Kirch's contributions to the observation of variable stars are harder to trace in the historical record, as was unfortunately typical for the work of women astronomers in this period. But we know that she participated actively in the observing programs conducted at the Berlin Observatory and that she maintained observation logs during periods when her husband was occupied with other duties or was unwell. The study of variable stars, with its requirement for observations spread across many months and years, was particularly well suited to collaborative work within families, where the burden of nightly observation could be shared and where gaps in the record due to illness or travel could be filled by a knowledgeable partner. The Kirch family, which eventually included children who also participated in astronomical work, represented an early model of this kind of collaborative observation, a small team united by family bonds and shared dedication to the patient work of watching the skies. As the 17th century gave way to the 18th, other observers across Europe began to contribute to the slowly growing catalogue of variable stars, each new discovery adding to the evidence that Mira and Cygni were not isolated curiosities but representatives of a broader category of stellar objects. In 1704, the Italian-French astronomer Giacomo Filippo Maraldi, working at the Paris Observatory, identified what would become the third known long-period variable, a star in the constellation Hydra, the water snake, that long and winding pattern stretching across a large area of the southern spring sky. This star, which would come to be designated a Hydra following the naming conventions established much later for variable stars, showed the same pattern of gradual brightening and fading that characterized Mira and Cygni, though with its own particular period and range of variation. Giacomo Filippo Maraldi was the nephew of the more famous Giovanni Domenico Cassini, the first director of the Paris Observatory, and he had come to Paris from his native Italy to assist his uncle in the great astronomical projects being conducted there. Maraldi proved to be a capable observer with a particular interest in the careful measurement of stellar positions, work that naturally led him to notice when a star's brightness did not match what previous catalogues had recorded. His discovery of a Hydra demonstrated that variable stars could be found in any part of the sky, not just in the particular constellations where Mira and Cygni resided, a realization that encouraged other astronomers to examine their own observations with fresh attention to the possibility of variability. The work of variable star observation was continued and extended by Jean-Dominique Maraldi, who was the nephew of Giacomo Filippo and who carried on the family tradition of careful astronomical observation at the Paris Observatory well into the 18th century. Jean-Dominique Maraldi made numerous observations of known variable stars and searched systematically for new ones, contributing to the gradual expansion of the catalogue and to the refinement of period estimates for stars like Mira, Cygni, and our Hydra. His observations, combined with those of other astronomers working at observatories across Europe, began to establish a more complete picture of how these stars behaved, revealing both the regularities of their periodic variations and the subtle irregularities that made each cycle slightly different from the ones before and after. The discoveries of this period established what would eventually be called the category of long-period variables, a designation that distinguished these stars from other types of variable stars that would be discovered in later centuries. Long-period variables, as the name suggests, are characterized by periods of variation ranging from several months to well over a year, with Mira's period of approximately 332 days being fairly typical and Cygni's period of 408 days representing the longer end of the common range. These stars also share certain other characteristics that would not be fully understood until the 20th century, including their cool surface temperatures, their enormous physical sizes, and their tendency to be surrounded by expanding shells of gas and dust that they have shed during their pulsations. But for the astronomers of the 17th and 18th centuries, these physical details remained hidden, and the defining characteristic of long-period variables was simply their slow, patient rhythm of brightening and fading, a rhythm that demanded an equally slow and patient approach to observation. The challenge of tracking stars that disappeared entirely from naked eye visibility, and sometimes from telescopic visibility as well, was one of the central difficulties facing early variable star observers. When Mira or Cygni faded to minimum brightness, there was no way to continue observing them in the same manner that one observed them at maximum, no way to measure their brightness against comparison stars when they could not be seen at all. This disappearance created gaps in the observational record that were deeply frustrating for astronomers trying to determine precise periods and to understand the full pattern of each star's variation. The only solution was patience, the willingness to wait through the weeks or months of invisibility until the star slowly emerged again from the darkness, gradually brightening until it could once more be detected and measured. This requirement for patience across very long timescales, combined with the need for observations on as many clear nights as possible, naturally led to the development of collaborative networks among European astronomers, informal arrangements for sharing observations and coordinating efforts across different locations. If clouds obscured the sky over Berlin for several weeks during a critical phase of Cygni's cycle, perhaps the sky would be clear over Paris or London, and observations made there could fill the gap in the record. This sharing of observations required correspondence, of course, letters traveling slowly across the continent bearing news of what had been seen and when, and it required a degree of trust and mutual respect among astronomers who might never meet in person but who recognized that their individual observations gained value from being combined with those of others. Among the astronomers contributing to this collaborative enterprise was Johann Abraham Eil, a German astronomer and customs official who made observations from Weissenfels in Saxony during the latter part of the 17th century. Eil is perhaps best known for his observation of the globular cluster now designated M22, but he also made contributions to the observation of variable stars, recording his observations carefully and sharing them with correspondents across Europe. His work illustrates how variable star observation in this period was not the exclusive province of professional astronomers at major observatories, but could be conducted by dedicated amateurs with good instruments and the patience to maintain systematic watching programs over extended periods. The process of maintaining observational continuity across months and years without the aid of photography was laborious in ways that are difficult to fully appreciate from our present vantage point. Each observation had to be made by eye, either naked or aided by a telescope, and the result had to be recorded immediately in a logbook, including the date and time, the conditions of the sky, the brightness of the variable star relative to comparison stars, and any other relevant details. These logbooks, written in careful handwriting by candlelight, represented the primary record of the observation, and their accuracy depended entirely on the skill and honesty of the observer. There were no photographs to be checked later, no recordings that could be analyzed with fresh eyes, only the written testimony of what someone had seen on a particular night. and the hope that this testimony was precise enough to be useful when combined with observations made on other nights by other observers. The comparison method, by which a variable star's brightness was estimated by comparing it to nearby stars of known and constant brightness, was the standard technique for these observations, but it required considerable skill to apply consistently. An observer had to memorize the brightness sequence of the comparison stars, or consult charts prepared for this purpose, and then make a rapid judgment about where the variable star fell in that sequence, noting whether it appeared brighter than one comparison star, fainter than another, or roughly equal to a third. These estimates were necessarily somewhat subjective, influenced by the observer's eyesight, the quality of the night's transparency, the altitude of the star above the horizon, and dozens of other factors that could introduce small errors into the measurement. The accumulation of many observations by many observers helped to average out these individual errors, but the process was inherently less precise than the photographic methods that would eventually replace it. Despite these difficulties, the early observers of variable stars achieved results of remarkable quality, establishing periods that remain essentially accurate today and creating baseline records of stellar behavior that still have scientific value nearly 3 centuries later. Their success depended on the combination of careful technique, collaborative effort, and above all persistence, the willingness to continue the work night after night and year after year, trusting that the slow accumulation of data would eventually reveal the patterns hidden in the star's variations. This persistence was perhaps the defining virtue of the early variable star observers, a quality of temperament that enabled them to find satisfaction in work whose rewards were measured not in dramatic discoveries but in the gradual refinement of knowledge across decades of patient watching. The establishment of long-period variables as a recognized category of astronomical objects was thus a collective achievement, built up slowly through the contributions of many observers across several generations. From Fabricius and the discovery of Mira in the early 17th century, through Kirch and Kai Cygni, the Miraldis and Arhydri, and onward through the work of countless other observers whose names are less well remembered, the catalogue of known variable stars grew and the understanding of their behavior deepened. Each generation of observers inherited the records of those who came before and added their own observations to the growing body of data, creating a continuous tradition of watching that would eventually lead to the remarkable efflorescence of variable star research in the 19th and 20th centuries. But that expansion lay still in the future, and for now, in the quiet observatories of Europe, astronomers continued their patient vigil, recording the slow brightening and fading of these few known variables and wondering whether other stars might be waiting to reveal their own secrets to those with eyes careful enough to notice and patience enough to watch. In the city of York, in the north of England, during the early 1780s, a young man who could not hear the sounds of the world around him turned his attention instead to the silent rhythms of the stars, and in doing so, he solved a mystery that had puzzled observers for centuries, a mystery concerning a single point of light in the constellation Perseus that the ancient astronomers had named the Demon Star, and which we know today by its Arabic-derived name, Algol. This young man was John Goodricke, and though he would live only 21 years, his careful observations and his bold theoretical explanation would eventually revolutionize our understanding of stellar systems, revealing that many stars are not solitary points of light at all, but rather pairs of suns, locked together in gravitational embrace, circling one another across distances and timescales that dwarf all human experience. John Goodricke was born in 1764 in the city of Groningen, in what is now the Netherlands, to English parents of comfortable means, and his early years were marked by both privilege and hardship. For when he was still a young child, perhaps around the age of 5, he contracted scarlet fever, and the illness left him profoundly deaf. In an era when deafness was poorly understood and often associated with intellectual incapacity, Goodricke's family took the enlightened step of ensuring that he received a proper education, and he was sent to a school in Edinburgh that specialized in teaching deaf children, where he learned to communicate through lip reading and to express himself through writing. He proved to be an exceptional student, with a particular aptitude for mathematics and natural philosophy, and when he later attended the Warrington Academy in Lancashire, his abilities became even more apparent. By the time his family settled in York in the early 1780s, Goodricke was a young man of remarkable intellectual gifts, quiet and observant by necessity and by temperament, and he soon formed a friendship that would prove crucial to the history of astronomy. Edward Pigott was a few years older than Goodricke, the son of a wealthy astronomer named Nathaniel Pigott, and the Pigott family had established a private observatory in York that was equipped with excellent instruments for the time. The younger Pigott recognized in Goodricke a kindred spirit, someone who shared his fascination with the heavens and who possessed the patience and precision that astronomical observation requires. And the two young men began a collaboration that would prove remarkably fruitful. They communicated through writing and gesture, and they developed a systematic approach to their observations that was ahead of its time, keeping careful records, comparing their measurements, and checking one another's work. It was Edward Pigott who suggested to Goodricke that he might turn his attention to the variable stars, those puzzling objects whose brightness seemed to change over time, and Pigott directed his friend's attention specifically to Algol, the demon star in Perseus, which had been recognized as variable since at least 1667, when the Italian astronomer Geminiano Montanari had noted its inconstant brightness. Algol had long been a source of unease among those who observed it, and its very name reflects this ancient discomfort, for the Arabic name from which Algol derives, Ras al-Ghul, means the head of the demon or the head of the ogre, and in the constellation Perseus, the star marks the eye of the severed head of Medusa, which the mythical hero holds aloft after slaying the Gorgon. Ancient and medieval observers seem to have recognized something unsettling about this star, perhaps noticing its periodic dimming even without understanding its cause. And some scholars have suggested that this is why it was associated with malevolent forces in various cultures. The star's variability was documented by Montanari in 1667, as I mentioned, and other observers had noted its changes in brightness in the years that followed, but no one had yet determined the precise pattern of these variations, nor had anyone offered a satisfying explanation for why the star should behave as it did. It was in the autumn of 1782 that John Goodricke began his systematic observations of Algol, watching it night after night from York, carefully estimating its brightness in comparison to nearby stars of known and constant magnitude, and recording his observations with meticulous attention to detail. He was just 18 years old, and he brought to this work a fresh perspective unburdened by preconceptions, along with extraordinary patience and dedication. The method he employed was straightforward in principle but demanding in practice, for it required him to observe the star at every opportunity, weather permitting, and to note even small changes in its apparent brightness relative to its neighbors. Over the course of many weeks, as autumn turned to winter and the long English nights provided ample opportunity for observation, Goodricke accumulated a substantial body of data, and from this data, a clear pattern began to emerge. What Goodricke discovered was that Algol's variations were not random or chaotic, but instead followed a precise and predictable cycle, with the star maintaining a relatively constant brightness for most of the time, then dimming noticeably over the course of several hours, remaining at its minimum brightness for a short period, and then recovering to its former brightness in another span of hours, before the cycle repeated itself. The regularity of this pattern was striking, and Goodricke set himself the task of determining the exact period of the cycle, which is to say the length of time between one minimum and the next. Through careful analysis of his observations, he determined that this period was approximately 2 days, 20 hours, and 49 minutes, a figure that is remarkably close to the modern accepted value and that demonstrated both the precision of his observations and the sophistication of his analytical methods. To determine such a period required not only accurate observations, but also careful record-keeping and the ability to combine multiple observations into a coherent whole. And the fact that a deaf 18-year-old working from a private observatory in northern England could achieve such accuracy is a testament to Goodricke's extraordinary abilities. But determining the period of Algol's variations, impressive as that accomplishment was, represented only part of Goodricke's contribution, for he also proposed an explanation for why the star varied at all, and this explanation would eventually prove to be correct, though it would take more than a century before it was fully accepted by the astronomical community. In a paper that he submitted to the Royal Society of London, and that was published in the Philosophical Transactions in 1783, Goodricke suggested that the most likely cause of Algol's variations was the presence of a large dark body, perhaps a planet or perhaps another star too dim to be seen, which orbited around Algol and periodically passed in front of it as seen from Earth, blocking a portion of its light and causing the observed dimming. This hypothesis, which we now call the eclipsing binary theory, was a bold and imaginative leap, for it required Goodricke to conceive of astronomical objects that could not be directly observed, and to infer their existence solely from their effects on visible objects. The elegance of Goodricke's hypothesis lay in its ability to explain all of the observed features of Algol's variability in a simple and coherent way. The regularity of the period was naturally explained if the dimming was caused by an orbiting body, for orbital motion is itself regular and predictable, governed by the unchanging laws of gravitational attraction. The shape of the light curve, with its relatively flat portions between eclipses and its gradual dimming and brightening during the eclipse itself, was consistent with one object passing in front of another, with the gradual changes reflecting the partial phases of the eclipse as the obscuring body moved across the face of the brighter star. And the fact that Algol returned to exactly the same brightness after each eclipse was easily understood if the dimming was caused by obscuration rather than by some intrinsic change in the star itself. For once the obscuring body moved out of the way, the star would naturally appear as bright as before. Goodricke was careful in his paper to acknowledge that his hypothesis was just that, a hypothesis, and he noted that other explanations were possible, including the possibility that Algol might be a rotating body with dark spots on its surface, similar to sunspots, which would cause the star to appear dimmer when the spotted regions faced toward Earth. But he argued that the eclipsing companion hypothesis was the simplest and most natural explanation, and he was ultimately proven correct, though he did not live to see this vindication. The Royal Society received his paper favorably, and in recognition of his accomplishments, they awarded him the Copley Medal in 1783, which was at that time the most prestigious scientific award in Britain, an honor that had previously been bestowed upon such luminaries as Benjamin Franklin and Joseph Priestley. Goodricke was just 19 years old when he received this recognition, and the fact that it was given to a deaf young man who had never attended a university speaks to the genuine merit of his work and to the willingness of the scientific community of that era to recognize talent regardless of its origin. In the years that followed his work on Algol, Goodricke continued his astronomical observations, and he made further contributions to the study of variable stars, including the discovery of the variability of beta Lyrae and delta Cephei, the latter of which would prove particularly important in the 20th century as a tool for measuring cosmic distances. He worked closely with Edward Pigott throughout this period, and the two friends continued to refine their methods and to expand their catalogue of variable stars, though they approached their collaboration with a generosity of spirit that was notable for its time, each crediting the other for their contributions and neither seeking to claim sole credit for their joint accomplishments. The friendship between Goodricke and Pigott is a touching example of scientific collaboration at its best, with each partner bringing complementary skills and perspectives to their shared endeavor, and with mutual respect and affection underlying their professional relationship. But this fruitful collaboration was cut tragically short in the spring of 1786, when John Goodricke died at the age of just 21. The circumstances of his death are not entirely certain, but it is generally believed that he contracted pneumonia as a result of exposure to cold during his nighttime observations. For astronomical work in that era required observers to spend long hours outdoors in all weather, and the English climate is not kind to those who stand motionless in the open air through the long hours of a winter night. Some accounts suggest that Goodricke may have been weakened by his childhood illness, leaving him more vulnerable to respiratory infections, while others note that the winter of 1785 to 1786 was particularly severe, with cold and damp conditions that would have tested even a robust constitution. Whatever the precise cause, Goodricke's death robbed astronomy of one of its most promising young practitioners, and one can only wonder what further contributions he might have made had he been granted a longer life. Edward Pigott continued his astronomical work after his friend's death, though he never again achieved the kind of breakthrough that their collaboration had produced, and he lived until 1825, long enough to see the study of variable stars mature into a recognized branch of astronomy, though not long enough to see Goodricke's eclipsing binary hypothesis fully vindicated. For despite the elegance of Goodricke's explanation, and despite the Royal Society's recognition of his work, the eclipsing binary theory remained just one possible explanation among several throughout the 19th century, and many astronomers preferred alternative hypotheses, including the rotating starspot model that Goodricke himself had acknowledged as a possibility. The difficulty was that no one could directly observe the hypothetical companion to Algol, and without such direct evidence, the hypothesis remained speculative, however plausible it might seem. The confirmation of Goodricke's theory came at last in 1889, more than a century after his original observations, through the work of the German astronomer Hermann Karl Vogel at the Potsdam Observatory. Vogel was a pioneer in the application of spectroscopy to astronomical problems, using the technique of analyzing starlight through a prism to reveal information about the physical properties and motions of stars. When a star is moving toward the Earth, its light is shifted slightly toward the blue end of the spectrum, and when it is moving away, its light is shifted toward the red, a phenomenon known as the Doppler effect, and by carefully measuring these shifts in the spectral lines of starlight, astronomers could determine the radial velocity of stars, which is to say their motion toward or away from us along our line of sight. Vogel turned his spectroscope toward Algol and made a series of observations over the course of the star's variability cycle, and what he found was decisive evidence for the eclipsing binary hypothesis. He discovered that the spectral lines of Algol shifted back and forth in a regular pattern, moving toward the blue when the star was at one point in its cycle and toward the red at another. And this pattern of shifts corresponded precisely with what would be expected if Algol were orbiting around a common center of mass with an unseen companion. The velocity curve that Fogel measured matched the predictions of the eclipsing binary model with remarkable precision, and it showed that the companion to Algol, though too dim to be seen directly, was definitely present and was definitely a substantial body, probably a star in its own right rather than a planet. With this spectroscopic confirmation, Goodricke's hypothesis was at last elevated from the status of an ingenious speculation to that of established fact, and the eclipsing binary theory took its place as one of the fundamental concepts of stellar astronomy. In the years that followed Fogel's confirmation, astronomers discovered many other eclipsing binary systems, and they developed increasingly sophisticated methods for analyzing the light curves and radial velocity curves of these systems, extracting from them detailed information about the masses, sizes, and orbital characteristics of the component stars. Eclipsing binaries became invaluable tools for testing theories of stellar structure and evolution, for they provided one of the few ways to measure stellar masses directly, and they continue to be important objects of study to this day. All of this work traces its origins back to those quiet nights in York in the autumn of 1782, when a deaf young man watched the demon star blink and dim and brighten again, and had the insight to recognize what this slow celestial rhythm might mean. John Goodricke's story is in many ways a gentle one, despite its sad ending, for it speaks of patience and persistence, of careful observation and imaginative reasoning, of friendship and collaboration in the service of understanding. The silence in which he lived and worked perhaps attuned him in some way to the slow and silent processes of the heavens, where changes unfold over timescales that make human life seem brief indeed, and where the only voices are the faint signals of light that reach us across the vast distances of space. His deafness, which might have been an insurmountable obstacle in another field, proved to be no impediment to astronomical observation, for the stars speak to us not in sounds but in light, and Goodricke had eyes to see what they were telling him. And though he died young, his ideas lived on, waiting patiently for more than 100 years until the technology existed to confirm what he had understood, and his name is still honored by astronomers today as one of the founders of variable star research. As you rest now, perhaps you might spare a thought for young Goodricke, standing in the cold Yorkshire night, watching Algol dim and brighten according to its ancient rhythm, and understanding for the first time that this flickering light was the signature of two stars, locked together in an endless dance, one bright and one dim, circling one another as they have circled for millions of years and will continue to circle for millions more. The demon star, it turns out, was never a demon at all, but simply a pair of suns, doing what suns do, following the laws of gravity and motion as all celestial bodies must. There is something peaceful in that thought, something reassuring in the knowledge that even the most unsettling mysteries of the night sky can yield to patient observation and careful reasoning, and that the universe, for all its vastness and strangeness, operates according to principles that the human mind can grasp. And with that thought, you might let your own eyes close now, as Goodricke's once closed for the last time, knowing that the stars will continue their slow and silent motions whether we watch them or not, and that there will always be time enough, tomorrow or some other day, to look up again and wonder at what we see. In the autumn of 1784, in the ancient city of York in northern England, a young man of 20 years sat at the window of his family's home on Treasurer's House, just beside the Great York Minster, and gazed upward at the constellation Cephei as it wheeled slowly through the September sky. His name was John Goodricke, and he had been deaf since early childhood, having lost his hearing to scarlet fever when he was perhaps 5 years old, though he had learned to communicate with remarkable fluency through lip reading and through his own careful, measured speech. The night was clear and still, as September nights in Yorkshire can sometimes be, and the stars hung bright and steady in the darkness above the medieval rooftops, and Goodricke was watching, as he had watched on so many nights before, with the patient attention that would soon lead him to one of the most important discoveries in the history of stellar astronomy. The star he was observing that night, and on the nights that followed through late September and into October, was one that we now call Delta Cephei, a star of modest brightness in the constellation of the King, visible to the unaided eye as a faint point of light not far from the more prominent stars that mark out the distinctive shape of that northern constellation. Goodricke had noticed, with his careful eye and his methodical approach to observation, that this star did not maintain a constant brightness from night to night, but rather seemed to vary in a regular and predictable way, growing brighter and then dimmer and then brighter again in a cycle that repeated itself over and over with remarkable consistency. This was not the first variable star that Goodricke had discovered, for he had already made his name in astronomical circles through his brilliant work on Algol in the constellation Perseus. But Delta Cephei would prove to be something altogether different, a new type of variable star that would eventually become one of the most important tools in the astronomer's understanding of the universe. Goodricke recorded his observations with meticulous care, noting the brightness of Delta Cephei on each clear night and comparing it to the brightnesses of other nearby stars that did not vary, and over the weeks and months that followed, he was able to determine the period of the star's variation with impressive precision. The cycle, he found, took approximately 5 days, 8 hours, and 47 minutes to complete, a period that has been refined only slightly by modern measurements using instruments of far greater sensitivity than anything available to an observer in the 18th century. This regularity was itself remarkable, for it suggested that whatever was causing the star to vary in brightness was operating according to some consistent physical process, some underlying mechanism that repeated itself with clockwork precision, though Goodricke could not have known what that mechanism might be, and indeed the true explanation would not be understood for well over a century after his death. The way in which Delta Cephei varied was also distinctive and unlike the variations that Goodricke had observed in Algol. When he plotted the brightness of the star against time, the resulting curve had a characteristic shape that astronomers would later describe as sawtooth, though Goodricke himself did not use this term. The star would brighten quite rapidly, rising from its minimum brightness to its maximum over a relatively short portion of its cycle, perhaps a day or a day and a half, and then it would fade more slowly, declining gradually back to its minimum brightness over the remaining 3.5 or 4 days of the period before beginning to brighten again. This asymmetry, this rapid rise and slower fall, would prove to be one of the defining characteristics of what would eventually be called Cepheid variable stars, named after this very star that Goodricke was watching from his window in York, though he could not have known that his discovery would one day lend its name to an entire class of cosmic distance indicators. But Goodricke was not working entirely alone in his observations, and his discovery of Delta Cephei was part of a broader collaborative effort that had been ongoing for several years in the intellectual and scientific community of York. His closest collaborator, mentor, and friend was a man named Edward Pigott, who was some 11 years older than Goodricke and who had been observing the heavens from his own home in York since the early 1780s. Piggott came from a family with strong scientific interests, and his father, Nathaniel Piggott, was himself an accomplished astronomer who had observed transits of Venus and had established a private observatory that Edward would later inherit and expand. The Piggotts had moved to York in 1781, and it was there that Edward met the young John Goodricke, recognizing almost immediately the exceptional talent and dedication that the younger man brought to the study of the stars. The partnership between Piggott and Goodricke was one of mutual benefit and genuine friendship. Though Piggott was clearly the more experienced observer and provided much of the equipment and guidance that made Goodricke's work possible, Piggott had access to better telescopes and instruments than Goodricke could have afforded on his own, and he shared these resources generously with his young colleague, providing not only the physical tools of observation but also the intellectual framework within which to interpret what they saw. The two men would meet regularly to discuss their observations, to compare their measurements, and to plan their future work, and their collaboration produced a remarkable series of discoveries in a very short period of time, a flowering of astronomical knowledge that arose from the combination of Piggott's experience and resources with Goodricke's keen eye and tireless dedication. Indeed, just days before Goodricke made his observations of Delta Cephei in September of 1784, Piggott himself had discovered another variable star of the same general type, a star in the constellation Aquila that we now call Eta Aquili. Piggott announced his discovery on the 10th of September, and Goodricke followed with his own announcement regarding Delta Cephei shortly thereafter, so that the two friends had, within the space of a few weeks, discovered two of the most important examples of what would become known as Cepheid variables. Eta Aquili has a period of approximately 7 days, 3 hours, and 48 minutes, somewhat longer than that of Delta Cephei but showing the same characteristic light curve, the same rapid brightening and slower fading, the same clockwork regularity that marked these stars as somehow fundamentally different from the eclipsing binaries like Algol or the long-period variables like Mira. The intellectual environment of York in the 1780s was conducive to this kind of careful, systematic astronomical work, for the city had a thriving community of natural philosophers and amateur scientists who met regularly to discuss their observations and to share their discoveries. The York Philosophical Society would not be formally established until 1822, but the spirit of scientific inquiry that would animate that institution was already present in the informal networks of correspondence and conversation that linked observers like Piggott and Goodricke with astronomers elsewhere in England and on the continent. York was a prosperous city with a long history, home to wealthy merchants and professional men who had the leisure and the means to pursue scientific interests, and the presence of the Great Minster created an atmosphere of learning and contemplation that may have encouraged the patient, careful observation that astronomy requires. Goodricke presented his findings on Delta Cephei to the Royal Society in London, as he had done with his earlier work on Algol, and the quality of his observations and the clarity of his reasoning earned him considerable respect in the astronomical community despite his youth and his deafness. The Royal Society awarded him the Copley Medal in 1783 for his work on Algol, a remarkable honor for someone who was then only 19 years old, and his subsequent discoveries only added to his reputation as one of the most promising astronomers of his generation. But Goodricke's career was to be tragically short, for he died in April of 1786, just a few weeks after being elected a Fellow of the Royal Society, at the age of only 21. The cause of his death is not entirely certain, but it has often been attributed to pneumonia brought on by the long hours he spent observing in the cold night air of York, though some historians have suggested that he may have suffered from other health problems related to his childhood illness. The loss of John Goodricke was a profound blow to the astronomical community and a personal tragedy for Edward Pigott, who had lost not only a brilliant colleague but also a dear friend. But Pigott did not abandon the work that he and Goodricke had begun together, and in the years that followed he continued to search for new variable stars and to refine the observations of those already known. His most significant later discovery came in 1795, when he identified the variability of a star in the constellation Scutum that we now call our Cephei. This star proved to be yet another type of variable, different from both the Cepheids and the eclipsing binaries, belonging to a class that astronomers would later call semi-regular variables because their periods, while roughly consistent, show more variation from cycle to cycle than the highly regular Cepheids. Pigott continued to observe and to publish his findings well into the 19th century, serving as a living link between the pioneering work he had done with Goodricke and the new generation of astronomers who would build upon their discoveries. The stars that Goodricke and Pigott discovered, Delta Cephei and Eta Aquila, along with other similar stars identified in the decades that followed, would eventually give their collective name to an entire class of variable stars, the Cepheid variables, though this terminology did not come into use until much later. These stars share certain defining characteristics that set them apart from other types of variables. They are intrinsically luminous, much brighter than our Sun, and they pulsate in a regular, rhythmic way, expanding and contracting over periods ranging from about 1 day to several months. Their light curves show the distinctive sawtooth pattern that Goodricke observed, with a rapid rise to maximum brightness followed by a slower decline to minimum, and this pattern repeats with a regularity that rivals the finest mechanical clocks. The cause of this pulsation, we now understand, lies in the physics of the star's outer layers, where helium atoms cycle between different states of ionization in a way that traps and releases energy, driving the star to expand and contract like a slowly beating heart, though none of this was known or even suspected in Goodricke's time. The true cosmic importance of the Cepheid variables would not be realized until well over a century after Goodricke's death, when an American astronomer named Henrietta Swan Leavitt, working at the Harvard College Observatory in the early 1900s, discovered a remarkable relationship between the period of a Cepheid's variation and its intrinsic luminosity. Leavitt found that the longer a Cepheid's period, the more luminous the star, and this period-luminosity relation, as it came to be called, transformed the Cepheids from interesting curiosities into powerful tools for measuring distances in the universe. If you know how bright a star truly is, and you can measure how bright it appears to be from Earth, then simple mathematics allows you to calculate how far away it must be. And since the period of a Cepheid can be measured with great precision simply by watching it for a few weeks or months, the period-luminosity relation provides a way of determining cosmic distances that remains in use to this day. But all of that lay far in the future as Edward Pigott continued his observations in York through the 1790s and into the new century, and as other astronomers in England and across Europe added to the slowly growing catalogue of known variable stars. The work was painstaking and often tedious, requiring night after night of careful watching and recording, comparing the brightness of one star against another, noting the time and the conditions and the appearance of the sky, building up a picture of stellar behavior one observation at a time. There were no photographs in those days, no electronic detectors, no computers to process the data, only the human eye and the human mind, trained and patient and attentive to the small changes that might reveal something new about the nature of the stars. Goodricke's observations of Delta Cephei were made with the simplest of equipment, primarily his own eyes and a pocket watch and a notebook in which to record what he saw. He used the technique of comparing the brightness of the variable star to nearby stars of known and constant brightness, estimating where the variable fell on a scale defined by these comparison stars, a method that astronomers would continue to use for more than a century until photographic and photoelectric techniques made more precise measurements possible. The precision that Goodricke achieved with these simple tools was remarkable, and his determination of the period of delta Cephei was accurate to within a few minutes, a testament to his careful methods and his exceptional observational skills. The city of York itself played a quiet but important role in these discoveries, providing the stable base from which Goodricke and Pigott could pursue their observations. The medieval walls and towers, the great bulk of the minster rising above the narrow streets, the slow curve of the River Ouse through the heart of the city, all of these formed the backdrop against which the two astronomers conducted their work, stepping out into their gardens or positioning themselves at upstairs windows to gain a clear view of the night sky. The latitude of York, about 54 degrees north, meant that the constellation Cepheus was circumpolar, never setting below the horizon, and delta Cephei could be observed on any clear night throughout the year, making it an ideal target for the kind of sustained, systematic observation that revealing its variability required. We may imagine, though we cannot know for certain, the quiet satisfaction that Goodricke must have felt as the pattern of delta Cephei's variation became clear to him, as night after night confirmed the regularity of its brightening and fading, as the period emerged from his careful records with ever greater precision. He could not have known that he was laying the groundwork for one of the great distance ladders of 20th century cosmology, that the star he watched from his window in York would one day give its name to a class of objects used to measure the distances to galaxies millions of light-years away. He was simply doing what he loved, observing the stars with care and recording what he saw, contributing his small part to the great collective enterprise of human knowledge, one clear night at a time. The Cepheid variables, including delta Cephei itself, continue to be observed today with instruments of far greater power and precision than anything Goodricke could have imagined, orbiting telescopes and digital detectors and sophisticated analysis techniques that can tease out subtle variations invisible to the human eye. But the fundamental discovery remains his: the recognition that this particular star varies in brightness with a regular period and a distinctive light curve, and the careful measurement of that period to an accuracy that modern observations have refined but not dramatically improved upon. It is a reminder that progress in science often depends not on the most advanced instruments but on the most careful and dedicated observers, those who watch and wait and record and think, building the foundations on which future generations will construct their grander theories. And so we may leave John Goodricke at his window in York, watching the slow pulse of delta Cephei through the autumn nights of 1784, and Edward Pigott in his observatory nearby, the two friends pursuing together a shared passion for the stars that would lead them to discoveries whose full significance they could never have suspected. The standard candle was beginning to emerge from the darkness, though it would be many decades before anyone recognized it for what it was, a beacon that would one day illuminate the true scale of the cosmos and reveal the universe to be vaster and grander than any observer in the 18th century could have dreamed. In the city of Bonn, along the gentle curves of the Rhine, there stood an observatory where a patient man spent his evenings looking upward, developing methods that would shape the practice of variable star observation for more than a century to come. Friedrich Wilhelm Argelander arrived at the Bonn Observatory in 1837, having already established himself as a careful and methodical astronomer through his earlier work in Finland and his studies of stellar proper motion. He was not a man given to hurry, and this quality of unhurried precision would prove to be exactly what the field of variable star observation required at that particular moment in its development. The problem facing astronomers who wished to study variable stars in the early 19th century was fundamentally one of measurement. How does one determine, with any degree of reliability, just how bright a star appears on any given night? And how does one compare that brightness to previous observations made by other astronomers at other times and in other places? The instruments available for measuring stellar brightness were few and often inconsistent, and the terminology used to describe magnitude was imprecise in ways that made comparison between different observers quite difficult. What was needed was a method that could be used consistently by many different people, that required no expensive or specialized equipment, and that would yield results accurate enough to reveal the patterns of variation that astronomers suspected lay hidden in the changing light of these peculiar stars. Argelander devoted considerable thought to this problem throughout the late 1830s and into the 1840s, and the method he developed was elegant in its simplicity. Rather than attempting to assign an absolute brightness value to a variable star on any given night, an observer would instead compare the variable to nearby stars of known and constant brightness, determining which comparison star appeared most similar in brightness and by how much the variable differed from its neighbors. This technique of differential comparison removed many of the difficulties inherent in absolute measurement, because the human eye, while not particularly reliable at judging absolute brightness, is remarkably sensitive to small differences in brightness between objects viewed simultaneously or in quick succession. The refinement that Argelander introduced, and which came to bear his name, was the concept of the step. A step represented the smallest difference in brightness that an observer could reliably detect between two stars. If a variable star appeared exactly equal in brightness to a comparison star, this would be recorded as a step of 0. If the variable appeared very slightly fainter than the comparison, perhaps just barely perceptibly so, this might be recorded as 1 step fainter. 2 steps would indicate a more noticeable difference, 3 steps a difference that was quite obvious to the eye, and so on. By establishing a consistent vocabulary for these small gradations of brightness, Argelander made it possible for different observers to communicate their measurements in terms that could be meaningfully compared. The beauty of this system lay in its accessibility. An observer required nothing more than a telescope of modest aperture, a chart showing the positions of suitable comparison stars, and patience enough to make careful observations over many nights. There was no need for expensive photometric equipment, no requirement for complex calibration procedures, no dependence on mechanisms that might fail or fall out of adjustment. The instrument was the human eye itself, and while individual eyes might differ somewhat in their sensitivity, the differential nature of the comparison method meant that these differences mattered far less than they would in absolute measurement. In 1844, Argelander published a document that would become foundational to the organized study of variable stars. His appeal to the Friends of Astronomy, written in German with the title Aufforderung an Freund der Astronomie, was essentially an invitation to amateur astronomers everywhere to participate in the systematic observation of variable stars using his step estimation method. The document was remarkable both for its practical clarity and for its democratic spirit. Argelander recognized that the professional observatories of the world, few in number and occupied with many competing demands, could not possibly maintain continuous surveillance of all the variable stars that deserved attention. But if dedicated amateurs could be enlisted in this work, if they could be provided with clear instructions and reliable comparison sequences, Then a network of observers might accomplish what no single observatory could achieve alone. The appeal laid out the method in careful detail. An observer would select a variable star for study, identify several comparison stars of known brightness in the same telescopic field or nearby, and then on each clear night make a systematic comparison of the variable against each of these reference stars. The results would be recorded using a simple notation that indicated which comparison stars were brighter than the variable, which were fainter, and by how many steps the variable differed from each. From these observations, the brightness of the variable could be interpolated with considerable precision, and over time the accumulated observations would reveal the pattern of the star's variation. Meanwhile, Argelander had embarked on an even more ambitious project at Bonn, one that would occupy him and his assistants for more than a decade and would result in one of the great catalogues of 19th-century astronomy. The Bonner Durchmusterung, or Bonn Survey, was an attempt to record the position and brightness of every star visible through a modest telescope in the northern sky. The work began in 1852 and continued through 1859, with Argelander and his assistants Eduard Schonfeld and Adalbert Kruger systematically sweeping the sky and recording what they observed. The completed catalogue contained the positions and estimated magnitudes of more than 300,000 stars, and it became an indispensable reference for astronomers throughout the world. For variable star observers, the Bonner Durchmusterung was particularly valuable because it provided a vast network of comparison stars with estimated magnitudes. An observer wishing to monitor a variable star could consult the catalogue to identify suitable comparison stars in the vicinity, and the magnitudes assigned in the catalogue, while not perfectly precise by later standards, were consistent enough to serve as a useful framework for differential observations. The catalogue demonstrated what patient, systematic visual work could accomplish, and it reinforced the credibility of careful visual estimation as a legitimate tool for astronomical measurement. The question of what exactly a magnitude meant, in numerical terms, had been a source of some confusion since ancient times. The original system, attributed to the Greek astronomer Hipparchus and refined by Ptolemy, divided the visible stars into 6 classes of brightness, with first magnitude stars being the brightest and sixth magnitude stars being the faintest visible to the unaided eye. But this ancient system was imprecise in its definition and inconsistent in its application. Different astronomers assigned different magnitudes to the same stars, and there was no agreed upon mathematical relationship between one magnitude and the next. This uncertainty was addressed in 1856 by the English astronomer Norman Robert Pogson, who proposed a precise mathematical definition for the magnitude scale. Pogson observed that first magnitude stars appeared roughly 100 times brighter than sixth magnitude stars, spanning a range of 5 magnitudes. He suggested that the scale should be defined such that a difference of 5 magnitudes corresponded to exactly a factor of 100 in brightness. This meant that each single magnitude step represented a brightness ratio equal to the fifth root of 100, which works out to approximately 2.512. A star of magnitude 2 is about 2.512 times fainter than a star of magnitude 1. A star of magnitude 3 is about 2.512 times fainter again than magnitude 2, and so on down the scale. This logarithmic definition brought mathematical consistency to a system that had previously been somewhat arbitrary. It meant that magnitude differences could be converted into actual brightness ratios through straightforward calculation, and that instruments designed to measure stellar brightness could be calibrated against a well-defined standard. Pogson's formalization did not change the practice of visual estimation in any fundamental way, Observers still compared variables to comparison stars and estimated differences in steps, but it provided a rigorous framework within which those estimates could be interpreted and combined with more precise instrumental measurements. The development of instruments for measuring stellar brightness more precisely continued alongside the refinement of visual methods. In 1861, the German physicist Johann Carl Friedrich Zollner introduced his visual photometer, a device that allowed an observer to make quantitative comparisons between a star and an artificial light source of adjustable brightness. The instrument worked by creating a small point of light that could be varied in intensity through known amounts, and the observer would adjust this artificial star until it appeared to match the brightness of the star being measured. By recording the setting required to achieve this match, the observer could determine the brightness of the star with greater precision than simple step estimation allowed. Zollner's photometer represented an important advance in the technology of stellar brightness measurement, and instruments based on his design saw use at many observatories in the latter half of the 19th century. However, the visual photometer was a specialized piece of equipment that required careful calibration and considerable skill to use effectively. It was well suited to the needs of professional observatories, where accurate magnitude determinations were required for specific research programs, but it was not practical for the sort of wide-ranging surveillance work that amateur observers using the Argelander method could accomplish. The two approaches, careful instrumental measurement and systematic visual estimation, thus developed in parallel, each serving different but complementary purposes in the study of variable stars. Among the observers who contributed to the accumulation of visual magnitude data during this period was Eduard Hayes, a German astronomer and educator who made extensive naked-eye observations of the stars. Hayes was particularly interested in mapping the distribution of stars visible without optical aid, and he produced an atlas of the naked-eye sky that included careful estimates of stellar magnitudes. His observations provided a valuable baseline for understanding the brightness of the brighter stars, including many of the more prominent variable stars that could be followed without a telescope. The work of Hayes demonstrated that useful scientific observations could be made with no instruments at all, merely through patient and systematic attention to the appearance of the night sky. The Argelander method proved remarkably durable as a practical technique for monitoring variable stars. Throughout the latter half of the 19th century and well into the 20th, amateur observers around the world continued to make step estimates in essentially the same way that Argelander had described in his 1844 appeal. The method required only modest equipment. It could be learned with reasonable ease, and it produced results that, when averaged over many observations by many observers, revealed the light curves of variable stars with impressive accuracy. Professional astronomers came to rely on the accumulated observations of amateur networks, recognizing that the sustained attention of dedicated amateurs could accomplish what the limited time available at professional observatories could not. The comparison sequences that observers used gradually became more refined as photometric measurements provided increasingly accurate magnitudes for the comparison stars. Organizations devoted to variable star observation, such as the American Association of Variable Star Observers founded in 1911, worked to standardize these sequences and to train observers in consistent techniques. The fundamental approach remained what Argelander had outlined, a careful comparison of the variable against nearby stars of known brightness, with the difference expressed in fractional steps that could be converted to magnitudes and combined with other observers' estimates. There is something rather peaceful in contemplating this long tradition of patient watching. Generations of observers, spread across many countries and many decades, spent their clear evenings looking upward at the same stars, making the same comparisons, recording their estimates in notebooks and on forms that would eventually find their way into the archives of variable star organizations. Each individual observation was imprecise, subject to the vagaries of atmospheric conditions and personal perception, but the accumulated weight of thousands upon thousands of estimates revealed patterns that no single observation could have shown. The slow pulsations of long-period variables, the sudden brightenings of cataclysmic stars, the subtle undulations of semi-regular variables, all of these emerged from the patient accumulation of visual estimates made by observers using methods that Argelander would have recognized and approved. The technique persisted not because better methods were unavailable, but because the Argelander approach remained genuinely useful for certain purposes. Photoelectric photometry, which emerged in the early 20th century, could measure stellar brightness with far greater precision than the human eye could achieve. But photoelectric instruments were expensive and required considerable technical expertise to operate effectively. For an amateur observer with a modest telescope and a few hours of clear sky each week, the visual step method remained the most practical way to contribute meaningful data to the ongoing study of variable stars. As the 20th century progressed, the proportion of variable star observations made visually gradually declined as photographic and later electronic methods became more widespread. But visual observation never entirely disappeared from the practice of variable star astronomy. There remained stars whose variations were best suited to visual monitoring, observers who preferred the direct connection of eye to sky, and circumstances where the simplicity and portability of visual methods outweighed the advantages of more complex instrumentation. The heritage of Argelander's careful methodology thus extended across more than a century of astronomical practice, a testament to the enduring value of patient, systematic observation using the simplest of instruments, the attentive human eye. The magnitude scale that Pogson formalized, the comparison sequences that accumulated through decades of careful work, the step estimation technique that Argelander described so clearly, all of these elements combined to create a framework within which variable star observation could flourish. It was not a framework that demanded genius or expensive equipment, but rather one that rewarded consistency, patience, and dedication to the gradual accumulation of reliable data. In this sense, the art of visual magnitude estimation embodied something essential about the nature of astronomical research, the recognition that understanding often emerges not from single brilliant insights but from the steady, unhurried accumulation of careful observations over many years and by many hands. And so we turn now to a quieter chapter in our story, one that concerns the stars that seemed to appear where no star had been before, the stars that blazed into visibility and then, over weeks or months, faded back into the darkness from which they had seemingly emerged. These are the novae, a word that comes to us from the Latin for new, and for many centuries astronomers believed that this was precisely what they were witnessing, the birth of entirely new stars in the heavens, or perhaps the unveiling of stars that had always existed but had been somehow hidden from our view. The true nature of these events would take centuries to unravel, and even now, as you listen to these words and perhaps feel your eyes growing a little heavy, there remains much that we are still learning about these remarkable celestial phenomena. But let us begin our journey in the 16th century, with a young Danish nobleman who looked up at the sky one November evening and saw something that would change his life and, in time, change our understanding of the cosmos itself. Tycho Brahe was born in 1546 into a family of Danish nobility, and from an early age he showed a keen interest in the workings of the heavens, an interest that was somewhat unusual for a young man of his social standing, but which his family eventually came to accept and even encourage. On the evening of the 11th of November in 1572, Tycho was walking home from his alchemical laboratory when he happened to glance up at the constellation of Cassiopeia, that familiar W-shaped pattern of stars that circles the north celestial pole. And there he saw something extraordinary. A star was shining in Cassiopeia where no star had shone before, a star so bright that it rivaled Venus in its brilliance and could be seen clearly even in the full light of day. Tycho was at first inclined to doubt his own eyes, and he stopped several passers-by to confirm that they too could see this remarkable visitor, which they could. And so he returned home in a state of considerable intellectual excitement to begin what would become 16 months of careful observation. The star that Tycho observed, which we now call SN 1572 or sometimes simply Tycho's supernova, remained visible to the naked eye until March of 1574, slowly fading over that period from its initial magnificent brightness to invisibility. Tycho made meticulous measurements of its position, using instruments of his own design that were the most accurate of his era, and he was able to demonstrate that the star showed no measurable parallax, which meant that it must be located far beyond the Moon, among the fixed stars themselves. This was a deeply significant finding, for the prevailing Aristotelian cosmology of the time held that the heavens beyond the Moon were perfect and unchanging, incapable of corruption or alteration of any kind. Here was clear evidence that change could and did occur in the supposedly immutable realm of the stars, and Tycho published his findings in a small book titled De Nova Stella, from which we derive our modern term nova. The book made Tycho famous throughout Europe and secured him the patronage of the Danish king, who provided him with the island of Hven and the resources to build his famous observatory, Uraniborg, where he would spend the next 20 years making the observations that would later enable Johannes Kepler to discover the laws of planetary motion. Speaking of Kepler, it is to him that we now turn, for in 1604, just 3 years after Tycho's death, another brilliant new star appeared in the sky, this time in the constellation of Ophiuchus, the serpent-bearer. Kepler first observed this star on the 17th of October, although it had actually been spotted a few days earlier by other observers whose records have come down to us, and he followed it with great attention for over a year as it slowly faded from view. Like Tycho's star before it, Kepler's star, as it came to be known, was bright enough to be seen in daylight, reaching perhaps magnitude -2.5 at its peak, which made it brighter than any planet except Venus. Kepler published his observations in a book titled De Stella Nova in Pede Serpentarii, and like Tycho before him, he used the lack of observable parallax to argue that the star was located among the fixed stars, far beyond the planetary spheres. What neither Tycho nor Kepler could have known, of course, was that the events they had witnessed were not ordinary novae at all, but supernovae, vastly more energetic explosions that mark the death of massive stars or the thermonuclear destruction of white dwarfs. This distinction would not be clearly understood until the 1930s, when Walter Bade and Fritz Zwicky proposed the existence of supernovae as a separate class of stellar explosion. But we are getting rather ahead of ourselves. And for now it is enough to note that these two observations, separated by just 32 years, were the last supernovae to be observed in our own galaxy with the naked eye, and no comparable event has occurred in the 4 centuries since. The period between Kepler's supernova and the 19th century saw numerous observations of stellar novae, though none as spectacular as the events of 1572 and 1604. William Herschel, That indefatigable observer of the heavens whom we have encountered before in our discussions of double stars and nebulae, naturally took an interest in these phenomena when they occurred during his long career. Herschel was primarily occupied with his systematic surveys of the sky, cataloguing nebulae and double stars and mapping the structure of the Milky Way, but he was always attentive to anything unusual that might present itself during his nightly observations. He was aware of the historical accounts of Tycho's and Kepler's stars, and he speculated about the nature of these objects in his papers, considering various possibilities, including the idea that they might represent stars that had somehow been obscured and then revealed, or stars that had undergone some kind of conflagration. His catalogues, which would later be incorporated into the new general catalogue that astronomers still use today, included many objects that would prove relevant to the study of novae, including planetary nebulae and the shells of gas that surround certain types of evolved stars, though the connections between these objects and nova explosions would not become clear for many decades. Let us move forward now to the year 1866, and to the quiet countryside of Ireland, where a gentleman astronomer named John Birmingham was spending his evenings observing the sky from his home near Tuam in County Galway. Birmingham was primarily interested in the observation of red stars, which he had been cataloguing systematically for some years, and on the night of the 12th of May he was scanning the constellation of Corona Borealis, the Northern Crown, a small but distinctive semicircle of stars that lies between Boötes and Hercules. As he observed this familiar region, his eye was caught by a star that he did not recognize, a star of approximately the second magnitude shining steadily where no such star should have been. Birmingham was a careful observer who knew the sky well, and he immediately suspected that something unusual had occurred. He contacted other astronomers to report his discovery, and over the following nights the star was observed to brighten further, reaching magnitude 2.0 before beginning a slow decline that would return it to invisibility within a few weeks. This was the first recorded outburst of the star that would come to be known as T Coronae Borealis, or more poetically as the Blaze Star, and it would prove to be one of the most important novae in the history of astronomy. What made T Coronae Borealis particularly significant was not its brightness, which was considerable but not exceptional, but rather what happened 80 years later. In February of 1946, the Blaze Star erupted again, brightening from its quiescent magnitude of about 10 to a peak of around magnitude 3 in a matter of hours, and then slowly fading back to obscurity over the following months. Here was clear evidence that at least some novae were recurrent phenomena, stars that could undergo repeated explosions rather than experiencing a single catastrophic event. The discovery of this recurrence, and the subsequent identification of other recurrent novae, would prove crucial to understanding the physical mechanisms behind these explosions, for it suggested that the outburst did not destroy the star but rather represented some kind of cyclical process that could repeat itself over timescales of decades to centuries. We now understand that T Coronae Borealis is a binary system consisting of a red giant star and a white dwarf, and that matter flows from the red giant onto the surface of the white dwarf, accumulating until it reaches a critical temperature and density at which it undergoes a runaway thermonuclear explosion, blowing off the accumulated material and causing the star to brighten dramatically before settling back into its quiescent state to await the next outburst. The Blaze Star continues to be monitored by astronomers and amateur observers alike, as there is evidence to suggest that another eruption may occur at some point in the coming years, though the exact timing of such events remains difficult to predict. The turn of the 20th century brought with it another spectacular nova that would contribute significantly to our understanding of these phenomena. On the night of the 21st of February in 1901, a Scottish amateur astronomer named Thomas David Anderson was walking home through the streets of Edinburgh when he glanced up at the constellation of Perseus and noticed an unfamiliar star shining brightly in the region between Algol and Delta Persei. Anderson was an experienced observer who had already discovered one nova, Nova Aurigui of 1892, and he immediately recognized that he was looking at another. He sent a telegram to the Royal Observatory in Greenwich to report his discovery, and within hours astronomers around the world were training their instruments on the new star. Nova Persei 1901, as it came to be known, proved to be one of the most remarkable novae ever observed, reaching a peak magnitude of 0.2 on the 23rd of February, which made it one of the brightest stars in the sky, comparable to Vega or Capella, before beginning a complex decline that included several secondary maxima over the following months. But the most extraordinary aspect of Nova Persei 1901 was not its brightness but rather what was revealed when astronomers photographed the surrounding region of sky in the months and years that followed. Beginning in September of 1901, photographs showed an expanding nebula surrounding the position of the nova, a shell of light that appeared to be moving outward at an astonishing rate. When astronomers calculated the apparent velocity of this expansion based on its angular growth across the sky, they obtained a figure that seemed to exceed the speed of light, which was clearly impossible. The explanation for this apparent paradox turned out to be that the nebula was not a shell of material ejected from the nova at all, but rather a light echo, a phenomenon in which light from the initial explosion was being reflected off pre-existing clouds of dust and gas in the surrounding interstellar medium, creating the illusion of superluminal expansion. This was the first light echo ever observed, and its discovery opened up new possibilities for studying the history of stellar explosions long after the initial event had faded from view. The study of Nova Persei 1901 contributed greatly to the growing understanding that novae were genuine explosions that ejected material into space, rather than simply the unveiling of previously hidden stars. And the photographs of its expanding light echo remain among the most striking astronomical images of the early 20th century. The First World War was drawing to its weary close in the summer of 1918 when another brilliant nova appeared in the sky, this time in the constellation of Aquila, the Eagle, which rides high in the summer skies of the Northern Hemisphere. Nova Aquila 1918 was discovered independently by several observers on the 8th of June, when it was already a naked-eye object, and over the following days it continued to brighten until it reached a peak magnitude of -1.1 on the 9th of June, making it the brightest nova observed since Kepler's supernova of 1604, and indeed the brightest nova that would be observed in the 20th century. At its maximum, Nova Aquila outshone every star in the sky except Sirius, and it remained visible to the naked eye for several years as it slowly faded. The nova attracted enormous public interest at a time when people were perhaps looking for any distraction from the horrors of the war, and it provided astronomers with an unprecedented opportunity to study a nova at close range. For subsequent distance measurements would show that Nova Aquila was located only about 1600 light-years from Earth, making it one of the nearest novae ever observed. The detailed observations of Nova Aquila 1918, combined with the growing body of data from earlier novae, allowed astronomers to begin piecing together a coherent picture of what these objects actually were. The old idea that novae represented the birth of new stars, or the sudden appearance of stars that had previously been hidden, was gradually giving way to the understanding that these were genuine stellar explosions, events in which an existing star underwent some kind of catastrophic outburst that caused it to brighten enormously before returning to a more quiescent state. Spectroscopic observations showed that novae ejected material at velocities of hundreds or thousands of kilometers per second, and that the expanding shells of gas displayed complex chemical compositions that suggested nuclear processes were at work. The recognition that some novae, like T. Coronii borealis, could undergo repeated outbursts suggested that the underlying star survived the explosion and could erupt again once conditions became favorable, and this in turn pointed toward the involvement of binary star systems, in which matter could be transferred from one star to another, providing the fuel for periodic explosions. By the middle of the 20th century, the broad outlines of nova physics were becoming clear, though many details remained to be worked out. Astronomers understood that classical novae occurred in close binary systems containing a white dwarf star, the dense remnant of a Sun-like star that had exhausted its nuclear fuel, and a companion star, often a red dwarf or red giant, from which matter flowed onto the white dwarf surface. As this hydrogen-rich material accumulated on the white dwarf, it was compressed and heated by the white dwarf's intense gravity until it reached the conditions necessary for thermonuclear fusion, at which point it ignited explosively, blowing off the accumulated layer and producing the brilliant flash of light that we observe as a nova. The white dwarf itself remained intact, and over time, more material would accumulate from its companion, setting the stage for another explosion decades or centuries in the future. This basic picture has been refined and elaborated in the years since, but its essential features remain our understanding of how classical novae occur. And so we have traced the history of nova observation from Tycho's brilliant star of 1572, through the careful work of Herschel and the discoveries of Birmingham and Anderson, to the spectacular novae of the early 20th century that helped establish our modern understanding of these remarkable events. The stars that seemed to appear from nowhere turned out to be stars that had always been there, too faint to see until some violent process within them caused them to blaze forth with a brightness that could not be ignored. In understanding the novae, astronomers gained new insights into the lives and deaths of stars, into the complex dance of matter and energy that plays out in binary systems across the galaxy, and into the restless, ever-changing nature of a universe that the ancients had believed to be perfect and immutable. These are thoughts that you might carry with you into sleep, if you wish, or you might simply let them drift away like the fading light of a nova past its peak, settling gradually into the soft darkness of the night. And so we come now to the gentle unfolding of light itself, to the quiet revelation that occurred when astronomers learned to take starlight and spread it into its component colors, much as a prism might spread sunlight into a rainbow upon a wall. This technique, which we call spectroscopy, would prove to be one of the most profound tools ever applied to the study of variable stars, for it allowed astronomers to move beyond merely measuring brightness and position, and to begin asking deeper questions about what stars actually were, what they were made of, how hot they burned, and how they moved through the vastness of space. The story of spectroscopy's contribution to variable star science is a gentle one, unfolding over decades through the patient work of many individuals, each adding their own careful observations to the growing body of knowledge. And it begins appropriately enough in a place of contemplation and quiet study, at the Vatican Observatory in Rome, where a Jesuit priest named Angelo Cephei turned his attention to the stars in the 1860s. Father Angelo Cephei was a man of methodical disposition and considerable patience, qualities that served him well in the demanding work of stellar spectroscopy. Working from the observatory atop the church of Sant'Ignazio, and later from a purpose-built dome on the roof of St. Peter's Basilica itself, Cephei undertook what was perhaps the first truly systematic survey of stellar spectra, observing and recording the spectral characteristics of several thousand stars over the course of many years. His approach was one of careful classification, much as a naturalist might sort specimens into related groups based on shared characteristics. And by 1866, he had developed a system that divided stars into four main types based on the patterns of dark lines and bands that appeared in their spectra. The first type showed strong hydrogen lines. The second displayed numerous fine metallic lines. The third exhibited broad dark bands that we now know are caused by molecules of titanium oxide. And the fourth type showed bands of carbon compounds. This work, though it may sound rather technical when described in this way, was of fundamental importance because it demonstrated that stars were not all identical points of light, but rather belonged to different families with genuinely different physical characteristics. And it laid the groundwork for all subsequent spectroscopic study of both constant and variable stars alike. Cephei himself observed some variable stars and noted their spectral characteristics, finding for instance that many of the long-period variables like Mira belonged to his third type with their distinctive molecular bands. But it was his contemporary William Huggins in England who would make some of the most dramatic early applications of spectroscopy to the study of stellar variability. Huggins was a wealthy amateur astronomer who had built a private observatory at Tulse Hill in South London, and he had equipped it with the finest spectroscopic apparatus available at the time. He was assisted in his work by his wife Margaret, who was herself a skilled observer and photographer, and together they pursued a program of stellar spectroscopy that would yield remarkable results. When the recurrent nova T Coronii Borealis underwent its dramatic brightening in May of 1866, rising from obscurity to become one of the brighter stars in the sky, Huggins was among those who turned their spectroscopes toward this unexpected visitor, and what he observed was quite unlike anything seen in ordinary stars. The spectrum of T Coronii Borealis during its outburst showed bright emission lines rather than the dark absorption lines that characterized normal stellar spectra, and this indicated that the star was surrounded by hot, luminous gas that was itself radiating light at specific wavelengths. Huggins recognized the characteristic green emission line of hydrogen, and he noted other bright lines as well, recording his observations with the careful precision that marked all his work. This was significant because it suggested that the brightening of the nova was not simply a matter of the star becoming hotter, but involved the ejection of material into space, creating a shell or envelope of glowing gas around the star. The nova faded relatively quickly, but Huggins's observations had demonstrated the power of spectroscopy to reveal physical processes occurring in variable stars, processes that could never have been detected through brightness measurements alone. His work on T Coronii Borealis, published in the Proceedings of the Royal Society, represented one of the first successful attempts to understand what was actually happening during a stellar outburst, and it set a precedent for spectroscopic observation of novae that would be followed throughout the following decades. Meanwhile, the problem of Algol, that ancient and puzzling star whose regular diminutions had been measured so carefully by Goodricke more than a century earlier, continued to occupy the minds of astronomers. The eclipsing binary hypothesis, which proposed that Algol's variations were caused by a darker companion star passing in front of the brighter primary, had been widely accepted on circumstantial grounds, but direct proof remained elusive. It was the German astronomer Hermann Karl Vogel who would finally provide the definitive confirmation through spectroscopic observation, working at the Potsdam Astrophysical Observatory in the late 1880s. Vogel reasoned that if Algol truly had a companion star orbiting around it, then both stars must be moving, approaching us and receding from us in turn as they circled their common center of mass. And this motion should produce a detectable shift in the wavelengths of the spectral lines, a phenomenon known as the Doppler effect. The Doppler effect, named for the Austrian physicist Christian Doppler, who had described it mathematically some decades earlier, causes light from an approaching source to be shifted slightly toward shorter wavelengths, toward the blue end of the spectrum, while light from a receding source is shifted toward longer wavelengths, toward the red. The effect is quite small for stellar velocities, amounting to shifts of less than 1/10 of a nanometer for typical orbital speeds, and detecting such tiny changes required both excellent equipment and painstaking measurement technique. Vogel possessed both, and by carefully measuring the positions of spectral lines in Algol's spectrum at different phases of its cycle, he was able to detect the predicted velocity shifts. When the bright star was approaching us, moving toward the observer in its orbit, the lines shifted slightly to the blue, and when it was receding, moving away as it passed behind its companion, the lines shifted slightly to the red. The results, published in 1889, demonstrated conclusively that Algol was indeed a binary system with the bright component orbiting a darker companion, exactly as Goodricke had proposed on purely photometric grounds more than a century before. This was a triumph of the spectroscopic method, and it opened up an entirely new field of study, for it meant that astronomers could now detect binary stars that were too close together to be separated visually, identifying them purely through the periodic shifts in their spectral lines. The category of spectroscopic binaries, as these systems came to be called, grew rapidly in the years following Vogel's discovery of Algol's orbital motion. Many stars that appeared perfectly constant in brightness were found to be binaries when examined spectroscopically, their spectral lines shifting back and forth with clockwork regularity as the component stars orbited each other. In some cases, both stars were bright enough to contribute visible spectral lines, and these lines could be seen to move in opposite directions, approaching and separating twice during each orbital period like dancers executing a slow waltz. In other cases, only one set of lines was visible, but their periodic shifting still betrayed the presence of an unseen companion. The study of spectroscopic binaries became an important branch of stellar astronomy in its own right, and it proved particularly valuable for determining stellar masses, since the orbital velocities combined with the period of the system could be used to calculate the gravitational forces at work and hence the masses of the stars involved. For eclipsing variables like Algol, where the orbital plane was aligned with our line of sight, the combination of spectroscopic velocities and photometric observations of the eclipses allowed astronomers to determine not only masses but also stellar radii and densities, building up a comprehensive physical picture of these binary systems that would have seemed impossibly detailed to observers of earlier generations. Across the Atlantic, at the Harvard College Observatory, a different approach to stellar spectroscopy was being developed under the direction of Edward Charles Pickering. Rather than observing individual stars one at a time with a slit spectroscope, Pickering pioneered the use of objective prism spectroscopy, in which a large prism was placed over the entire aperture of the telescope so that every star in the field of view produced its own small spectrum on the photographic plate. This technique was far less precise for detailed measurements than the slit spectroscope, but it allowed for the rapid survey of many thousands of stars, and it proved ideal for the task of classification and for identifying stars with unusual spectral characteristics. Under Pickering's direction, the Harvard Observatory embarked on an ambitious program to classify the spectra of all stars down to a certain brightness limit, a project that would eventually result in the Henry Draper catalogue containing spectral classifications for hundreds of thousands of stars. Much of the detailed classification work was carried out by a group of women astronomers, sometimes called the Harvard computers, who examined the photographic plates and assigned each star to its appropriate spectral class. Among these women was Antonia Maury, who brought to the classification work a remarkably keen eye for subtle differences in spectral line appearance. Maury was the niece of Henry Draper, the wealthy amateur astronomer whose widow had funded much of Harvard's spectroscopic work, and she had received an unusually thorough scientific education for a woman of her time. When she examined stellar spectra, she noticed that stars assigned to the same spectral class based on the types of lines present could nonetheless differ markedly in the appearance of those lines, with some stars showing sharp, narrow lines and others showing broad, diffuse lines. She developed her own classification system that incorporated this additional characteristic, adding a letter to each spectral class to indicate the line quality, with the letter C denoting stars with particularly sharp and well-defined lines. This C characteristic, as it came to be known, seemed at first to be merely a minor refinement of the classification system, but it would later prove to have profound significance. The Danish astronomer Ejnar Hertzsprung, studying Maury's classifications some years later, noticed that the C-type stars were systematically more luminous than other stars of the same spectral class, and this observation contributed to his recognition that stars of the same surface temperature could have vastly different luminosities depending on their size. The C-type stars, with their sharp spectral lines, were in fact giant stars, much larger and more luminous than ordinary dwarf stars of the same spectral type, and the sharpness of their lines reflected the lower density and pressure in their extended atmospheres. Maury's careful observation of line quality had thus contributed to one of the fundamental insights of 20th century stellar astronomy, the recognition that stars could be divided into giants and dwarfs with very different physical properties. For the study of variable stars, this distinction was crucial, since many types of variables, including the Cepheids and the long-period Mira-type variables, were found to be giant or supergiant stars, and their variability was intimately connected with the physical conditions in their extended atmospheres. The spectroscopic observation of novae continued to yield important insights into the nature of these dramatic events, and one particularly informative case occurred in 1892 when a nova appeared in the constellation Auriga. Nova Aurigii, as it was called, was discovered in late January and was observed spectroscopically by astronomers at many observatories as it brightened and then slowly faded over the following months. The spectrum proved to be complex and evolving, changing its character as the nova developed, and careful study revealed features that could only be explained by the ejection of material at high velocities. Some spectral lines appeared doubled, with one component shifted to the blue and another shifted to the red, indicating that gas was expanding outward from the nova in all directions, with some of it approaching us and some receding. By 1893, as astronomers continued to monitor the slowly fading nova, it became clear that the star was surrounded by an expanding shell of gas, a bubble of material that had been blown off during the outburst and was now dissipating into space. The velocities implied by the spectral line shifts were enormous by terrestrial standards, hundreds of kilometers per second, and this demonstrated that novae involved not merely brightening but also violent mass ejection, a physical process of considerable power. The accumulated spectroscopic observations of variable stars by the end of the 19th century had thus transformed the field from one concerned merely with the measurement of brightness variations to one that could address fundamental physical questions about stellar atmospheres and their changes. When a long-period variable like Mira pulsated through its cycle of brightening and fading, spectroscopy revealed that its surface temperature was changing, with different molecular species becoming visible in the spectrum at different phases as the outer layers of the star expanded and cooled or contracted and heated. The strong bands of titanium oxide that characterized these cool red giant stars waxed and waned in intensity as the star pulsed, and careful measurement of spectral line positions showed that the stellar atmosphere was actually moving, rising and falling as the star breathed in and out over its period of nearly a year. For the Cepheid variables, spectroscopy confirmed that these stars too were pulsating, with their spectral lines shifting in a characteristic pattern that correlated with their brightness changes, the lines shifting to the blue as the star approached maximum brightness and its surface rushed outward, then shifting to the red as the star faded and its atmosphere fell back inward. The ability to determine chemical abundances from stellar spectra also proved valuable for understanding variable stars, though this application developed more fully in the 20th century as the underlying atomic physics became better understood. Even in the earlier period, however, observers noted that some variable stars showed unusual spectral features suggesting peculiar chemical compositions, and this raised questions about whether the variability and the unusual chemistry might be related. The Novae, with their emission line spectra indicating hot gas, showed evidence of material that had been processed in nuclear reactions and expelled into space, providing clues about the internal structure of these systems. The Archeroni borealis stars, those strange variables that faded unpredictably when clouds of carbon dust formed in their atmospheres, showed spectra dominated by carbon compounds rather than the oxygen-rich molecules seen in most cool giant stars, and this carbon-rich composition was clearly connected to their peculiar fading episodes. Spectroscopy had thus provided astronomers with a window into the physical conditions within variable stars, allowing them to measure temperatures, detect motions, identify chemical species, and witness mass ejection events. Where the photometer revealed only that a star had changed its brightness, the spectroscope could reveal why, or at least provide important clues toward understanding the underlying physical processes. The combination of photometric and spectroscopic observation became the standard approach to variable star research, with each technique complementing the other and together providing a far more complete picture than either could alone. This union of brightness measurement and spectral analysis would continue to characterize variable star astronomy throughout the 20th century and into our own time, a quiet partnership between two ways of interrogating starlight that has proved remarkably fruitful over the generations. The observers who developed these techniques, working patiently at their telescopes night after night, measuring and classifying and recording, perhaps did not fully appreciate how their work would accumulate into a comprehensive understanding of stellar physics, but each careful observation contributed something to the whole, building up the picture piece by piece like a mosaic assembled from countless small tiles, each tile placed with care and attention, the final image emerging only gradually as more and more pieces found their proper places. And so we come now to a most gradual and gentle transformation in the way that observers came to study the changing stars. A transformation that did not arrive suddenly but rather accumulated over many decades, as so many things do in science, through patient experiments and small improvements and the quiet dedication of individuals who perhaps did not fully realize how profoundly their work would reshape the field. This transformation came through the capture of light itself upon treated surfaces, through the development of what we now call photography, and it would, in time, allow astronomers to study variable stars with a precision and a consistency that the human eye alone could never quite achieve, no matter how skilled or devoted the observer might be. The story begins, as such stories often do, somewhat before our main subject, with experiments that were not themselves concerned with stars at all, but rather with the fundamental question of whether light could be made to leave a permanent trace of itself upon physical materials. In the years leading up to 1840, various investigators in France and England had been working with silver compounds and other substances that darkened when exposed to light, and these early pioneers were gradually learning to fix their images so that they would not simply fade away when brought out into daylight again. The process that came to be called the daguerreotype, named after one of its principal developers, Louis Daguerre of France, was announced to the world in 1839, and it caused considerable excitement among those who understood its implications. For here was a method by which nature could, in a sense, draw its own portrait without the intervention of an artist's hand or eye. Among those who immediately grasped the potential of this new technique was John William Draper, an English-born scientist who had emigrated to America and established himself as a professor of chemistry at New York University. Draper was a methodical and patient experimenter, precisely the sort of person who would take up a new technique and explore its possibilities with systematic care, and in the early months of 1840, he turned his attention to the question of whether the daguerreotype process might be used to capture an image of the moon. This was not, one should understand, a simple matter, for the moon, bright as it appears to our eyes, provides far less light than a sunlit landscape, and the early daguerreotype process required considerable exposure times even under the best of conditions. Nevertheless, Draper persisted, and in March of 1840 he succeeded in producing a small but recognizable image of the lunar surface, showing the familiar pattern of Mira and highlands that observers had been sketching by hand for more than 2 centuries. This modest image, perhaps an inch or so across, marked the beginning of astronomical photography, though Draper himself could not have known quite where this beginning would lead. The progression from lunar photography to stellar photography was neither swift nor straightforward, for stars presented challenges that the moon did not. A star, even a bright one, delivers far less light to the camera than does the broad face of the moon, and early photographic emulsions were not especially sensitive. Furthermore, stars move across the sky as the Earth rotates, which means that any exposure lasting more than a few seconds would result in the star trailing across the plate rather than registering as a point of light, unless some mechanism were employed to track the sky's apparent motion. These difficulties meant that early attempts at stellar photography were often frustrating, yielding plates that were blank or showed only streaks and smudges rather than the crisp star images that observers hoped to capture. Progress came slowly through the 1840s and 50s, as photographers and astronomers experimented with longer exposures, better tracking mechanisms, and improved chemical processes. The wet collodion process, introduced in the early 1850s, proved more sensitive than the daguerreotype and allowed somewhat shorter exposures, which helped matters, though it brought its own complications, as the photographic plates had to be prepared, exposed, and developed while still damp, which was not always convenient at the telescope. By the 1860s, a number of observers had succeeded in photographing bright stars and even in capturing rudimentary stellar spectra, but photography remained more of a curiosity than a practical tool for serious astronomical research. The eye and the telescope were still the primary instruments, and most professional astronomers, if they thought about photography at all, regarded it as an interesting novelty rather than a technique that might transform their work. The person who did more than perhaps anyone else to demonstrate the true potential of astronomical photography was Henry Draper, the son of John William Draper, who had taken that first lunar photograph 30 years earlier. Henry Draper had grown up surrounded by science, had trained as a physician, and had inherited from his father both a love of astronomy and a conviction that photography was destined to become an essential tool for studying the heavens. In the 1870s, working at his private observatory in Hastings-on-Hudson, New York, Henry Draper set about demonstrating what could be accomplished when photographic techniques were applied with care and patience to astronomical problems. He built his own telescopes and mirrors, ground and polished with his own hands, and he worked steadily to improve every aspect of the photographic process as applied to celestial objects. In 1872, Henry Draper succeeded in photographing the spectrum of a star, Vega, capturing on a photographic plate the pattern of light and dark lines that revealed the chemical composition of that distant sun. This was a remarkable achievement, for it showed that photography could reveal details about stars that the eye alone could not easily discern, and it suggested that systematic photographic surveys might eventually catalogue the spectra of thousands or even millions of stars. Draper continued his work through the 1870s, photographing more stellar spectra, capturing images of nebulae, and demonstrating again and again that the photographic plate could serve as a reliable and objective recorder of celestial phenomena. His premature death in 1882, at the age of just 45, cut short what would surely have been many more years of productive research, but the work that he had begun would not be lost. Henry Draper's widow, Anna Palmer Draper, determined that her husband's scientific legacy should continue and indeed expand, made a most generous decision that would shape the course of variable star research for generations to come. She approached Edward Charles Pickering, who was then the director of the Harvard College Observatory, and offered to provide funding for a systematic survey of stellar spectra, to be carried out in her husband's memory. This survey, which came to be known as the Henry Draper Catalogue, would eventually classify the spectra of hundreds of thousands of stars, but it would also, as we shall see, produce an abundance of photographic plates that proved invaluable for studying variable stars of many kinds. Anna Palmer Draper's generosity, sustained over many years, transformed Harvard into the leading center for photographic astronomy and created an archive of celestial images that researchers continue to consult even now. Edward Charles Pickering, who received this funding, was precisely the right person to make use of it, for he combined administrative ability with scientific vision and understood better than most the advantages that photography could bring to astronomy. Pickering had become director of the Harvard Observatory in 1877, when he was just 30 years old, and he immediately began to reorganize the institution along more systematic lines. He recognized that astronomy was entering an era in which the accumulation and analysis of large amounts of data would become central to progress, and he saw photography as the key to gathering such data efficiently and objectively. Beginning in 1885, Pickering initiated a program of systematic photographic surveys of the sky, using relatively modest telescopes equipped with cameras designed to photograph wide fields of view rather than magnified images of individual objects. These patrol cameras, as they came to be called, could capture thousands of stars on a single photographic plate, and by taking repeated photographs of the same regions over weeks and months and years, Pickering's team could build up a record of stellar brightnesses that would reveal variations too subtle or too slow to be noticed by visual observers. The advantages of this photographic approach for studying variable stars were numerous and significant, and it is worth considering them in some detail, for they explain why photography so thoroughly transformed the field during this period. First and most fundamentally, a photographic plate provided an objective and permanent record of the sky at a particular moment in time, unlike a visual observation, which existed only in the memory and notebook of the observer. A photograph could be examined and re-examined, measured and re-measured, by different people at different times, and it would always show the same thing. This permanence meant that if a star were later discovered to be variable, one could go back to old plates and determine what its brightness had been years or even decades earlier, reconstructing a light curve that extended far back before anyone had suspected the star of varying. Second, a photograph captured the images of many stars simultaneously, which meant that comparison stars were automatically recorded on the same plate as the variable being studied, under exactly the same atmospheric and instrumental conditions. This greatly simplified the problem of determining accurate magnitudes and reduced many sources of systematic error that had plagued visual observers. Third, the photographs could be compared with one another using devices called blink comparators, which rapidly alternated the view between two plates taken at different times, causing any star that had changed in brightness to appear to pulse or blink. This technique made it possible to discover new variable stars with remarkable efficiency, simply by examining pairs of plates and watching for blinking images. The blink comparator was a marvelously simple but effective instrument, consisting essentially of an optical arrangement that allowed the observer to view first one plate and then another in rapid succession, perhaps several times per second. When two plates of the same star field were placed in the comparator and properly aligned, most stars would appear steady, their images blending smoothly together as the view alternated, but any star that had changed position or brightness would seem to flicker or jump, drawing the eye immediately. Variables that might have escaped notice entirely when plates were examined side by side became obvious when blinked in this fashion, and the technique allowed a single patient observer to survey thousands of stars in a reasonable time, identifying candidates for further study. Max Wolf, working at the Heidelberg Observatory in Germany from the 1890s onward, became particularly skilled at using photographic methods to discover both asteroids and variable stars. Wolf had established a program of systematic sky photography similar to Pickering's, and by carefully blinking his plates, he identified hundreds of minor planets and numerous variable stars that had previously escaped detection. His work demonstrated that photography was not merely a tool for studying known objects but also a powerful means of discovery, revealing the presence of celestial phenomena that no one had suspected. Pickering understood that for photographic surveys to reach their full potential, they would need to cover not only the northern sky visible from Massachusetts but also the southern sky, where many of the most interesting star fields lay hidden from northern observers. The dense star clouds of the Milky Way, passing through Scorpius and Sagittarius and the Southern Cross, contained millions of stars that could not be photographed from Harvard, and Pickering was determined to include them in his surveys. To this end, he established a southern observing station, and the person he chose to lead this venture was Solan Irving Bailey, a dedicated astronomer who would spend much of his career far from home in service of this photographic program. In 1889, Bailey traveled to Peru and established an observing station near the city of Arequipa, at an altitude of over 2,400 meters, where the thin dry air and dark skies provided excellent conditions for photography. There, using patrol cameras similar to those employed at Harvard, Bailey and his assistants began accumulating plates of the southern sky, building an archive that would eventually contain hundreds of thousands of stellar images. Bailey's work in Peru proved especially important for the study of variable stars in globular clusters, those ancient spherical collections of stars that orbit the outskirts of our galaxy. The globular clusters visible from the southern hemisphere included some of the richest and most spectacular examples, and Bailey, patiently photographing them night after night, identified hundreds of variable stars within these systems. Many of these variables proved to be of the type we have already encountered in our discussion of Goodricke's work, the short-period pulsating stars that would later be called Lyrae variables, and Bailey's observations provided crucial data about their periods and amplitudes. The plates that he and his colleagues exposed under the clear Peruvian skies became part of the great Harvard archive, available for study by anyone who wished to examine them, and they continue to be consulted by researchers interested in how particular stars behaved more than a century ago. As photographic methods became more widespread, astronomers found it necessary to develop reliable ways of measuring stellar brightnesses from photographs, which was not quite as straightforward as one might suppose. The human eye, observing stars visually, responds to light in a particular way, being most sensitive to the yellow-green portion of the spectrum, while photographic emulsions respond differently, often being more sensitive to blue light than to red. This meant that a star's photographic magnitude, as measured from a plate, might differ from its visual magnitude as estimated by an observer at the telescope, and the difference could be substantial for stars of different colors. A very red star might appear considerably brighter to the eye than to the photographic plate, while a very blue star might appear relatively brighter in photographs. Developing consistent photographic magnitude scales required careful calibration, using sequences of standard stars whose brightnesses had been determined by other methods, and this calibration was a painstaking process that occupied many astronomers for many years. Pickering and his colleagues at Harvard devoted considerable effort to establishing standard photographic magnitude sequences in selected regions of the sky, sequences that other observers could use to calibrate their own plates. These standard sequences, known as the Harvard Photometry, provided a common reference against which measurements from different observatories could be compared, though achieving real consistency remained difficult, as different telescopes, different cameras, different emulsions, and different development procedures all introduced their own systematic variations. The problem of photographic calibration was one that would occupy astronomers well into the 20th century, and it required not only careful technique but also a certain philosophical acceptance that perfect accuracy might remain forever just out of reach. Nevertheless, the precision achievable with photographic methods far exceeded what had been possible with visual estimates alone, and this increased precision opened new avenues of investigation into the nature and behavior of variable stars. And so, by the turn of the 20th century, the study of variable stars had been transformed from an endeavor dependent upon the trained eye and careful notebook of individual observers into a systematic photographic enterprise, one that generated permanent records, enabled blink comparison discovery of new variables, and allowed brightnesses to be measured with unprecedented consistency. The great plate archives accumulating at Harvard and Heidelberg and other observatories around the world represented a new kind of astronomical resource, a collection of frozen moments of starlight that could be consulted again and again as new questions arose and new techniques of analysis became available. Photography had not replaced the visual observer entirely, for there remained certain tasks for which the eye was still preferred, but it had established itself as an indispensable tool, one that would continue to evolve and improve throughout the coming decades. The stars went on with their ancient variations, pulsing and eclipsing and erupting as they had always done. But now, for the first time, those variations were being captured and preserved in silver and gelatin, held fast in archives where future generations might study them at leisure. And this permanence, this ability to look back and see what the sky had shown on some particular night long ago, was perhaps the most precious gift that photography brought to the quiet science of variable star observation. In the year 1881, a young Scottish woman named Williamina Fleming was working as a maid in the household of Edward Charles Pickering, who served as the director of the Harvard College Observatory in Cambridge, Massachusetts. Fleming had emigrated from Dundee just 2 years earlier, and circumstances had left her in need of employment, so she had taken up domestic work to support herself and her young son. Pickering, who was growing increasingly frustrated with the pace of work at the observatory, where male assistants were struggling to process the growing backlog of photographic plates that recorded the light of countless stars, made a decision that would quietly reshape the course of astronomical science. He offered Fleming a position at the observatory itself, initially to perform clerical duties, but soon to examine and catalogue the very same photographic plates that had been accumulating on the shelves. This decision, which arose partly from practical necessity and partly from Pickering's genuine belief that women could perform detailed analytical work with great precision, marked the beginning of what would become one of the most productive periods in the history of stellar observation. Over the following decades, Pickering would hire dozens of women to work as human computers at Harvard, and these women, working for wages that ranged from 25 cents to 50 cents per hour, would systematically examine hundreds of thousands of photographic plates and discover patterns in starlight that had eluded observers for centuries. The work was painstaking and repetitive, requiring long hours of sitting at desks with magnifying glasses, peering at tiny specks of light recorded on glass plates, and noting down measurements and classifications in ledgers that would eventually fill entire rooms. Williamina Fleming proved herself to be extraordinarily capable at this work, possessing both the visual acuity to distinguish subtle differences in stellar spectra and the intellectual curiosity to recognize when something unusual appeared on a plate. Within a few years of joining the observatory, she had begun developing a system for classifying stars according to the patterns of light and dark lines that appeared in their spectra when starlight was spread out into its component wavelengths. These spectral lines, which arise from the absorption of specific wavelengths of light by elements in the outer layers of stars, had been observed since the early 19th century, but no comprehensive system existed for organizing the thousands of stars whose spectra were being recorded by the Harvard telescopes. Fleming's classification scheme, which she developed and refined throughout the 1880s, assigned letters of the alphabet to different types of stellar spectra based on the strength of certain hydrogen lines that appeared as dark bands crossing the rainbow of colors. She labeled the spectra with letters from A through to Q, grouping stars that showed similar patterns of absorption lines into the same categories. This system, though it would later be modified and reordered by her colleagues, established the fundamental principle that stars could be organized into distinct spectral classes, and that these classes revealed something meaningful about the physical nature of the stars themselves. The work was not glamorous, and it proceeded one plate at a time, with Fleming examining each tiny stellar image through her magnifying glass and recording her classifications in careful handwriting. As the years passed and the photographic plate collection at Harvard continued to grow, Fleming's responsibilities expanded to include the identification of unusual or variable objects. She became particularly skilled at recognizing stars whose brightness changed from one plate to another, comparing images taken on different nights and noting which stars appeared brighter or fainter than they had before. By the time of her death in 1911, Fleming had personally discovered more than 200 variable stars, along with numerous novae and other peculiar objects. She also discovered the Horsehead Nebula in 1888, noticing an unusual dark shape silhouetted against the glowing hydrogen gas of the Orion region, though she recorded it simply as a curious feature worthy of further attention rather than recognizing it as the iconic object it would later become. The observatory's program of hiring women computers continued to expand throughout the 1890s, and in 1893, a young woman named Henrietta Swan Leavitt arrived at Harvard to begin work as a volunteer assistant. Leavitt had graduated from what was then called the Society for the Collegiate Instruction of Women, which later became Radcliffe College, and she had developed an interest in astronomy during her studies. Like Fleming, she possessed exceptional patience and attention to detail, qualities that would prove essential for the work that lay ahead. After a period of volunteer work, she was hired as a permanent staff member at a salary of 30 cents per hour, which was typical for the women computers at that time, and she was assigned to study the photographic plates that recorded the Magellanic Clouds, two small companion galaxies that are visible from the southern hemisphere and which had been photographed extensively by Harvard's observing station in Peru. The Magellanic Clouds, which appear to the naked eye as two hazy patches of light near the south celestial pole, contain millions of stars that lie at roughly the same distance from Earth, a fact that would prove crucial to Leavitt's later discoveries. She began the painstaking work of identifying variable stars within these cloudy patches, comparing plates taken on different nights and marking any stars that showed changes in brightness. The work required her to examine each plate under magnification, noting the positions and apparent brightnesses of thousands of individual stars, and then comparing these measurements to plates taken days, weeks, or months earlier. Year after year, she accumulated observations, building up records of how each variable star brightened and faded over time. By 1908, Leavitt had identified more than 1,700 variable stars in the Magellanic Clouds, and she had begun to notice something remarkable about a particular class of these variables known as Cepheids. These stars, which pulsate in a regular rhythm, growing brighter and then dimmer over periods ranging from a few days to several weeks, seemed to follow a pattern that connected their period of variation to their intrinsic luminosity. The Cepheids that took longer to complete their cycles of brightening and fading were also intrinsically more luminous than those with shorter periods. This relationship, which Leavitt published in 1912 after years of careful measurement, would eventually become one of the most important tools in all of astronomy, allowing later researchers to determine the distances to faraway galaxies by observing Cepheid variables within them and comparing their apparent brightness to their intrinsic luminosity as predicted by their period. Leavitt's discovery emerged not from a sudden flash of insight but from the slow accumulation of measurements taken over many years, each observation adding another point to the graph that would eventually reveal the period-luminosity relation. She worked quietly and methodically, rarely receiving public recognition for her contributions during her lifetime, and she continued her work at Harvard until her death from cancer in 1921 at the age of 53. The significance of her discovery would only become fully apparent in the years that followed, When Edwin Hubble and others used Cepheid variables to measure the distances to other galaxies and to demonstrate that the universe was far larger than anyone had previously imagined. Another of Pickering's computers, Annie Jump Cannon, arrived at Harvard in 1896 and would go on to become one of the most prolific classifiers of stellar spectra in history. Cannon, who had studied physics and astronomy at Wellesley College, brought both scientific training and remarkable visual acuity to her work, and she was able to classify stellar spectra with extraordinary speed and accuracy. She could examine a photographic plate and assign spectral classifications to hundreds of stars in a single working day, identifying the subtle differences in absorption line patterns that distinguished one spectral type from another. Over the course of her career, which spanned more than 4 decades, Cannon personally classified the spectra of more than 350,000 stars, a feat of sustained concentration and careful observation that has perhaps never been equaled. Cannon also refined and simplified the spectral classification system that Fleming had developed, rearranging the letter categories into the sequence O, B, A, F, G, K, which organized stars according to their surface temperature rather than simply the strength of their hydrogen lines. This sequence, which runs from the hottest blue-white O-type stars down to the coolest red M-type stars, remains the foundation of stellar classification to this day, and generations of astronomy students have memorized it using various mnemonic phrases. Cannon's classifications were published in the Henry Draper Catalogue, a massive reference work that appeared in volumes between 1918 and 1924 and which provided spectral types for stars across the entire sky, creating a resource that astronomers would consult for decades to come. Working alongside Fleming, Leavitt, and Cannon was Antonia Maury, a niece of the astronomer Henry Draper, whose memorial fund had helped finance the Harvard Spectral Survey. Maury brought a somewhat different perspective to the classification work, paying attention not only to which absorption lines appeared in a stellar spectrum but also to how sharp or fuzzy those lines appeared. She noticed that some stars with otherwise similar spectra showed absorption lines that were narrow and well-defined, while other stars of the same spectral type showed lines that were broader and more diffuse. Maury developed a system of secondary classifications to capture these differences, adding suffixes to the standard letter types to indicate the appearance of the spectral lines. This refinement was not immediately appreciated by Pickering, who preferred a simpler classification scheme that could be applied quickly and consistently across large numbers of stars. But Maury's observation would later prove to have profound physical significance. The sharpness of spectral lines is related to the density of the stellar atmosphere, which in turn depends on the size of the star, and Maury's careful attention to line width had inadvertently provided a way to distinguish giant stars from dwarf stars even when they had similar surface temperatures. This insight would be developed further by the Danish astronomer Ejnar Hertzsprung and others in the early 20th century, leading to the recognition that stars of the same spectral type could differ enormously in their intrinsic luminosity depending on whether they were compact main sequence dwarfs or bloated giants. The working conditions at Harvard Observatory were modest by any standard, with the women computers receiving wages that reflected the limited opportunities available to educated women in that era. At 25 to 50 cents per hour, their pay was substantially lower than that of male astronomers with comparable responsibilities, and they were generally excluded from using the telescopes themselves or from receiving formal academic appointments. They worked at desks in a building that came to be known informally as the Brick Building, examining plate after plate under the glow of electric lights, recording their observations in ledgers, and discussing their findings with one another in quiet conversations that rarely made it into the official historical record. Yet despite these limitations, the women computers produced scientific results of lasting importance, and their meticulous attention to the photographic plate collection enabled discoveries that would have been impossible for any individual observer working alone at a telescope. One such discovery came in 1907, when Louisa Wells, examining archival plates of the star SS Cygni, recognized that this object was undergoing repeated outbursts in which its brightness increased dramatically before fading back to its normal level. Wells identified SS Cygni as what we would now call a dwarf nova, a close binary system in which material from one star falls onto a white dwarf companion, occasionally triggering sudden releases of energy that cause the system to brighten by several magnitudes. Her discovery added to the growing catalogue of variable star types and demonstrated that the Harvard plate collection contained information that could reveal new classes of astronomical phenomena. The tradition of women's contributions to stellar astrophysics at Harvard continued into the 1920s and beyond, when a young British woman named Cecilia Payne arrived to pursue graduate studies under the supervision of Harlow Shapley, who had succeeded Pickering as observatory director. Payne, who would later marry the astronomer Sergei Gaposchkin and become known as Cecilia Payne-Gaposchkin, brought a strong background in theoretical physics to her study of stellar spectra, and her doctoral thesis of 1925 demonstrated that hydrogen was by far the most abundant element in the Sun and other stars. This conclusion, which contradicted the prevailing assumption that stars had roughly the same chemical composition as the Earth, was initially met with skepticism but was eventually accepted as one of the fundamental insights of 20th century astrophysics. Payne-Gaposchkin went on to make important contributions to the study of variable stars, particularly the analysis of their light curves and the physical mechanisms responsible for their brightness changes. She spent decades studying the photographic plate collection that had been built up by Fleming, Leavitt, Cannon, and their colleagues, extracting new information from this remarkable archive and training subsequent generations of astronomers in the techniques of stellar observation. In 1956, she became the first woman to be promoted to full professor at Harvard, a belated recognition of contributions that had been evident for decades. The work of the Harvard computers, proceeding quietly through the decades from the 1880s to the mid-20th century, created the observational foundation upon which modern stellar astrophysics was built. Their classifications organized the bewildering variety of stellar spectra into a coherent system that revealed the physical properties of stars. Their discovery of variable stars provided the raw material for understanding stellar evolution and pulsation. Their measurements of Cepheid periods and luminosities gave astronomers a tool for measuring distances across the universe. And their careful examination of hundreds of thousands of photographic plates demonstrated that systematic, patient observation could reveal patterns and relationships that no amount of theoretical speculation could have predicted. The glass plates themselves, each one recording a moment in time when starlight fell upon a sensitized emulsion, accumulated in the Harvard archives until they numbered in the hundreds of thousands, representing a century of observations that continue to be valuable for research into stellar variability and long-term changes in stellar brightness. The women who examined these plates, hour after hour and year after year, transformed raw data into scientific knowledge through the simple but demanding process of careful looking and precise recording. They worked in obscurity for modest wages, rarely receiving the recognition that was given to male astronomers who interpreted their observations and built theoretical frameworks around their discoveries. And yet the stars themselves, indifferent to human distinctions of gender or status, yielded their secrets to anyone with the patience and skill to examine them closely. The variable stars that brighten and fade in their endless cycles, the Cepheids pulsing with clockwork regularity, the dwarf novae flaring unpredictably in the night. All of these were waiting to be noticed by observers who took the time to look carefully at what the universe was showing them. The Harvard computers looked, and they saw, and they wrote down what they observed. And in doing so they mapped a variable sky that had been changing overhead since long before humans existed to wonder at it. The quiet dedication of this work, the accumulation of small observations into large patterns, the transformation of photographic dots into knowledge about the physical nature of stars, all of this proceeded without fanfare through the decades, one plate at a time, one classification at a time, one variable star at a time. The women who did this work have largely faded from public memory, their names known mainly to historians of astronomy and to those who take the time to look back at the origins of our modern understanding of the stars. But the universe they helped reveal remains overhead. The same stars varying in brightness tonight as they did when Williamina Fleming first sat down at her desk in Cambridge to examine a glass plate under a magnifying lens. In the quiet archive rooms of the Harvard College Observatory, where the winter light filtered softly through tall windows and the Massachusetts cold pressed gently against the glass, there worked a woman whose careful measurements would ultimately reshape humanity's understanding of the cosmos itself. Henrietta Swan Leavitt had come to the observatory in 1893, initially as a volunteer, and she possessed what her colleagues would later describe as an extraordinary patience for the painstaking work of examining photographic plates, those glass negatives that captured the light of thousands upon thousands of stars in a single exposure. She had studied at what was then called the Society for the Collegiate Instruction of Women, which would eventually become Radcliffe College, and her interest in astronomy had drawn her to the observatory where Edward Charles Pickering was assembling a remarkable team of women computers, as they were called in that era, to catalogue and analyze the overwhelming flood of stellar data that new photographic techniques were producing. The work was meticulous in a way that modern observers might find difficult to imagine, requiring hours upon hours of peering through magnifying lenses at tiny points of light on glass plates, comparing one plate against another, measuring the precise positions and brightnesses of individual stars among fields containing tens of thousands of them. Leavitt was assigned to study variable stars, those celestial objects whose brightness changes over time, and she brought to this task a methodical precision that would prove essential to one of the most important discoveries in the history of astronomy. Her particular focus became the Magellanic Clouds, those two hazy patches of light visible in the southern hemisphere sky that we now know to be satellite galaxies of our own Milky Way, and it was in the smaller of these two clouds that she would find the key to measuring the universe. The small Magellanic Cloud presented a unique opportunity for astronomical investigation, though it required Leavitt to work with photographic plates taken at Harvard's Southern Station in Arequipa, Peru, where the skies were clear and the Magellanic Clouds rose high above the horizon. She began systematically identifying variable stars within the cloud, a process that involved comparing multiple photographs of the same region taken on different nights and noting which stars had changed in brightness between exposures. This was not glamorous work, and it offered none of the excitement that popular imagination associates with astronomical discovery, but it was precisely the sort of careful, accumulating labor upon which great insights are sometimes built, like sediment gathering grain by grain until a new landscape emerges. In 1908, Leavitt published a preliminary report in the Annals of the Harvard College Observatory, a publication that served as a repository for the ongoing work of the observatory staff and which circulated among the small community of professional astronomers who concerned themselves with such technical matters. In this report, She presented her findings regarding 1,777 variable stars she had identified in the Magellanic Clouds, and near the end of this catalogue, almost as an aside, she noted something curious about a particular class of these variables. Among the 16 stars in the small Magellanic Cloud that she had been able to classify as Cepheid variables, based on the characteristic shape of their light curves, she observed that the brighter ones appeared to have longer periods of variation. It was a simple observation, stated without fanfare, and yet it contained within it the seed of a revolution in our understanding of cosmic distances. The significance of this observation lay in a circumstance that Leavitt clearly understood, even if she did not elaborate upon it extensively in that initial report. The small Magellanic Cloud, whatever it might prove to be, was clearly very far away from Earth, so far that all of the stars within it could be considered to lie at essentially the same distance from us. This was rather like observing a city's lights from a distant hilltop, where the differences in brightness that you perceive must reflect genuine differences in the luminosity of the lights themselves, rather than differences in how far away each light happens to be. If one street lamp appears brighter than another when both are 30 miles away, then the brighter one truly is more luminous, and this simple principle, applied to the stars of the small Magellanic Cloud, meant that Leavitt could compare their true brightnesses directly, something that was ordinarily impossible when studying stars scattered at vastly different distances throughout our own galaxy. 4 years passed, during which Leavitt continued her patient work, adding more Cepheid variables to her sample and refining her measurements of their periods and apparent brightnesses. Her health was never robust, and she had struggled with illness that had left her progressively deaf, yet she persisted in her examinations of the photographic plates, building her catalogue of variable stars one careful measurement at a time. In 1912, she published a more complete analysis in the Harvard College Observatory Circular, a brief communication of just 3 pages that would prove to be one of the most consequential documents in the history of astronomy. In this paper, she presented data on 25 Cepheid variables in the small Magellanic Cloud, plotting their periods against their apparent magnitudes and demonstrating unmistakably that there existed a clear relationship between the two quantities. The relationship that Leavitt had discovered was remarkably simple in its form, though profound in its implications. When she arranged her 25 Cepheids according to their periods of variation, which ranged from about 1.25 days to 127 days, their apparent brightnesses fell along a smooth curve, with the longer period stars being systematically brighter than the shorter period ones. She presented this finding both in tabular form and as a graph, showing the maximum and minimum brightness of each star plotted against the logarithm of its period, and the points clustered with satisfying tightness around 2 parallel lines, one for the maximum brightness and one for the minimum. A straight line could be drawn through each set of points, indicating that the relationship between period and luminosity was logarithmic in nature, which is to say that a star with a period 10 times longer than another would be a fixed amount brighter, not 10 times brighter but rather brighter by a specific number of magnitudes. Leavitt was characteristically modest in presenting her discovery, noting simply that since the variables are probably at nearly the same distance from the Earth, their periods are apparently associated with their actual emission of light, as determined by their mass, density, and surface brightness. She did not speculate extensively on the physical causes of this relationship, nor did she calculate what distances might be determined if the relationship could be calibrated in absolute terms. That work would fall to others, For the division of labor at Harvard Observatory meant that Leavitt's role was primarily to gather and analyze data rather than to develop theoretical interpretations, and her employer Pickering was careful to maintain this distinction even when, as in this case, the data gatherer had made a discovery of the first importance. What Leavitt had provided to astronomy was nothing less than a new kind of cosmic measuring rod, though it was a measuring rod whose absolute scale remained unknown. If one could determine the true luminosity of even a single Cepheid variable at a known distance, then the period-luminosity relation would allow astronomers to calculate the distance to any Cepheid anywhere in the sky, simply by measuring its period and apparent brightness. The period told you the star's true luminosity. The apparent brightness told you how much that luminosity had been dimmed by distance, and from these two quantities the distance followed by straightforward calculation. It was, in principle, elegantly simple, though in practice the calibration of the relationship would prove to be a persistent challenge that would occupy astronomers for decades to come. The first serious attempt to calibrate Leavitt's relationship came just a year after her 1912 paper, when the Danish astronomer Ejnar Hertzsprung took up the problem at the Potsdam Observatory in Germany. Hertzsprung was already well known for his work on stellar classification and for his independent discovery of what would become known as the Hertzsprung-Russell diagram, and he recognized immediately the importance of what Leavitt had found. The difficulty he faced was that no Cepheid variable was close enough to Earth to have a measurable parallax using the techniques available at that time, which meant that no Cepheid's distance was directly known. He therefore turned to a statistical method, using the proper motions of 13 Cepheids, their apparent movement across the sky due to the Sun's motion through space, to estimate their average distance through what is called statistical parallax. The method was ingenious though necessarily imprecise, relying on the assumption that the Cepheids he studied were moving randomly through space, so that their apparent motions reflected both their true velocities and their distances from us. By analyzing these motions statistically, Hertzsprung derived an estimate for the average distance to his sample of Cepheids, and from this he could calculate their average luminosity, which in turn allowed him to calibrate Leavitt's period-luminosity relation. Applying this calibration to the small Magellanic Cloud, he obtained a distance of approximately 30,000 light-years, a figure that was later revised significantly upward as astronomers came to recognize various sources of error in his analysis. Nevertheless, Hertzsprung's work represented the first quantitative application of Leavitt's discovery to the measurement of cosmic distances, transforming her empirical relationship from a curious observation into a practical tool for astronomical investigation. It was the American astronomer Harlow Shapley who would make the most dramatic early use of Leavitt's period-luminosity relation, applying it in a systematic campaign to measure the distances to the globular clusters that surround our galaxy like a sparse halo of ancient stellar swarms. Shapley had arrived at Mount Wilson Observatory in California in 1914, where he had access to the 60-inch reflector that was then the largest telescope in the world, and he set himself the ambitious task of determining the structure of the Milky Way system through the study of these globular clusters. He had recognized that many globular clusters contained Cepheid variables, or at least stars that he believed to be Cepheids, and that Leavitt's relationship could therefore be used to determine their distances if proper calibration could be achieved. Shapley adopted a calibration based partly on Hertzsprung's work and partly on his own analysis of Cepheids in our galaxy, and he began systematically measuring the periods and brightnesses of variables in one globular cluster after another. The results that emerged from this work were startling, for they indicated that the globular clusters lay at distances far greater than most astronomers had supposed. ranging from tens of thousands to hundreds of thousands of light-years from the Sun. Moreover, when Shapley plotted the positions of the globular clusters in three-dimensional space, he found that they were not distributed uniformly around the Sun but rather concentrated in one direction, toward the constellation Sagittarius. This asymmetry led him to a remarkable conclusion, namely that the Sun was not at the center of the Milky Way system but rather far out toward its edge, with the center lying in the direction where the globular clusters were most densely concentrated. This finding represented a fundamental shift in humanity's understanding of its place in the cosmos, a shift comparable in its philosophical implications to the earlier Copernican revolution that had removed the Earth from the center of the solar system. Shapley's estimate of the Milky Way's size, based on the distribution of the globular clusters, indicated a system roughly 300,000 light-years in diameter, far larger than previous estimates had suggested. The Sun and its planetary system occupied no privileged position in this vast stellar city, but rather circled somewhere in its outer suburbs, an ordinary star among hundreds of billions of others. All of this rested ultimately upon Leavitt's discovery of the period-luminosity relation, without which Shapley would have had no means of determining the distances to the globular clusters with any confidence. Yet even as Shapley was drawing these sweeping conclusions, there remained significant uncertainties about the period-luminosity relation itself, uncertainties that would take decades to fully resolve. One persistent question was whether the relationship that Leavitt had discovered in the Small Magellanic Cloud applied equally well to all Cepheid variables everywhere, or whether there might be different types of Cepheids with different relationships between their periods and luminosities. Shapley himself had assumed that the variables he was observing in globular clusters were the same type of Cepheid that Leavitt had studied, but this assumption would eventually prove to be only partially correct. The stars he was measuring in globular clusters were in fact a different class of variable, now called Type II Cepheids or W Virginis stars, which are older and less luminous than the classical Cepheids of Leavitt's original study. This confusion between different types of Cepheid variables would not be fully resolved until the 1950s. When Walter Bade's work revealed that there were indeed two distinct populations of stars with different period-luminosity relations, a discovery that would require a significant revision of all cosmic distance measurements. But in the decades following Leavitt's original discovery, the existence of this complication was only dimly suspected, and astronomers proceeded on the assumption that all Cepheids obeyed a single universal relationship. The errors introduced by this assumption would lead to systematic underestimates of cosmic distances, but even so, the period-luminosity relation remained far more reliable than any method that had come before it, and its application transformed astronomy from a science that knew the distances to only a handful of nearby stars into one that could measure the scale of the galaxy and beyond. Throughout all of this, Henrietta Swan Leavitt continued her work at Harvard Observatory, receiving little of the recognition that her discovery deserved. Her salary was modest. Her title remained that of a computer rather than an astronomer, and the papers she published appeared under the direction of Pickering even when the work and the insights were substantially her own. She continued to catalogue variable stars, eventually identifying more than 2,400 of them over the course of her career, and she developed a standard sequence of stellar magnitudes that was adopted by the International Committee on Photographic Magnitudes in 1913. Her contributions were known and respected within the small community of variable star astronomers, but the broader recognition that might have come with the Nobel Prize or other major honors eluded her entirely. In 1921, Henrietta Swan Leavitt died of cancer at the age of 53, her health having declined steadily over the preceding years. She had never married, having devoted herself entirely to her work at the observatory, and she left behind a legacy of careful measurements and one profound discovery that would continue to reshape astronomy for decades after her death. The full implications of the period-luminosity relation were still being worked out, with Edwin Hubble soon to use it to measure the distance to the Andromeda Nebula and demonstrate that it lay far beyond the bounds of our own galaxy. And Leavitt would not live to see this culmination of the work she had begun. There is a poignant footnote to her story that illustrates both the magnitude of her contribution and the limitations of the recognition she received. In 1924, 3 years after her death, the Swedish mathematician Gösta Mittag-Leffler wrote to Harlow Shapley inquiring about Leavitt's address, for he had been impressed by her work and wished to consider nominating her for the Nobel Prize in Physics. Shapley was obliged to inform him that Miss Leavitt's work on the Cepheid variables had been of such importance that he was indeed considering her for nomination, but that regrettably she had died of cancer 3 years earlier. The Nobel Prize is not awarded posthumously, and so the opportunity was forever lost, and Leavitt's name remains absent from the rolls of Nobel laureates despite her having made one of the most important observational discoveries in the history of astronomy. Her legacy lives on in every measurement of cosmic distance that relies upon the period-luminosity relation, which astronomers now often call Leavitt's law in her honor. The relationship she discovered in those patient hours of examining photographic plates remains one of the primary methods by which we determine the scale of the universe, refined and recalibrated over the century since her death but fundamentally unchanged in its principle. Every time an astronomer measures the period of a Cepheid variable in a distant galaxy and uses that measurement to calculate how far away that galaxy lies, they are building upon the foundation that Henrietta Swan Leavitt laid in her quiet, methodical way, one careful measurement at a time, in the archive rooms of the Harvard College Observatory where the winter light filtered softly through the windows and the stars waited patiently on their glass plates to reveal their secrets. And so we come now to a particular kind of star that would prove essential in measuring the vast distances of our galaxy. And we find ourselves journeying first to a high desert plateau in Peru, where the air is thin and the skies are remarkably clear, and where a patient American astronomer named Solan Irving Bailey spent many years photographing the southern heavens with a dedication that would reshape our understanding of stellar populations in ways he could scarcely have imagined when he first arrived. Solan Bailey was born in New Hampshire in 1854, and he came to astronomy through the path that many did in those days, beginning as an assistant at the Harvard College Observatory under the direction of Edward Pickering, who had grand ambitions to survey the entire sky and who recognized early on that the southern hemisphere contained treasures that could not be properly studied from Massachusetts. Pickering needed someone reliable, someone methodical, someone willing to endure the isolation and the altitude sickness and the considerable logistical difficulties of establishing an observing station in a remote corner of South America. And in Solan Bailey he found precisely such a person, quiet and thorough and possessed of the kind of patience that astronomical work demands. Bailey first traveled to Peru in 1889. Scouting locations for what would become the Harvard Southern Station, and after considering several sites, he eventually settled on a location near the city of Arequipa, at an elevation of approximately 8,000 feet above sea level, where the Atacama Desert creates conditions of extraordinary atmospheric stability. The seeing, as astronomers call it, was often excellent, meaning that the stars appeared as sharp points of light rather than the blurred disks that plagued observers at lower altitudes, and this clarity would prove essential for the work that Bailey was about to undertake, work that required him to distinguish between stars that differed only slightly in brightness. The observing station at Arequipa was not a grand establishment in those early years, consisting of modest buildings and equipment that had been shipped at considerable expense from the United States, and Bailey worked there with a small staff, photographing the southern sky night after night, building up an archive of glass plates that would eventually number in the tens of thousands. The plates were sent back to Harvard for measurement and analysis, where the famous women computers, including Williamina Fleming and Annie Jump Cannon and Henrietta Leavitt, would examine them with magnifying glasses and carefully record the positions and brightnesses of countless stars. It was during these years at Arequipa that Bailey turned his attention to the globular clusters, those remarkable spherical assemblages of stars that appear as fuzzy patches of light when viewed through small telescopes but resolve into countless individual points when examined with larger instruments. The globular clusters had been known since the time of William Herschel, who had catalogued many of them in the late 18th century, and astronomers had long suspected that they represented some kind of fundamental building block of our galaxy, though their true nature and their distances remained entirely mysterious. Bailey began systematically photographing globular clusters in the early 1890s, and what he found astonished him, though he was not a man given to dramatic expressions of surprise. Plate after plate revealed that these clusters contained variable stars, not just one or two, but dozens, and in some cases hundreds. The cluster known as Omega Centauri, which is visible to the naked eye from southern latitudes as a hazy star of the fourth magnitude, proved to contain more than 100 variables that Bailey could identify on his photographs, each one brightening and fading with its own characteristic period and amplitude. This was a discovery of considerable importance, for it suggested that variable stars were not rare curiosities scattered randomly across the sky, but rather common inhabitants of certain stellar environments. Bailey continued his work through the 1890s, photographing cluster after cluster, identifying variable after variable, until he had accumulated a catalogue of cluster variables that numbered in the hundreds. The work was painstaking in the extreme, requiring him to compare photographs taken on different nights, looking for stars that had changed their brightness by even small amounts, and the eye strain and the tedium must have been considerable, though Bailey never complained in his published writings. In 1902, Bailey published his comprehensive catalogue of variable stars in globular clusters, a work that represented nearly a decade of sustained effort and that established him as the leading authority on this particular corner of astronomical research. In this catalogue, Bailey did something that would prove consequential for future astronomers. He classified the cluster variables into distinct types based on the shapes of their light curves, that is, the way their brightness changed over time when plotted on a graph. Bailey designated these types with lowercase letters, calling them Type A, Type B, and Type C, and the distinctions between them were based on the amplitude of variation and the asymmetry of the light curve. Type A variables had the largest amplitudes, sometimes changing by more than a full magnitude from maximum to minimum light, and their light curves showed a rapid rise to maximum brightness followed by a slower decline. Type B variables had smaller amplitudes and more symmetrical light curves, rising and falling at approximately the same rate. Type C variables had the smallest amplitudes and the most symmetrical curves of all, barely changing their brightness enough to be detected on the photographic plates. These classifications might seem like mere bookkeeping, the sort of systematic arrangement that astronomers are fond of making, but they would later prove to have physical significance, reflecting real differences in the pulsation modes of the stars themselves. Bailey could not have known this at the time, for the theory of stellar pulsation was still decades in the future, but his careful observational work laid the groundwork for theoretical developments that would come later. While Bailey was photographing clusters from our Keeper, another observer was making a discovery that would give these cluster variables their more familiar name. Williamina Fleming, working at Harvard as one of the women computers who examined the photographic plates, identified a variable star in the constellation Lyra in 1901. This star, which received the designation RR Lyrae following the standard conventions for naming variable stars, proved to have a period of approximately half a day, brightening and fading roughly twice every 24 hours, and its light curve had the same characteristic shape that Bailey had observed in his cluster variables. It gradually became clear that the cluster variables that Bailey had been cataloguing were members of the same class as RR Lyrae, and eventually the entire group came to be known as RR Lyrae stars, named after Fleming's prototype. The periods of these stars clustered tightly around half a day, some slightly shorter and some slightly longer, but rarely exceeding a day in total length. This distinguished them clearly from the classical Cepheids, which had periods measured in days or weeks, and from the long-period variables like Mira, which took months to complete a single cycle. Bailey's work continued through the first decade of the 20th century, and by the time he compiled his final statistics, he had demonstrated that individual globular clusters might contain thousands of variable stars each. The cluster Omega Centauri alone harbored several hundred confirmed variables, and Bailey estimated that the true number, including those too faint to detect on his photographs, might be many times higher. This abundance of variables would prove crucial for later distance determinations, for it meant that astronomers did not need to rely on a single star to measure the distance to a cluster, but could instead observe dozens of variables and take an average, reducing the errors that inevitably crept into individual measurements. And now we come to Harlow Shapley, a young astronomer from Missouri who would use Bailey's cluster variables to revolutionize our understanding of the size and structure of the Milky Way galaxy. Shapley was a confident man, sometimes brash in his assertions, but he was also a capable observer and a creative thinker. And when he arrived at Mount Wilson Observatory in California in 1914, he was searching for a problem worthy of his ambitions. The problem he found was the distribution of globular clusters in space. Astronomers had long noticed that the globular clusters were not scattered uniformly across the sky but instead concentrated heavily in one direction, toward the constellation Sagittarius. This asymmetry was puzzling, for if the Sun were located at the center of the galaxy, one might expect the clusters to be distributed more or less evenly in all directions. Shapley suspected that this asymmetry held the key to understanding our place in the cosmos, but to test his suspicion, he first needed to determine the distances to the clusters, and for this he turned to Bailey's variables. The connection between RR Lyrae stars and distance measurement rested on a crucial assumption, that these stars, wherever they were found, had approximately the same intrinsic luminosity. If this assumption were correct, then the apparent brightness of an RR Lyrae star could be used to calculate its distance, for a star of known luminosity will appear fainter when it is farther away, following the well-established inverse square law of light propagation. The challenge lay in determining what that intrinsic luminosity actually was. Shapley approached this calibration problem by drawing on several lines of evidence, none of them entirely satisfactory but all of them pointing in roughly the same direction. He compared the properties of RR Lyrae stars with those of classical Cepheids, whose distances had been estimated through statistical parallax methods, and he concluded that the cluster variables were somewhat less luminous than the Cepheids, as one might expect given their shorter periods. He also examined the few Lyrae stars in the solar neighborhood whose distances could be estimated through proper motion studies, though these estimates were plagued by considerable uncertainty. The calibration was further complicated by a question that would vex astronomers for decades. Were the cluster variables truly identical to the classical Cepheids in all respects except period? Or were they a fundamentally different type of star that merely happened to pulsate in a similar manner? Shapley assumed, reasonably enough given the evidence available at the time, that both types of variables followed the same period-luminosity relation that Henrietta Leavitt had discovered for the Cepheids in the Magellanic Clouds. This assumption would later prove to be incorrect, but the errors it introduced, while significant, did not change the fundamental conclusions of Shapley's work. Between 1914 and 1918, Shapley systematically observed the globular clusters visible from Mount Wilson, photographing them night after night, identifying the Lyrae stars within them, measuring their periods and their apparent magnitudes, and calculating distances using his adopted calibration. The distances he derived were startling in their magnitude. The nearest globular clusters proved to be tens of thousands of light-years away, and the most distant ones, those concentrated toward Sagittarius, were more than 100,000 light-years from the Sun. When Shapley plotted the positions of the globular clusters in three-dimensional space, a remarkable pattern emerged. The clusters formed a roughly spherical distribution, not centered on the Sun, but centered instead on a point far away in the direction of Sagittarius. If the globular clusters outlined the true extent of the galaxy, as Shapley believed they did, then the Sun was not at the galactic center but rather in the outskirts, like a street lamp on the edge of a great city. Shapley estimated that the center of the globular cluster system, and hence the center of the galaxy, lay approximately 50,000 light-years away from the Sun. This figure was considerably larger than most astronomers had previously imagined, and it placed humanity in a humblingly peripheral position within the Milky Way. We were not, as had been commonly assumed, at or near the center of things, but rather tucked away in the galactic suburbs, viewing the concentrated glow of the Milky Way toward Sagittarius because that was the direction toward the crowded central regions of our stellar city. This conclusion, published in a series of papers between 1917 and 1919, was controversial from the outset. Some astronomers questioned Shapley's calibration of the period-luminosity relation, arguing that he had overestimated the luminosity of the cluster variables and hence overestimated the distances to the clusters. Others pointed out that interstellar absorption, the dimming of starlight by dust and gas between the stars, might have caused Shapley to overestimate distances to clusters that lay in dusty regions of space. Still others questioned whether the globular clusters truly outlined the extent of the galaxy, or whether they might be a separate system of objects that happened to surround the Milky Way without being part of it. The controversy would continue for many years, and Shapley's original estimate of 50,000 light-years to the galactic center would eventually be revised downward to approximately 26,000 light-years as better calibrations became available and as the effects of interstellar absorption were better understood. But the fundamental insight remained valid. The Sun is indeed far from the center of the Milky Way, located roughly 2/3 of the way from the center to the edge of the galactic disk. And the globular clusters do indeed form a spherical halo centered on the galactic nucleus. The Lyrae stars that made this discovery possible continue to serve as valuable distance indicators to this day, their short periods and consistent luminosities making them useful for measuring distances within the Milky Way and to nearby galaxies. They are old stars, members of what astronomers call population II, formed early in the history of the galaxy before the interstellar medium had been enriched with heavy elements from successive generations of stellar nucleosynthesis. Their presence in globular clusters reflects the ancient origins of these systems, which formed when the galaxy itself was young, more than 10 billion years ago. Bailey spent his later years at Harvard, where he served as acting director of the observatory for a time and continued to work on variable stars until his retirement. His catalogues of cluster variables, assembled with such patience and care from the high desert of Peru, remained standard references for decades, and his classification of RR Lyrae stars into types A, B, and C, though later refined and modified, established the framework within which subsequent observers worked. He died in 1931, having lived long enough to see Shapley's bold conclusions about the size of the galaxy become widely accepted, though the details would continue to be refined for many years thereafter. The period-luminosity relation for RR Lyrae stars differs from that of classical Cepheids in important ways that were not fully understood until the mid-20th century. The RR Lyrae stars have periods clustered tightly around half a day, showing relatively little spread compared to the Cepheids, and their luminosities are correspondingly uniform, making them useful as what astronomers sometimes call standard candles. A standard candle is simply a light source of known intrinsic brightness, and if you know how bright a source truly is, you can determine its distance by measuring how bright it appears to be from Earth. The challenges of calibrating these standard candles persisted for decades, as astronomers refined their estimates of the absolute magnitudes of RR Lyrae stars through various methods: statistical parallax studies, main sequence fitting in globular clusters, observations of RR Lyrae stars in the Magellanic Clouds, and eventually direct parallax measurements from space-based observatories. Each method brought its own uncertainties, and the calibration debate continued well into the latter half of the 20th century, though the fundamental utility of RR Lyrae stars as distance indicators was never seriously questioned. And so the beacons in the star clusters, as we might gently call them, served their purpose in mapping the architecture of the Milky Way, their regular pulsations providing the rhythmic signal that astronomers needed to determine distances across tens of thousands of light-years. The work of Bailey in Peru and Fleming at Harvard and Shapley at Mount Wilson built upon each other in the way that scientific progress so often does, each contribution necessary for what came after, each patient observation adding to the slow accumulation of knowledge about our place among the stars. The globular clusters themselves drift through the halo of our galaxy like ancient guardians, their orbits carrying them far above and below the galactic plane, their populations of RR Lyrae stars blinking in their steady half-day rhythms just as they have for billions of years. They are among the oldest structures in the Milky Way, relics of an early epoch of galaxy formation, and the variable stars within them carry information about conditions that prevailed when the universe itself was young. That information, encoded in the periods and amplitudes of their light curves, was first read by observers like Bailey, working in the thin air of a Peruvian mountain, photographing the southern sky with instruments that would seem primitive by modern standards, but that were sufficient to reveal truths about the cosmos that previous generations could only have guessed at. And so we come now to a rather lovely chapter in the story of variable star observation, one that concerns not the great observatories with their towering domes and expensive instruments, but rather the quiet dedication of ordinary people who simply looked upward from their gardens and rooftops, night after night, recording what they saw with patience and care. These were the citizen astronomers, the amateurs in the truest and most honorable sense of that word, people who loved the stars and gave their time freely to the work of watching them change. Their contribution to astronomy would prove immense, far greater than anyone might have predicted, and the organizations they built to coordinate their efforts still function today, still gathering observations from backyards and balconies around the world, still adding to our understanding of these restless, variable suns. The story of organized amateur variable star observation might properly begin in England, in the year 1890, when the British Astronomical Association established its variable star section. This was among the first formal attempts to coordinate the work of amateur observers specifically for the purpose of monitoring variable stars, and it grew from the recognition that professionals alone could never hope to watch all the variables that needed watching. The section's early leadership included Joseph Baxendale, a name perhaps not widely remembered today but one that deserves our quiet respect. Baxendale had been observing variable stars since the 1840s, accumulating decades of careful measurements, and he understood both the scientific value of long-term monitoring and the practical challenges of maintaining consistent observations. He knew that a single observer, no matter how dedicated, would inevitably miss nights due to weather or illness or simple exhaustion, and that the gaps in any individual record could obscure the very phenomena one hoped to study. The solution, he believed, lay in numbers, in coordinating many observers so that when one was clouded out another might enjoy clear skies. When one retired for the night another in a different time zone might just be beginning their session. The British Astronomical Association's Variable Star Section developed methods for standardizing observations and established programs that assigned specific stars to specific observers, ensuring that important variables received regular attention. Subsequent directors built upon Baxendale's foundation, refining techniques and expanding the network of contributors, creating a model that other nations would eventually follow. The work was unglamorous in the extreme, consisting largely of filling out forms and comparing one star's brightness to another's, night after night and year after year. But it was precisely this unglamorous persistence that gave the observations their scientific value. A single measurement of a variable star tells you rather little, but 10,000 measurements spanning 50 years can reveal the deep rhythms of stellar behavior, can show whether a star's period is changing, whether its brightness varies in ways that suggest complex internal processes. The British amateurs understood this, and they committed themselves to the long accumulation of data that professional astronomers increasingly needed but could not themselves provide. Across the Atlantic, a similar movement was taking shape, though it would not achieve formal organization until somewhat later. The American tradition of amateur variable star observation owes much to a partnership between two men whose contributions complemented one another beautifully. Edward Charles Pickering, whom we have encountered before in his role directing the Harvard College Observatory, recognized early that the professional astronomical establishment could not possibly monitor all the variable stars being discovered. Every year brought new variables to light, and every new variable ideally required regular observation to determine its period, its amplitude, the shape of its light curve. Pickering's observatory was making extraordinary contributions to stellar classification and photographic photometry, but even Harvard's resources had limits. The solution, Pickering believed, lay in recruiting amateur observers, ordinary people with small telescopes and an interest in contributing to science. He began corresponding with amateurs, encouraging their work and, crucially, providing them with comparison star charts that would allow their observations to be placed on a common scale. These charts were essential tools, and Pickering's willingness to prepare and distribute them represented a significant commitment of professional resources to amateur astronomy. A comparison star chart shows the variable star and surrounding stars of known brightness, allowing the observer to estimate the variable's magnitude by comparing it to these standard reference points. Without such charts, each amateur's observations would be expressed on their own personal scale, difficult or impossible to combine with observations from other sources. With standardized charts, an observer in Massachusetts and an observer in California could both report that a particular star appeared to be magnitude 7.3 on a given night, and those reports could be meaningfully averaged or compared. Pickering understood that the value of amateur observations depended entirely on this kind of standardization, and he worked tirelessly to provide the necessary tools. Among the amateur observers Pickering encouraged was William Tyler Alcott, a lawyer from Connecticut with a passionate interest in astronomy. Alcott had begun observing variable stars in the early 1900s, corresponding with Pickering and learning the techniques of visual magnitude estimation. He proved to be not only a capable observer but also an effective organizer, someone who could inspire others and coordinate their efforts. On the first day of January, 1911, in Cambridge, Massachusetts, Alcott founded the American Association of Variable Star Observers, an organization that would grow to become the world's largest network of variable star observers and that continues its work to this day, more than a century later. The date is worth pausing over for a moment, if only to appreciate the quiet ambition it represented. Alcott and his fellow founders were proposing to create a permanent institution dedicated to coordinating amateur astronomical observations, with no guarantee of funding, no professional staff, no building of their own, nothing but shared enthusiasm and a belief that organized amateurs could contribute meaningfully to science. As it came to be known, began modestly, with a handful of observers submitting reports on a few dozen variable stars. Pickering's encouragement and his provision of comparison charts gave the young organization scientific credibility, while Alcott's energy and organizational skills kept it functioning through its early years. The association established standard forms for reporting observations, specifying what information each report should contain: the date and time, the estimated magnitude, the comparison stars used, the observing conditions. These forms served multiple purposes. They ensured that observations were recorded in a consistent format that facilitated later analysis. They reminded observers what details mattered and needed to be noted, and they created a permanent record that could be archived and consulted by future researchers. The humble reporting form, easily overlooked, was in fact a crucial technology for maintaining data quality across a distributed network of observers with varying levels of experience and skill. In 1915, leadership of the AAVSO's observational program passed to Leon Campbell, a professional astronomer who would guide the organization through decades of growth and refinement. Campbell proved an extraordinarily effective coordinator, patient and encouraging with amateur observers while maintaining rigorous standards for data quality. Under his direction, the AAVSO expanded its roster of observers and the number of stars under regular surveillance, developing systems to handle the increasing flow of observations. By the early 1920s, the association was receiving thousands of observations each month, a volume of data that required systematic methods for recording, checking, and archiving. Campbell established procedures for identifying and flagging questionable observations, not to embarrass or exclude observers who made errors, but to ensure that the final published data was as reliable as possible. The challenge of maintaining data quality in a volunteer network deserves some consideration, for it was not a trivial problem. Amateur observers varied enormously in their equipment, their experience, their eyesight, and their conscientiousness. Some owned excellent telescopes and had trained themselves to estimate magnitudes with impressive precision, while others worked with inferior instruments or had not yet developed reliable observing habits. An observer with poor color vision might consistently misjudge the brightness of red stars, while an observer who rushed through their observations might fail to notice when atmospheric conditions were degrading their accuracy. The AAVSO and similar organizations developed various mechanisms to identify and address these problems, comparing each observer's reports against those of other observers on the same nights, looking for systematic differences that might indicate calibration issues, gently corresponding with observers whose reports seemed anomalous to understand what might be causing the discrepancies. The result of all this careful coordination was an observational resource of remarkable value. Professional observatories, for all their sophisticated equipment, could observe any given star only intermittently, perhaps for a few nights when it happened to be included in a research program, or when passing through the field of a photographic plate exposed for other purposes. Amateur networks, by contrast, could provide nearly continuous coverage of important variables, with multiple observers reporting on the same star night after night for years or decades on end. This continuity proved essential for studying stars with long or irregular periods, for catching nova outbursts in their earliest stages, for detecting subtle changes in stellar behavior that might otherwise go unnoticed. The professionals had the equipment to make precise measurements of individual stars at particular moments, but the amateurs had the persistence to watch those stars through all their changes over lifetimes of observation. Similar organizations emerged in other countries, each adapting to local conditions and traditions while pursuing the same fundamental goal of coordinating amateur variable star observation. The German astronomical community, centered around the Astronomische Gesellschaft, developed its own programs for variable star monitoring, drawing on a strong tradition of precise positional astronomy and meticulous record-keeping. German observers contributed systematic surveys of variable star behavior, and German publications provided outlets for sharing observations and analyses. The French eventually established the Association Française des Observateurs d'Étoiles Variables, known by its initials AFOEV, which would grow to coordinate observations from throughout the French-speaking world, adding its data to the global pool of variable star measurements. Each national organization developed its own character and specializations, but all recognized themselves as part of a larger international enterprise, sharing data and methods and working toward common scientific goals. Among the individual amateur observers whose contributions deserve particular mention is Leslie Peltier, an American observer whose dedication and productivity remain almost difficult to comprehend. Over a lifetime of observation, Peltier accumulated approximately 132,000 variable star observations, a number so large that one must pause to consider what it actually represents. Night after night, year after year, decade after decade, Peltier went out to his small observatory in Ohio and systematically worked through his assigned stars, estimating magnitudes, recording observations, submitting reports. He began observing in 1918, using comparison charts provided by the AAVSO, and continued until poor health finally ended his career more than 50 years later. His observations filled volumes of archival records and contributed to scientific papers too numerous to count. He discovered 12 comets and several variable stars. But his greatest contribution lay simply in the patient accumulation of routine observations. The unglamorous work of watching stars change brightness and writing down what he saw. Peltier exemplified a particular kind of astronomical dedication, the willingness to subordinate personal glory to collective scientific progress. Most of his observations would never bear his name in any publication, would simply be averaged together with observations from other sources to produce light curves and period determinations credited to no individual observer. He accepted this anonymity as part of the bargain, understanding that the scientific value of his work depended precisely on its being combined with the work of others. Amateur variable star observation was not a pursuit for those seeking fame or recognition. It was a pursuit for those who found satisfaction in contributing to something larger than themselves, in knowing that their careful measurements would help future astronomers understand the behavior of distant suns. Another amateur contributor whose work deserves recognition is the Reverend Thomas David Anderson, a Scottish clergyman with a particular talent for discovering novae. Anderson discovered Nova Aurigui in 1892 and Nova Persei in 1901, both important events in the study of stellar explosions. His method was simple but effective. He had memorized the star fields visible from his locations so thoroughly that he could immediately recognize when something new appeared. This knowledge did not come easily or quickly. It represented years of patient study, night after night of looking at the same regions of sky until their patterns became as familiar as the streets of his parish. When Nova Persei blazed into visibility in February of 1901, Anderson spotted it almost immediately and notified professional astronomers, allowing them to begin observations while the nova was still brightening. The speed of this notification made possible observations that would have been lost had the discovery been delayed even a few days. The standardization of reporting forms and observational methods continued to evolve throughout the early 20th century, as organizations learned from experience what worked and what did not. The basic format established by the AAVSO and similar groups proved remarkably durable, asking observers to report the date and time of observation, the magnitude estimate, the comparison stars used, and relevant observing conditions such as the state of the atmosphere and the altitude of the star above the horizon. Some organizations experimented with more detailed reporting forms, asking for information about the observer's telescope and magnification, the length of time spent on each estimate, the observer's confidence in their measurement. The goal was always to capture enough information that later researchers could evaluate the reliability of individual observations and combine them appropriately with other data. The interwar period saw continued growth in amateur variable star observation, with the AAVSO in particular expanding its international reach and increasing the volume of observations it processed. Leon Campbell's patient leadership helped maintain coherence as the organization grew, ensuring that new observers received proper training and that established standards were consistently applied. The association developed educational materials explaining observational techniques, distributed comparison charts for hundreds of variable stars, and published regular bulletins summarizing recent observations and calling attention to stars requiring particular attention. Professional astronomers increasingly relied on amateur data for their research, citing AAVSO observations in scientific papers and acknowledging the essential contribution of the volunteer observers who had gathered them. By the middle of the 20th century, Amateur variable star observation had established itself as an indispensable component of astronomical research, a remarkable achievement for an enterprise carried out largely by unpaid volunteers working with modest equipment in their spare time. The organizations founded in the late 19th and early 20th centuries had proved their worth many times over, providing data that professionals could not have gathered on their own and demonstrating that careful amateur observation could meet scientific standards of quality and reliability. The model they developed, of coordinated volunteer networks contributing to centralized databases, would later be adopted in other areas of citizen science. But variable star observation had pioneered the approach and remained one of its most successful applications. The professional astronomers who had initially encouraged amateur observation, people like Edward Charles Pickering and those who shared his vision, had been vindicated in their belief that organized amateurs could contribute meaningfully to science. And the amateurs themselves, people like Leslie Peltier with his 132,000 observations, like the Reverend Anderson with his memorized star fields, like countless others whose names appear only in observer lists and archival records, had demonstrated that scientific dedication is not limited to those with professional training or institutional positions. They had watched the stars change, night after night and year after year, and in doing so they had helped reveal the rhythms and processes of stellar evolution. Their contribution continues, for the organizations they built still function, still gathering observations from around the world, still adding to our understanding of these distant, variable suns that have fascinated human observers since Fabricius first noticed Mira brightening in the constellation Cetus so very long ago. The story of how astronomers came to understand and organize the many different kinds of variable stars is, in its own quiet way, a story about the human desire to find patterns in what first appears to be chaos, and to move gradually from simple description toward deeper understanding of why the universe behaves as it does. When the first variable stars were discovered in the 17th and 18th centuries, there was no framework for thinking about them, no established vocabulary, no way to know whether one star that changed its brightness was doing so for the same reasons as another. Each new discovery stood somewhat alone, a curiosity to be noted and wondered at, but not yet part of any larger picture. The development of classification systems for variable stars took more than 2 centuries, and it proceeded through many stages, from the simplest catalogues that merely listed stars and their observed ranges of brightness, through increasingly sophisticated schemes that attempted to group similar behaviors together, and finally toward the integration of physical understanding that allowed astronomers to explain not just what these stars were doing, but why they were doing it. In the earliest decades of variable star observation, there was no real classification at all, simply because there were so few known examples. Mira in the constellation Cetus was the first, discovered by David Fabricius and later studied systematically by Johannes Hollwaarder and others. For many years it remained nearly unique, a star that brightened and faded over a period of roughly 11 months, disappearing from naked eye visibility and then returning. When other similar stars were eventually found, stars that also showed long periods of variation and large changes in brightness, it was natural to group them together by their resemblance to this first example, and so the term Mira variable came into use, a designation that has persisted to the present day. This pattern of naming a class of variable stars after its prototype, the first or most prominent member of the group to be identified, became standard practice in the field, and it gives the classification system a certain historical texture, with the names of individual stars serving as labels for entire categories of stellar behavior. Friedrich Wilhelm Argelander, working in Bonn during the middle decades of the 19th century, made contributions to variable star observation that extended well beyond his famous Borner Durchmusterung, the great positional catalogue of northern stars. Argelander was deeply interested in variable stars and recognized early on that systematic observation by many people would be necessary to understand their behavior. In 1844, he published an appeal to amateur astronomers, encouraging them to take up the regular monitoring of variable stars, and he established methods for visual brightness estimation that remained in use for more than a century. His catalogues of known variable stars, though modest by later standards, represented an important step toward organizing the scattered observations of earlier decades. Argelander also proposed the naming convention that would eventually become standard, suggesting that variable stars in each constellation be designated by capital letters beginning with R, since the letters A through Q had already been used by Johann Bayer for the brightest stars in his 17th century atlas. This seemingly simple suggestion had lasting consequences for how variable stars would be identified and discussed. Under Argelander's system, the first variable star discovered in a given constellation received the letter R followed by the constellation's genitive name, so that the first variable found in the constellation Leo, for instance, would be called R Leonis. The second would be S Leonis, and so on through the alphabet to Z, providing 9 possible single-letter designations. When more variables were discovered in a constellation than these 9 letters could accommodate, the system was extended to double letters, beginning with RR and proceeding through RS, RT, and onward to RZ, then SS through SZ, and so forth, eventually reaching ZZ. This allowed for a total of 54 more designations per constellation. In time, as photographic surveys revealed ever more variable stars, even this extended scheme proved insufficient, and a numerical system was adopted for stars beyond the 334th variable in any constellation, using designations such as V335, V336, and continuing upward without limit. The naming convention thus bears the marks of its gradual historical development, starting from a simple alphabetical scheme that seemed more than adequate in the mid-19th century, when only a few dozen variable stars were known, and expanding by necessity as the true abundance of stellar variability was revealed. As more variable stars accumulated in the catalogues, the need for meaningful classification became increasingly apparent. Simply listing stars alphabetically by constellation told observers nothing about the nature of the variability they were studying. Were all variable stars examples of a single phenomenon, or were there fundamentally different kinds of stellar change occurring for different reasons? This question could not be answered until enough examples had been gathered to reveal patterns, and until the observations themselves became precise enough to distinguish between different types of behavior. By the late 19th century, both conditions were beginning to be met. The light curves of many variable stars had been carefully determined, showing how their brightness changed over time, and it was clear that these curves came in distinctly different shapes. Some stars, like Mira, showed smooth, roughly symmetrical rises and falls over periods of many months. Others, like Algol in Perseus, showed long stretches of nearly constant brightness interrupted by sharp, regular dips. Still others, like Delta Cephei, displayed continuous, wave-like variations with periods measured in days and distinctive asymmetric profiles, rising to maximum more quickly than they faded to minimum. The recognition that delta Cephei and similar stars formed a coherent class was one of the great organizing achievements of 19th-century variable star astronomy. These stars, which came to be called Cepheids after their prototype, shared a characteristic pattern of variation that was unmistakable once it had been identified. Their periods ranged from roughly 1 day to several weeks. Their brightness changes were completely regular and repeatable, and the shape of their light curves, with the rapid rise and slower fall, was consistent from one example to another. The discovery by Henrietta Swan Leavitt in 1908 that the periods of Cepheids in the Magellanic Clouds were related to their intrinsic luminosities made these stars enormously important for measuring cosmic distances. But even before this relationship was established, Cepheids were recognized as a distinct and significant type of variable star. The integration of spectral classification with variability studies represented a major advance in understanding the physical nature of variable stars. And here the work of Annie Jump Cannon at Harvard College Observatory was of central importance. Cannon spent decades classifying stellar spectra, developing and refining the system of spectral types that remains in use today. The familiar sequence of O, B, A, F, G, K, and M stars arranged by surface temperature. Her work on the Henry Draper catalogue and its extensions, carried out under the direction of Edward Pickering and funded by a memorial to the amateur astronomer Henry Draper, resulted in the classification of hundreds of thousands of stellar spectra. This monumental effort, which owed much to the contributions of other women computers at Harvard including Williamina Fleming and Antonia Mori, provided a framework for understanding where variable stars fit within the broader population of stars generally. When the spectral types of variable stars were systematically determined, clear patterns emerged. The long-period variables like Mira proved to be cool red stars of spectral type M, giant or supergiant stars with extended atmospheres. The Cepheids were found to be yellow supergiants, spectral types F and G, much more luminous than the Sun. The eclipsing binary Algol contained hot blue-white stars of spectral type B. These correlations were not coincidental, and they pointed toward the physical mechanisms responsible for the different types of variability. Cool red giants with their extended, tenuous atmospheres were apparently prone to large-scale pulsations that changed their brightness over periods of months. Yellow supergiants of a certain temperature and luminosity pulsated more rapidly and more regularly. The brightness changes of Algol-type stars had nothing to do with changes in the stars themselves, but rather with the geometry of two stars orbiting one another and periodically blocking each other's light. This last point highlights one of the fundamental distinctions that gradually became clear in variable star classification: the difference between intrinsic and extrinsic variability. An intrinsically variable star is one that is actually changing, its luminosity rising and falling because of physical processes occurring within or upon the star itself. Pulsating stars like Mira and the Cepheids are intrinsically variable, as are stars that experience eruptions, flares, or other energetic events. An extrinsically variable star, by contrast, is not really changing at all in any fundamental sense, but merely appears to change because of geometric effects, most commonly because it is part of a binary or multiple star system in which one star periodically passes in front of another as seen from Earth. The eclipsing binaries, of which Algol is the prototype, are the most important class of extrinsic variables. Their light curves can be analyzed to yield information about the sizes, masses, and orbital properties of the component stars, making them valuable astrophysical laboratories. But the variability itself is a consequence of our viewing angle rather than any physical change in the stars. The classification of eclipsing binaries into subtypes reflects the diversity of these systems. The designation EA refers to Algol-type eclipsing binaries, systems in which the two component stars are well separated and spend most of their orbital period at nearly constant combined brightness, with relatively sharp and distinct eclipses when one star passes in front of the other. The designation EB refers to beta Lyrae type systems, in which the stars are closer together and often distorted into ellipsoidal shapes by their mutual gravitational attraction, producing light curves that show continuous variation throughout the orbital cycle rather than flat maxima between eclipses. The designation EW refers to W Ursae Majoris type systems, contact binaries in which the two stars are so close that they share a common envelope of material, resulting in components of nearly equal surface brightness and light curves with eclipses of almost identical depth. These subtypes, named after their prototype stars, illustrate how classification could capture physically meaningful differences within a broader category. The RR Lyrae stars constitute another important class that received its name from a prototype, in this case the variable star RR in the constellation Lyra. These stars were recognized as a distinct group through the patient accumulation of observations at several observatories, and they proved to have periods much shorter than the classical Cepheids, typically ranging from about a quarter of a day to roughly 1 day. Their light curve shapes resembled those of Cepheids, with rapid rises and slower declines, but their periods and luminosities placed them in a different part of the stellar population. The RR Lyrae stars are found in abundance in globular clusters, the ancient spherical aggregations of stars that surround our galaxy, and they proved to be old, metal-poor stars quite different in their evolutionary history from the classical Cepheids. This distinction led astronomers to recognize that there were in fact two populations of Cepheid-like pulsating stars: the classical Cepheids associated with young stellar populations and the Type II Cepheids and RR Lyrae stars associated with old populations, a recognition that was closely connected to Walter Bade's identification of stellar populations in the 1940s. The progression from purely descriptive classification toward physically based classification involved considerable debate among astronomers. Some argued that classification should be based strictly on observable properties: the shape of the light curve, the period, the amplitude of variation, without making assumptions about underlying physical causes. This approach had the virtue of objectivity, since it relied only on what could be directly measured, and it avoided the risk of misclassifying stars based on incorrect theoretical ideas. Others argued that classification should aim to group together stars that were physically similar, even if this required making inferences about stellar structure and evolution. Under this view, a classification system was not merely a filing scheme for observations but a map of stellar physics, and it should be revised as understanding improved. In practice, variable star classification evolved to incorporate both perspectives, retaining descriptive categories based on light curve morphology while also recognizing physical groupings such as pulsating variables, eruptive variables, cataclysmic variables, and rotating variables. The effort to compile a comprehensive catalogue of all known variable stars, with consistent nomenclature and classification, culminated in the General Catalogue of Variable Stars, first published in 1948 under the editorship of Boris Vasilievich Kukarkin and Pavel Petrovich Poronago at the Sternberg Astronomical Institute in Moscow. This work represented the consolidation of more than 3 centuries of variable star observations into a single authoritative reference. Kukarkin and Paranago had been working on the project for years, gathering data from observatories around the world, standardizing star designations, and assigning classification types according to an evolving scheme that attempted to accommodate the full diversity of known variable stars. The first edition of the General Catalogue listed several thousand variables with their positions, brightness ranges, periods where known, spectral types, and variability classifications. It was intended not as a final statement but as a living document that would be updated as new discoveries were made and new understanding was gained. The Moscow location of this cataloging effort reflected the strong tradition of variable star research that had developed in Russia and the Soviet Union, building on earlier work by astronomers such as Sergei Blashko, who had discovered the curious period modulations seen in some Lyrae stars, and Vasily Struve, who had contributed to double star astronomy in the 19th century. The Sternberg Institute became a center for the coordination of variable star observations internationally, maintaining the general catalogue through successive editions and supplements as the number of known variables grew from thousands to tens of thousands and eventually to hundreds of thousands. The naming conventions established in the 19th century, with their alphabetical and numerical designations, proved flexible enough to accommodate this growth, even as the classification schemes became increasingly detailed and subdivided. The integration of physical understanding with observational classification continued throughout the first half of the 20th century. The theory of stellar pulsation, developed by Arthur Eddington and others, explained why Cepheids and related stars varied as they did, identifying the ionization of helium in their outer layers as the driving mechanism for their oscillations. The theory of stellar evolution, emerging from the work of many researchers, explained why only stars in certain stages of their lives and with certain properties would become variable. The study of binary star dynamics explained the light curves of eclipsing systems in terms of the sizes, separations, and orbital inclinations of the component stars. Each advance in theory enriched the classification system, transforming it from a taxonomy of appearances into a map of stellar physics. Yet the older, observationally based classifications were not abandoned, for they remained useful as a first step in identifying what type of star one was dealing with, before more detailed physical analysis could be undertaken. By the middle of the 20th century, the field of variable star research had matured into a discipline with established methods, comprehensive catalogues, international coordination, and a theoretical framework that connected observations to physical understanding. The simple curiosity aroused by Mira's unexpected fading in 1638 had grown into a branch of astronomy that touched on stellar structure, stellar evolution, the distant scale of the universe, and the dynamics of binary systems. The classification schemes that had developed over those 3 centuries bore the marks of their history, with names drawn from prototype stars, letters and numbers assigned by conventions established when only a handful of variables were known, and categories that reflected the gradual refinement of both observational technique and theoretical insight. It was a quiet, cumulative achievement, the work of many hands over many generations, each contributing some small piece to a picture that no single individual could have constructed alone. And so we come now to a rather lovely idea, one that may help you settle more deeply into wherever you are resting. And that idea is simply this: that stars can breathe. Not in the way that you are breathing now, slowly and peacefully, but in their own stellar fashion, swelling outward and then contracting inward again, over and over, with a regularity that astronomers eventually came to understand through decades of patient theoretical work. The Cepheid variables, those dependable celestial beacons we have already met, were not always understood to be pulsating objects, and the journey toward recognizing them as breathing stars rather than something else entirely is a gentle and meandering story, one filled with careful mathematics and quiet revelations that accumulated over many years. We might begin this particular chapter of our tale in the year 1879, when a German physicist named August Ritter turned his attention to a question that might seem almost abstract at first, namely what would happen if a sphere of gas were to oscillate radially, expanding and contracting while maintaining its spherical shape. Ritter was not specifically thinking about variable stars when he began this work, but rather about the general physics of gaseous bodies, and his investigations were carried out with the kind of theoretical patience that characterized much of 19th century physics. He worked through the mathematics of how such a sphere would behave, considering how the pressure and density would change as the sphere expanded and contracted, and he arrived at certain relationships that would later prove remarkably relevant to the study of pulsating stars. Among these was a relationship between the period of oscillation and the mean density of the sphere, a connection that suggested denser spheres would oscillate more quickly while less dense spheres would take longer to complete each cycle of expansion and contraction. This work sat quietly in the scientific literature for many years, appreciated by those who encountered it but not yet connected to the puzzle of why certain stars varied in brightness with such clock-like regularity. The question of what exactly the Cepheid variables were doing remained open for some time, and one of the leading ideas in the late 19th and early 20th centuries was that these stars might be binary systems, pairs of stars orbiting one another in such a way that they periodically eclipsed each other or otherwise caused variations in the total light we received from them. This was a sensible hypothesis, as binary stars were well known and their ability to produce periodic brightness changes was well established. However, a young astronomer named Harlow Shapley, working in the 1910s, began to notice certain features of the Cepheid variables that did not fit comfortably with the binary hypothesis. In 1914, Shapley put forward arguments that these stars were more likely to be single stars undergoing some kind of pulsation, and one of the key pieces of evidence he marshaled was the correlation between the periods of these stars and their spectral types. The spectral type of a star reveals information about its temperature and physical characteristics, and Shapley observed that among the Cepheids, there was a clear relationship between how long a star took to complete its cycle of variation and what kind of spectrum it displayed. This correlation made sense if the stars were pulsating, because one would expect the physical properties of a pulsating star to be connected to how quickly or slowly it could oscillate. But it was harder to explain if the stars were binaries, where the period would depend primarily on the orbital characteristics of two separate objects rather than the intrinsic properties of a single star. Shapley's argument was not immediately accepted by everyone, as the binary hypothesis had its defenders, but it marked an important step toward the pulsation theory that would eventually prevail. The theoretical understanding of how stars could actually pulsate, and why they would do so in a sustained and regular fashion rather than simply oscillating once and then settling down, required much deeper investigation into the physics of stellar interiors. And this is where the work of Arthur Stanley Eddington becomes central to our story. Eddington was one of the great astrophysicists of the early 20th century, a man whose contributions to our understanding of stars were profound and far-reaching, and he brought to the problem of stellar pulsation both mathematical skill and physical insight. Beginning around 1917 and continuing through the 1920s, Eddington developed a theoretical framework for understanding how pulsation could work in stars like the Cepheids. One of the fundamental challenges he faced was explaining how the pulsation could be maintained over time, because in most physical systems, oscillations tend to die away as energy is dissipated, and yet the Cepheids showed no signs of their variations diminishing. There had to be some mechanism that was feeding energy into the pulsation, keeping it going century after century. Eddington proposed what came to be known as a valve mechanism, drawing an analogy to the way a valve in a heat engine could convert thermal energy into mechanical motion. The basic idea was that certain layers within the star could act as a kind of valve, trapping heat during one phase of the pulsation cycle and then releasing it during another phase, in such a way that energy was systematically fed into the oscillation rather than being lost. The key to this mechanism lay in how the opacity of the stellar material, which is to say how readily it absorbed and blocked the passage of radiation, changed as the star expanded and contracted. Opacity is a measure of how difficult it is for light to pass through a substance, and in the hot, dense interiors of stars, opacity depends on temperature and density in complex ways. Eddington realized that if the opacity behaved in the right way, it could create the conditions for sustained pulsation. The specific mechanism that Eddington identified, which later came to be called the kappa mechanism after the Greek letter kappa that is conventionally used to represent opacity, works something like this, and you may find the gentle logic of it rather soothing to follow. Imagine a layer within the star that is being compressed as the star contracts. Normally, when gas is compressed, it heats up, and you might expect that heating to increase the pressure and push back against the compression, which would tend to damp out the oscillation. However, if the opacity of the material increases when it is compressed and heated, then that layer will trap more of the radiation trying to pass through it from the hotter interior below. This trapped radiation adds to the pressure in that layer, and this extra pressure comes at just the right time to push the layer outward again when the star begins to expand. Conversely, when the star is expanding and the layer is becoming less compressed and cooler, the opacity decreases, allowing radiation to escape more freely, which reduces the pressure and allows the layer to fall inward again. The net effect is that energy is being added to the oscillation at each cycle, through this asymmetry in how radiation is trapped and released, and this is what keeps the pulsation going indefinitely. Eddington's theoretical work established the broad outlines of how stellar pulsation could work, but the detailed understanding of exactly which physical processes were responsible for the opacity changes that drove the pulsation took longer to develop. The interiors of stars are composed primarily of hydrogen and helium, along with small amounts of heavier elements, and the opacity of this material depends on various atomic processes, including the ionization of atoms, which is to say the stripping away of electrons from atoms by the intense heat. When atoms are partially ionized, meaning some but not all of their electrons have been removed, the material can have different opacity properties than when the atoms are fully ionized or neutral, and this turns out to be crucial for understanding pulsation. The identification of exactly which ionization process was primarily responsible for driving Cepheid pulsation came in 1953, when a Soviet astrophysicist named Sergei Alexandrovich Zhevakin published work identifying the ionization of helium as the key mechanism. Specifically, Zhevakin showed that the second ionization of helium, which is the removal of the second electron from helium atoms that have already lost their first electron, occurs at temperatures and depths within Cepheid-type stars that are ideally suited to drive pulsation through the kappa mechanism. When the star compresses and heats, helium atoms in this zone absorb energy by having their second electron stripped away, And this absorption of energy is associated with an increase in opacity that traps radiation and provides the extra push needed to sustain the pulsation. The zone where this second helium ionization occurs acts as the valve that Eddington had envisioned, and Jevikin's identification of this process was an important step forward in the detailed understanding of stellar pulsation. There is a quantity that astrophysicists use when discussing pulsating stars called the pulsation constant, which is conventionally denoted by the letter Q. And this quantity captures the relationship between a star's pulsation period and its physical properties in a useful way. The pulsation constant is related to the period density relation that August Ritter had derived decades earlier in his theoretical work on oscillating gas spheres, and it provides a way of characterizing different modes of pulsation and comparing pulsating stars of different types. The basic relationship states that the period of pulsation multiplied by the square root of the mean density of the star gives approximately the same value for stars pulsating in the same mode, which means that denser stars pulsate more quickly and less dense stars pulsate more slowly, just as Ritter's early work had suggested. This period density relation was confirmed observationally for the Cepheids and other pulsating stars, providing further support for the pulsation theory and offering a way to estimate the physical properties of pulsating stars from their observed periods. One of the puzzles that the theory of stellar pulsation had to address was why only certain stars showed Cepheid-type pulsation, while the vast majority of stars remained constant in their brightness. If the Kappa mechanism could drive pulsation, why did it not do so in all stars? Or at least in a much wider variety of stars than was actually observed? The answer to this puzzle emerged from the recognition that the driving mechanism only works effectively when the ionization zone that acts as the valve is located at the right depth within the star, and this depends on the star's temperature and luminosity. The Hertzsprung-Russell diagram, which you may recall is the chart that plots stars according to their luminosity and temperature, shows a distinct region called the instability strip where pulsating stars like the Cepheids are found, and understanding why this strip exists and has the boundaries it does became an important goal of pulsation theory. In stars that are too hot, the helium ionization zone lies too close to the surface, where there is not enough mass above it for the valve mechanism to work effectively. In stars that are too cool, the ionization zone lies too deep within the star, where other damping effects overwhelm the driving mechanism. Only in stars with temperatures that place the ionization zone at just the right depth does the pulsation get driven effectively, and these are the stars that populate the instability strip. Furthermore, the luminosity of the star matters because more luminous stars have more extended envelopes, which affects where the ionization zones are located relative to the total structure of the star. The boundaries of the instability strip, both the blue edge where stars are too hot and the red edge where stars are too cool, could be understood in terms of where the helium ionization zone fell relative to the stellar structure. And working out these boundaries in detail occupied theorists for many years. The work of understanding pulsation did not stop with the initial successes of Eddington and Jevikin, and many other astrophysicists contributed refinements and elaborations of the theory in subsequent decades. Among these were John Cox and Charles Whitney, who worked on developing more detailed and accurate models of stellar pulsation that could account for the observed properties of Cepheids and other variable stars with greater precision. Their work, along with that of many others, involved constructing numerical models of stellar interiors and envelopes, following how these models would behave as they pulsated, and comparing the results with observations. The advent of electronic computers in the mid-20th century made it possible to carry out much more detailed calculations than had been feasible by hand, And this computational power allowed theorists to explore the physics of pulsation in greater depth and to test their ideas more rigorously against the growing body of observational data. The theory of stellar pulsation that emerged from this collective effort was a satisfying achievement, connecting the observed behavior of variable stars to fundamental physics in a coherent and testable way. The regular breathing of the Cepheids, their swelling and contracting with such dependable rhythm, could now be understood as a natural consequence of how radiation interacted with partially ionized helium in their outer layers, with the ionization zone acting as a valve that fed energy into the oscillation and kept it going. The period-luminosity relation that Henrietta Leavitt had discovered observationally could now be understood theoretically, because more luminous Cepheids were also larger and less dense, which meant they pulsated more slowly according to the period-density relation. The existence of the instability strip could be understood in terms of where the ionization zones fell within stars of different temperatures, and the boundaries of this strip could be predicted from theory and compared with observation. This understanding did not come quickly or easily, but accumulated over decades through the work of many individuals, each contributing pieces to the puzzle. From Ritter's abstract considerations of oscillating gas spheres in 1879, through Shapley's arguments for pulsation over binarity in 1914, through Eddington's development of the valve mechanism in the 1920s, through Jeverkin's identification of helium ionization in 1953, and through the refinements of Cox and Whitney and many others, the theory of stellar pulsation was gradually assembled into a coherent and powerful framework. The breathing stars, those gentle cosmic oscillators, had yielded their secrets to patient inquiry, and the understanding that emerged was both beautiful in its physical clarity and useful in its astronomical applications. And so we may rest now with this image of stars gently pulsing, their outer layers rising and falling in slow cosmic respiration, driven by the subtle interplay of radiation and ionization deep within their atmospheres. The mathematics of their pulsation is complex, but the basic picture is one of balance and rhythm, of energy being fed into the oscillation just enough to keep it going, of valves opening and closing with astronomical regularity. These breathing stars, the Cepheids and their cousins in the instability strip, continue their patient pulsations as they have for millions of years, and will continue long after we have drifted into sleep, their light carrying across the vastness of space the steady rhythm of their cosmic breath. And so we turn now to a rather lovely corner of variable star astronomy, one where geometry and light combine in the most satisfying way, where patient observation and careful mathematics allow us to measure things that might otherwise seem quite beyond our reach. The eclipsing binary stars, you see, offered astronomers something remarkable, a way to determine the actual physical dimensions of stars, their true sizes and masses, quantities that for single stars remained frustratingly unknowable throughout much of astronomical history. The development of techniques to extract this information from the gentle undulations of light curves is a story of slow, methodical progress, of mathematicians and observers working together across decades to refine methods that grew ever more precise, ever more revealing of the intimate details of these distant stellar pairs. We have already encountered the eclipsing binaries in our earlier discussions, those systems where two stars orbit one another in a plane that happens to be aligned nearly edge-on to our line of sight from Earth, so that periodically one star passes in front of the other, blocking some portion of its light and causing the combined brightness of the system to diminish in a regular and predictable fashion. The light curve of such a system, that smooth graph showing how brightness changes over time, contains within its shape a wealth of information about the stars themselves, Information that patient analysis can gradually coax into the open, much like reading a letter written in a script one has only partially learned, where meaning emerges slowly but surely with careful attention. The earliest observers of eclipsing binaries, Goodricke and Piggott, and those who followed in the late 18th and early 19th centuries, recognized that these regular dimmings indicated eclipses, but the detailed mathematical analysis of what the light curve shapes could tell us about stellar properties came considerably later. The problem, you see, is not a simple one. The shape of the light curve depends on many factors working together: the relative sizes of the two stars, how bright each one is compared to the other, the inclination of the orbital plane to our line of sight, the eccentricity of the orbit if it is not perfectly circular, and even the way light falls off toward the edges of each stellar disk due to an effect we shall discuss shortly called limb darkening. Untangling all these factors from a single wavy line on a graph required mathematical techniques of considerable sophistication. It was Henry Norris Russell, working at Princeton University in the early 20th century, who developed the first truly comprehensive method for extracting stellar dimensions and orbital parameters from eclipsing binary light curves. Russell, who would later become famous for his work on the diagram relating stellar luminosity to spectral type that now bears his name along with that of Ejnar Hertzsprung, published his fundamental paper on eclipsing binary analysis in the Astrophysical Journal in 1912. This work represented years of careful mathematical development, and it provided astronomers with a systematic procedure, a recipe of sorts, for working backward from the observed shape of a light curve to the physical properties of the system that produced it. Russell's method was based on recognizing that different features of the light curve carried information about different aspects of the binary system. The depth of the eclipses, how much the light dropped when one star passed in front of the other, depended on the relative sizes and brightnesses of the two stars. The duration of the eclipses, how long the light remained diminished before recovering, told observers something about the sizes of the stars relative to their orbital separation. The shape of the ingress and egress, how the light curve curved as one star began to cover or uncover the other, contained information about the inclination of the orbit and about how brightness varied across the stellar disks. And the presence or absence of a secondary minimum, a shallower dip occurring when the other star was eclipsed, revealed the relative temperatures and luminosities of the two components. The mathematics Russell developed allowed these various pieces of information to be combined systematically, solving a set of equations that related observable quantities, things that could be measured from the light curve, to physical parameters, things that described the actual stars and their orbit. The process was laborious, requiring many calculations performed by hand in those days before electronic computers, but it worked, and it opened a door that had previously been firmly closed. For the first time, astronomers could determine the actual radii of stars, not merely their brightnesses or their colors, but their physical sizes measured in kilometers or in units of the solar radius. When these eclipsing binary results were combined with spectroscopic observations, the results became even more powerful. Spectroscopy, you see, could reveal the velocities of stars along our line of sight through the Doppler shifting of their spectral lines, and in a binary system where both stars are moving in their mutual orbit, spectroscopy could determine the velocity amplitudes of each star, combined with the orbital period, which the light curve gave directly. These velocities allowed the actual physical size of the orbit to be calculated, not merely its angular size on the sky, but its true dimension in kilometers. And from the orbital size and period, Through the straightforward application of Newton's laws of gravitation, came the masses of the stars. This was extraordinary, if one pauses to consider what it meant. The masses of stars, those most fundamental of stellar properties, were directly measurable only for binary systems, and eclipsing binaries where the orbital plane was seen edge-on gave the most complete information because there was no ambiguity about the inclination of the orbit. Single stars, no matter how bright, no matter how well observed, kept their masses secret, but eclipsing binaries revealed theirs to patient observers armed with Russell's methods. From the masses and the radii, moreover, came the mean densities of the stars, and astronomers could begin to understand the physical structure of stellar interiors, could begin to test theories of how stars were built and how they generated their prodigious outputs of energy. Russell's 1912 paper was not the end of the story, of course, for science rarely reaches final answers, only progressively better approximations. The methods required refinement and extension as observations improved and as theoretical understanding deepened. In this ongoing development, the work of Zdeněk Koupal stands out with particular prominence. Koupal, a Czech-born astronomer who spent much of his career in England, devoted himself to the mathematics of close binary systems with a thoroughness that has rarely been equaled. His monumental works on the subject, published from the 1940s onward, extended and refined the analytical techniques to handle systems where the stars were so close together that they distorted each other's shapes through their mutual gravitational attraction. In such close binaries, you see, the stars are no longer spherical. Gravity pulls them out of shape, elongating them toward each other like two water droplets about to merge, and this distortion affects the light curve in subtle but measurable ways. Even when no eclipse is occurring, the total light from the system varies as the elongated stars present different aspects toward Earth during their orbit, and this ellipsoidal variation, as it came to be called, had to be accounted for in any accurate analysis. Koupal developed mathematical techniques to handle these complications, techniques that remained the standard approach for decades and that formed the foundation upon which later computer-based methods would build. The classification of eclipsing binaries into distinct types emerged naturally from the accumulation of observations and the recognition that these systems displayed different characteristic light curve shapes corresponding to different physical configurations. Three main classes came to be recognized, each named after a prototype star, and each representing a different relationship between the sizes of the stars and the dimensions of their mutual orbit. The Algol type eclipsing binaries, sometimes called detached systems, are those where both stars are well separated from each other, each fitting comfortably within its own region of space, neither one filling the teardrop-shaped volume called the Roche lobe within which its gravity dominates. The prototype of this class is Algol itself, Beta Persei, that same star whose regular fading first caught John Goodricke's attention in 1782 and 1783. In Algol-type systems, the light curve shows well-defined ellipses with relatively flat portions between them, because when no eclipse is occurring the stars maintain essentially constant brightness, their spherical shapes presenting the same luminous area regardless of orbital phase. The eclipses themselves can be quite deep if one star is significantly larger or brighter than the other, and the primary and secondary minima often differ substantially in depth, reflecting the different temperatures of the two stellar surfaces. The Beta Lyrae type eclipsing binaries represent a more intimate configuration, where at least one of the stars has expanded to fill or overflow its Roche lobe. The prototype here is Beta Lyrae itself, the second eclipsing binary to be discovered, whose variability was recognized by John Goodricke in 1784, just a year after his work on Algol. Beta Lyrae shows a light curve that is continuously changing, never quite flat even between eclipses, because the stars are so close and so distorted that their apparent brightness varies throughout the orbit due to their non-spherical shapes and due to gas streaming between them. These semi-detached systems often show evidence of mass transfer, material flowing from one star to the other, complicating both their light curves and their evolutionary histories. The third class, the WRC Majoris type eclipsing binaries, represents the most extreme case, where both stars have expanded to fill their Roche lobes completely and are actually in contact with each other, sharing a common envelope of gas. The prototype of this class is WRC Majoris, a star in the northern constellation of the Great Bear, whose variability was discovered in 1903 by the German astronomer Gustav Müller and Ernst Hartwig. These contact binaries show light curves with eclipses of nearly equal depth, the primary and secondary minima being almost indistinguishable, because the two stars share their outer layers and have come to nearly the same surface temperature despite sometimes having quite different masses. The periods of WRC Majoris systems are typically quite short, measured in hours rather than days, because the stars must orbit very close to each other to maintain their contact configuration. These three classes represent something of an evolutionary sequence, though the details are complex and depend on the initial masses and separations of the stellar pair. As stars age and evolve, they tend to expand, and a binary that begins its life as a detached Algol-type system may eventually become semi-detached as one star grows to fill its Roche lobe, and may in some cases progress to a contact configuration. The study of eclipsing binaries in all their variety has provided crucial tests of our understanding of stellar evolution, showing us how stars change over time not in isolation but in the gravitational embrace of companions. The improvement of observational techniques throughout the early 20th century allowed ever more precise light curves to be obtained, and two astronomers deserve particular mention for their contributions to the photoelectric observation of eclipsing binaries. Joel Stebbins, working at the University of Illinois and later at the University of Wisconsin, was a pioneer in the application of photoelectric photometry to stellar observations, beginning in the first decade of the 20th century. Stebbins recognized that the human eye and the photographic plate both had limitations in precision, and he worked to develop electronic detectors that could measure stellar brightness with far greater accuracy and consistency. His photoelectric observations of eclipsing binaries revealed subtle features of their light curves that had been invisible to earlier methods, and his work helped establish photoelectric photometry as the standard technique for precise stellar brightness measurements. Sergei Gaposchkin, born in Russia and working later at Harvard Observatory alongside his wife Cecilia Payne-Gaposchkin, also made substantial contributions to the observation and analysis of eclipsing binaries. The Gaposchkins were indefatigable workers who catalogued and analyzed vast numbers of variable stars, including many eclipsing systems, and their careful observational work provided the raw material upon which theoretical understanding could be built. One of the most interesting discoveries to emerge from the detailed analysis of eclipsing binary light curves was the phenomenon of limb darkening. If you could observe the Sun through a properly filtered telescope, which you should never attempt without appropriate equipment, you would notice that the disk of the Sun appears slightly brighter at its center than at its edges. This is limb darkening, and it occurs because when we look at the center of the solar disk, we are looking straight down into the solar atmosphere, seeing to relatively deep and hot layers, while when we look at the edge or limb we are looking obliquely through the atmosphere and seeing only the cooler outer layers. The effect is subtle on the Sun, a gentle gradation from center to edge, but it has measurable consequences for eclipsing binary light curves. When one star in an eclipsing binary begins to pass in front of the other, it first covers the edge of the disk behind, the part that is slightly dimmed by limb darkening, and only later does it cover the brighter central regions. This means that the light does not decrease linearly during ingress and egress, but follows a curved path that depends on the degree of limb darkening present. By analyzing the precise shape of the light curve during these partial phases of eclipse, astronomers can determine the limb darkening coefficient of the eclipsed star, and this provides information about the structure of its atmosphere, about how temperature varies with depth in its outer layers. The analysis of limb darkening from eclipsing binary light curves was one of the early triumphs of the detailed mathematical methods developed by Russell and refined by Köppel and others. It demonstrated that these stellar systems were not merely geometric curiosities but actual physical laboratories where the properties of stellar atmospheres could be probed in ways impossible for single stars. The coefficients of limb darkening derived from eclipsing binary observations could be compared with theoretical predictions from models of stellar atmospheres, providing tests of our understanding of how light is absorbed and emitted in the outer layers of stars. Throughout the period we are considering, from Russell's foundational work in 1912 through the refinements of the 1930s and 1940s, the analysis of eclipsing binary light curves grew steadily more sophisticated. Each improvement in observational precision revealed new features that required theoretical explanation, and each theoretical advance suggested new observations that might test the predictions. This back and forth between observation and theory, this gradual accumulation of understanding through patient work, is characteristic of how science progresses, not through sudden revolutions so much as through the steady accretion of knowledge, layer upon layer, like the sediments that build up slowly on the ocean floor. The fundamental importance of eclipsing binary studies lay in their provision of basic stellar data, the masses and radii and densities of stars, that could not be obtained by any other means. These parameters, measured for a growing number of eclipsing systems, revealed the relationships between mass and luminosity, between mass and radius, that characterize stars of different types. They showed that more massive stars are both larger and more luminous than less massive ones, following regular patterns that could be expressed in mathematical relationships. They revealed that red giant stars, those cool luminous objects that puzzled early astronomers, were indeed giants, stars of enormous physical extent, while white dwarf stars were compact objects smaller than Earth despite containing masses comparable to the Sun. This empirical foundation, built up patiently through the analysis of one eclipsing binary after another, provided the observational constraints that any theory of stellar structure and evolution had to satisfy. The theoretical physicists who worked to understand how stars generate their energy and how they change over time had to produce models that matched the masses, radii, and luminosities that the eclipsing binary observers had determined. In this way, the quiet work of measuring light curves and solving Russell's equations contributed to the grand enterprise of understanding the physical nature of the stars. And so we may picture the astronomers of this era, bent over their calculations or peering at their photographic plates or reading the deflections of their photoelectric galvanometers, engaged in work that might seem tedious to the casual observer but that held within it the promise of genuine discovery. The regular fading of Algol, noticed by Goodricke in the 18th century, had grown into a sophisticated branch of astrophysics, a means of weighing and measuring the stars themselves. The geometry of eclipses, combined with the mathematics of orbits and the physics of light, had opened a window onto the fundamental properties of these distant suns, and the view through that window grew ever clearer as the years passed and the techniques improved. And so we come now to a quieter revolution, one that unfolded not in a single dramatic moment but gradually, across decades of patient refinement, as astronomers learned to replace the sensitive but imperfect human eye with something steadier, something that did not tire or misjudge, something that could perceive differences in starlight too subtle for any living retina to detect. This was the introduction of photoelectric photometry, and it would transform the measurement of variable stars from an art requiring years of trained observation into something approaching a precise physical science. Though of course the human mind and hand remained essential in designing the instruments and interpreting what they revealed. The story begins, as so many stories in science begin, with a curious researcher and a modest instrument. And in this case that researcher was Joel Stebbins, a young American astronomer working at the University of Illinois in the quiet college town of Urbana. Stebbins had arrived there in 1903 to take charge of the university's small observatory, which housed a 12-inch refracting telescope of the sort common at teaching institutions of that era, perfectly adequate for introducing students to the night sky, but not particularly distinguished for research purposes. Yet Stebbins possessed that particular quality of mind that sees possibility where others see limitation. And by 1907 he had begun experimenting with something quite novel, the application of a selenium cell to the measurement of starlight. Selenium, you may recall from earlier lessons in chemistry or physics that you have perhaps half forgotten, is a metalloid element discovered in 1817, and one of its curious properties, recognized in 1873 by the telegraph engineer Willoughby Smith, is that its electrical resistance changes when light falls upon it. In complete darkness, selenium conducts electricity rather poorly, but as light increases, the resistance decreases and current flows more readily, and this relationship between illumination and electrical conductivity suggested to several imaginative minds that selenium might serve as a kind of artificial eye, converting light into measurable electrical signals. Various experimenters had attempted to use selenium for astronomical purposes before Stebbins, but the sensitivity of the cells was poor, the response was sluggish and often unreliable, and the difficulties seemed insurmountable. Stebbins was not deterred by these earlier failures, and working with what we might charitably describe as homemade equipment, he constructed a selenium photometer that he could attach to the eyepiece end of the Illinois 12-inch telescope. The apparatus was delicate and temperamental, requiring constant adjustment and careful shielding from stray light, and the signals it produced were faint indeed, requiring a sensitive galvanometer to detect the tiny currents that varied as different stars drifted through the field of view. Progress was measured not in months but in years, as Stebbins patiently refined his technique, learning to account for the many sources of error and noise that afflicted these early measurements. By 1910, Stebbins had achieved something remarkable with this unpromising equipment: the detection of what we now call the secondary eclipse of the bright star Algol. Now, Algol had been known as an eclipsing binary for well over a century, its primary minimum, when the fainter companion passes in front of the brighter star, being easily visible to any careful observer, but the secondary minimum, when the brighter star partially blocks the fainter companion, produces a dimming of only about 1/10 of a magnitude, far below what the human eye could reliably detect against all the sources of variation and error that plague visual estimates. Stebbins, with his selenium cell and his patient methodology, recorded this secondary eclipse clearly and repeatedly, demonstrating that photoelectric methods could perceive variations invisible to even the most skilled human observer. This was a proof of concept of the most compelling kind, and Stebbins continued to refine his work, publishing careful studies of eclipsing binaries that revealed details of their light curves no visual observer could hope to match. But selenium cells had fundamental limitations. Their response to light was slow, taking appreciable fractions of a second to stabilize when the illumination changed, and their sensitivity, while sufficient for bright stars, proved inadequate for the fainter objects that increasingly interested astronomers. Stebbins recognized that a better detector was needed, and fortune provided one in the form of the photoelectric cell based on the alkali metals. The photoelectric effect, that phenomenon by which certain metals emit electrons when struck by light, had been discovered by Heinrich Hertz in 1887 and explained theoretically by Albert Einstein in 1905, for which Einstein would eventually receive his Nobel Prize. Unlike the selenium cell, which relied on changes in resistance, photoelectric cells produced an actual current of electrons knocked free from a photosensitive surface, and this current was directly proportional to the intensity of the incident light. Moreover, the response was essentially instantaneous, and by choosing appropriate photosensitive materials, cells could be made responsive to different portions of the spectrum. In the 1910s, Stebbins began working with potassium hydride photoelectric cells, which proved far superior to his old selenium apparatus. Potassium surfaces were particularly sensitive to blue and violet light, which happened to be well suited to astronomical work since most stars emit generously in these wavelengths. The current produced by starlight falling on a potassium cell was still extremely small, measured in billionths of an ampere, but sensitive galvanometers and later vacuum tube amplifiers could detect and measure these minute signals with remarkable accuracy. Through the 1920s, Stebbins continued his photoelectric work, now at the Washburn Observatory of the University of Wisconsin in Madison, where he had relocated in 1922 to take advantage of better instruments and facilities. The Washburn Observatory possessed a 15-inch refractor, somewhat larger than his old Illinois telescope, and Stebbins applied his photoelectric techniques to an expanding program of stellar photometry. His measurements of eclipsing binaries grew ever more precise, revealing subtle features in their light curves that corresponded to effects like limb darkening, wherein the edges of a stellar disk appear slightly fainter than the center due to the geometry of the stellar atmosphere, and the reflection effect, wherein the heated face of one star appears brighter than its cooler far side. It was at Washburn that Stebbins began his long and productive collaboration with Albert Edward Whitford, a younger physicist who arrived in 1931 and who possessed precisely the technical skills needed to advance photoelectric photometry into its next phase. Whitford was trained in electronics and vacuum tube technology, the emerging fields that were transforming communication and instrumentation throughout the 1930s, and he applied this expertise to the design of more sensitive and stable amplifiers for astronomical photometry. Together, Stebbins and Whitford developed photoelectric photometers of unprecedented precision, instruments that could detect changes in stellar brightness of less than 1/100th of a magnitude under favorable conditions. To appreciate what this precision meant, consider that visual observers working carefully with comparison sequences could achieve estimates accurate to perhaps 1/10th of a magnitude, and even this level of accuracy required extensive training and favorable observing conditions. The photoelectric methods of Stebbins and Whitford represented an improvement by at least a factor of 10, opening a new domain of subtle stellar variation that had been completely inaccessible to visual observation. Stars that appeared perfectly constant to the eye were revealed as gentle variables, pulsating with amplitudes of only a few hundredths of a magnitude, and the light curves of already known variables were mapped with a smoothness and detail that allowed meaningful comparison with theoretical models of stellar structure and pulsation. The Stebbins-Whitford collaboration proved enormously productive through the 1930s and 40s, with the pair making fundamental contributions not only to variable star photometry but also to the measurement of interstellar reddening, the color excess imposed on starlight by its passage through the dusty medium between the stars. Their measurements of stellar colors, using photoelectric cells with different spectral sensitivities, provided essential data for understanding how dust grains scatter and absorb light of different wavelengths, work that would prove crucial for later studies of galactic structure and the cosmic distance scale. Yet even as Stebbins and Whitford achieved their successes, a new detector technology was emerging that would surpass the simple photoelectric cell in sensitivity by an enormous margin. This was the photomultiplier tube, an ingenious device that amplified the tiny electron current from a photosensitive surface through a cascade of secondary emissions. In a photomultiplier, electrons knocked free by incident light are accelerated toward a series of electrodes called dynodes, each held at a progressively higher voltage than the last, and when an electron strikes a dynode, it liberates several additional electrons, which are in turn accelerated to the next dynode to liberate still more, so that a single photoelectron at the input can produce millions of electrons at the output, an amplification sufficient to detect individual quanta of light arriving one by one from a distant star. The development of practical photomultiplier tubes during the late 1930s, driven largely by applications in nuclear physics and military technology, provided astronomers with a detector of remarkable capability, and among the first to exploit this technology for variable star observation was Gerald Edward Crone at the Lick Observatory in California. Crone began his photomultiplier work in the early 1940s, and his careful development of photomultiplier photometry established techniques and standards that would dominate stellar photometry for the next several decades. The sensitivity of photomultiplier detectors allowed observations of much fainter stars than had been accessible to earlier photoelectric methods, extending precision photometry from the relatively bright stars that Stebbins had studied to the remote and faint objects that increasingly occupied astronomical attention. Crone's work at Lick included extensive studies of eclipsing binary stars, continuing the tradition that Stebbins had established, but with photomultiplier precision that revealed ever subtler details in their light curves. He also developed important techniques for calibrating photomultiplier photometers and for correcting the various instrumental effects that could compromise the accuracy of measurements. The extreme sensitivity of photomultiplier tubes brought new challenges as well as new capabilities, since the detectors were sensitive to cosmic rays, radioactive decay in the glass envelope, and thermal emission of electrons from the photocathode, all of which contributed unwanted signals that had to be carefully measured and removed. One persistent difficulty that affected all photometric observations, whether visual, photographic, or photoelectric, was the absorption and scattering of starlight by Earth's atmosphere, an effect known as atmospheric extinction. When a star is high overhead, its light passes through a minimum thickness of air, but as the star approaches the horizon, the light must traverse an increasingly long path through the atmosphere, and more of it is absorbed or scattered away before reaching the telescope. This effect depends on wavelength, being stronger for blue light than for red, and it varies from night to night with changes in atmospheric humidity, dust content, and temperature structure. For photometry to achieve its full potential precision, these atmospheric effects had to be carefully measured and removed from the observations. The technique developed to address atmospheric extinction involved observing standard stars of known brightness at various elevations throughout the night and using these observations to determine the extinction coefficient, a number that characterizes how much light is lost per unit air mass traversed. Once this coefficient was established for a given night, it could be applied to correct all the other observations made during that night, bringing them to what they would have been if observed from above the atmosphere entirely. This procedure required considerable additional telescope time devoted to extinction standards rather than to the variable stars themselves, and it assumed that the extinction remained constant throughout the night, an assumption that was not always valid. A more elegant solution, particularly for variable star observation, was the technique known as differential photometry, in which the variable star was measured not in absolute terms but in comparison to one or more nearby stars of constant brightness observed through the same air path and during the same moments. If the comparison stars were truly constant and were close enough on the sky that they experienced essentially the same atmospheric extinction as the variable, then the ratio of their brightnesses would be independent of atmospheric effects, and any changes in this ratio could be attributed to genuine variation of the target star. This differential approach, which echoed in spirit the visual comparison methods that observers like Argelander had championed, proved extraordinarily powerful for detecting small variations, since many sources of error that affected both stars equally simply cancelled out in the comparison. The quest for precision and standardization in photoelectric photometry culminated in the early 1950s with the development of the UBV photometric system by Harold Lester Johnson and William Wilson Morgan, both working at Yankees Observatory. Johnson and Morgan recognized that the proliferation of different photoelectric systems, each with its own filters and photocathode sensitivities, was making it increasingly difficult to compare measurements from different observatories or to combine observations into coherent datasets. What was needed was a carefully defined standard system that other observers could reproduce, along with a network of standard stars whose magnitudes in this system were precisely established. The UBV system, published in 1953, defined three broad passbands for stellar photometry, designated U for ultraviolet, B for blue, and V for visual, each specified by the combination of colored glass filter and photomultiplier response that an observer should use. Johnson and Morgan established a set of primary standard stars, carefully chosen for constancy and for their distribution across the sky, and they measured these standards with great precision to provide the foundation on which all other UBV observations would rest. The system was designed to be reproducible, so that an observer in Chile or Australia or South Africa could assemble the specified filters and photomultiplier and, after carefully calibrating against the standard stars, could make measurements directly comparable to those made anywhere else in the world. The establishment of the UBV system represented a kind of maturation of photoelectric photometry, the transformation from a specialized technique practiced by a few pioneering groups into a standardized methodology accessible to the broader astronomical community. Within a few years, UBV photometry had become the common currency of stellar observation, and the accumulating body of standardized measurements opened new possibilities for studying variable stars on a systematic basis. The precision of photoelectric methods revealed an entire population of variable stars whose variations had been invisible to visual observers. stars with amplitudes of only a few hundredths of a magnitude, fluctuations completely lost in the noise of visual estimates, now stood out clearly in photoelectric light curves. Among the discoveries enabled by this new precision were the subtle variations of certain hot blue stars that came to be known as beta Cephei variables, the tiny oscillations of the Sun-like stars that presaged the later field of astroseismology, and the complex small-amplitude variations of certain peculiar stars that defied easy classification. For the classical variable stars that had been studied visually for decades or even centuries, photoelectric photometry provided a new level of detail that enabled meaningful tests of theoretical models. The precise shape of a Cepheid light curve, the exact depth and duration of eclipses in a binary system, the phase relationships between brightness and color variations. All of these details carried information about the physical processes occurring within these stars, information that could only be extracted when the observations achieved sufficient precision to constrain the models. And so, as we approach the middle of the 20th century, we find variable star observation transformed from an enterprise dependent on the trained human eye to one relying on the electronic eye of the photomultiplier. From measurements uncertain by tenths of a magnitude to determinations precise to hundredths or better. From isolated observations made according to individual conventions to standardized photometry conducted within a common international system. The patient work of Stebbins with his selenium cell, the technical innovations of Whitford, the photomultiplier refinements of Crone, and the systematization achieved by Johnson and Morgan. All of these contributions accumulated gradually over nearly half a century to effect this quiet revolution. The stars themselves, of course, continued their variations as they always had, indifferent to the improvements in how humans perceived and measured their light. But the picture of stellar variability that astronomers could construct from their observations had become immeasurably richer and more detailed. Among the many varieties of variable stars that 19th and 20th century astronomers catalogued and studied, there exists a particularly fascinating group whose members undergo sudden and sometimes violent increases in brightness, flaring up from relative obscurity to prominence before slowly fading back toward their original dimness. And these stars, which include the classical novae, the dwarf novae, and various related systems now gathered under the broader heading of cataclysmic variables, would eventually reveal themselves to be not single stars at all, but rather close binary systems in which matter flows from one star to another, producing the dramatic outbursts that first drew observers' attention to them, though understanding this would require many decades of patient observation, careful spectroscopy, and the gradual development of theoretical frameworks capable of explaining such unusual behavior. The word nova itself comes from the Latin for new, and it reflects the ancient perception that these objects represented new stars appearing suddenly in the heavens where none had been visible before. Though of course we now understand that novae are not new stars being born, but rather existing stars undergoing temporary but extreme increases in luminosity, brightening by factors of thousands or even hundreds of thousands before gradually declining over weeks or months or sometimes years. And while novae had been recorded since antiquity, with Chinese astronomers documenting several guest stars that modern analysis suggests were likely nova events, the systematic study of these objects and the recognition that they constituted a distinct class of stellar phenomenon belongs primarily to the period we are considering, when improvements in telescopes and the advent of spectroscopy allowed astronomers to examine these strange visitors with unprecedented precision. Before we discuss the novae proper, however, it is worth spending some time with their gentler cousins, the dwarf novae, which undergo smaller but more frequent outbursts and which proved somewhat easier to study precisely because they repeated their performances on timescales measured in weeks or months rather than centuries, allowing observers to accumulate substantial records of their behavior within a single human lifetime. And the prototype of this class, the star that would eventually lend its name to the U Geminorum type of dwarf novae, was discovered to be variable in 1855 by the English astronomer John Russell Hind, who had already made a name for himself as a diligent observer and discoverer of minor planets before turning his attention to variable stars. Hind noticed that a star in the constellation Gemini, normally invisible or barely visible in small telescopes at around 13th magnitude, had brightened considerably, reaching approximately 9th magnitude, and he recognized that this represented a substantial increase in the star's light output, though he could not have known at the time what mechanism might be responsible for such behavior, and subsequent observations by Hind and others revealed that U Geminorum repeated these outbursts at somewhat irregular intervals averaging roughly 100 days, rising over the course of a day or two to its maximum brightness and then declining more gradually over a week or two back to its quiescent state. And this pattern of rapid rise followed by slower decline, occurring quasi-periodically but not with clockwork regularity, would come to define the dwarf nova class of variables. The discovery of U Geminorum's variability opened a new area of investigation, though for several decades it remained something of a curiosity, a single example of unusual stellar behavior that defied easy explanation, and it was not until 1896 that another dwarf nova was recognized, this time through the systematic examination of photographic plates at Harvard College Observatory, where the great project of cataloging stellar spectra and monitoring stellar brightnesses was well underway, employing the talents of numerous skilled women who examined plates, measured positions and magnitudes, and made discoveries that would reshape our understanding of the stellar universe. Among these remarkable individuals was Louisa Wells, who in 1896 identified the variable nature of a star in the constellation Cygnus that would become known as SS Cygni, and her discovery came not through serendipitous observation of a single outburst but through the careful comparison of photographic plates taken at different times, which revealed that this star underwent periodic brightenings similar to those of U Geminorum, rising from its normal 12th magnitude to roughly 8th magnitude and then fading back again over a period of 1 to 2 weeks, with the cycle repeating on average every 50 days or so, though like U Geminorum the intervals between outbursts showed considerable variation, sometimes occurring as frequently as every 30 days and sometimes waiting as long as several months between eruptions. Wells's discovery of SS Cygni was particularly significant because the star's relative brightness compared to U Geminorum made it more accessible to detailed study, and its somewhat shorter average cycle meant that observers could accumulate data more quickly, building up records of many outbursts within just a few years. And SS Cygni would go on to become one of the most intensively observed variable stars in history, with visual observers and later photoelectric photometrists and then digital detectors accumulating an extraordinarily detailed record of its behavior spanning well over a century, making it an invaluable laboratory for testing theories of dwarf nova outbursts. The recognition that U Geminorum and SS Cygni represented examples of a distinct class of variable star, rather than isolated curiosities, was an important conceptual step, and as more dwarf novae were discovered in subsequent years, astronomers began to search for common properties that might illuminate the underlying cause of their outbursts, noting for instance that all dwarf novae appeared to be relatively nearby stars, since even at maximum brightness they remained fairly faint, and that their spectra, when they could be obtained, showed unusual features that set them apart from ordinary stars. Alongside the dwarf novae, the classical novae continued to appear from time to time, their much more dramatic outbursts making them easier to discover even without systematic photographic monitoring, since a star that brightens by factors of tens of thousands can hardly escape notice even to casual observers of the night sky. And each new nova provided opportunities for spectroscopic study that gradually revealed the complex and sometimes puzzling nature of these events, showing for instance that the brightening was accompanied by the ejection of material at high velocities, with spectral lines displaying the characteristic broadening and splitting that indicated expanding shells of gas, and that the subsequent fading often occurred in stages, with the spectrum evolving through several distinct phases before the star returned to something resembling its pre-outburst state. One particularly instructive nova appeared in 1891 in the constellation Auriga, designated T Aurigui, which brightened sufficiently to become visible to the unaided eye before fading over subsequent months, and spectroscopic observations during and after the outburst provided valuable data on the nova process. But what made T Aurigui especially significant was what happened after the nova had faded and the star had returned to its quiescent state. For continued monitoring revealed that this faint star was an eclipsing binary, with its light curve showing the characteristic periodic dips that indicated one star passing in front of another as seen from Earth. The discovery that T Aurigui was a binary system was deeply suggestive, hinting that the nova outburst might somehow be connected to the presence of a companion star, though the exact nature of this connection remained unclear for many years, and similar observations of other old novae, as they were called, gradually accumulated evidence that binary status was not a coincidental property of these systems, but rather an essential feature, somehow integral to the mechanism that produced the outburst. And this realization, which developed slowly through the first half of the 20th century, would eventually revolutionize our understanding of novae and related phenomena. The key to unlocking the secrets of dwarf novae came through spectroscopic observation, which by the 1940s and 1950s had advanced to the point where the velocities of stars in binary systems could be measured with considerable precision through the Doppler shifts of their spectral lines. And in 1954, the American astronomers Alfred Harrison Joy and Milton Humason published the results of their detailed spectroscopic study of SS Cygni, demonstrating conclusively that this prototype dwarf nova was indeed a close binary system, with two stars orbiting their common center of mass in a period of just over 6 hours. Joy and Humason's work revealed not only that SS Cygni was binary but also provided clues about the nature of its components, showing through the analysis of spectral line velocities that one star was considerably more massive than the other despite being much fainter, suggesting that the unseen massive component was a compact star of some kind, highly condensed and therefore emitting relatively little light despite its substantial mass. And this finding aligned well with emerging theoretical ideas about white dwarf stars, the dense stellar remnants that result when stars like our Sun exhaust their nuclear fuel and collapse to objects roughly the size of Earth but containing roughly the mass of the Sun. The recognition that SS Cygni and by extension other dwarf novae contained white dwarf stars was a crucial step toward understanding the outburst mechanism, for it suggested a scenario in which the white dwarf might be accreting material from its close companion, drawing matter from the outer layers of the larger star through gravitational attraction, and this accreted material, spiraling inward toward the white dwarf surface, might under certain conditions undergo sudden releases of energy that would produce the observed brightening, a picture that subsequent theoretical work would refine and elaborate into the modern understanding of dwarf nova outbursts as instabilities in the accretion disks that form around white dwarfs in these systems. The same basic picture, involving a white dwarf accreting matter from a companion star, would prove capable of explaining classical novae as well, though with an important difference in the mechanism of the outburst. For while dwarf nova eruptions originate in the accretion disk itself, classical nova explosions occur on the surface of the white dwarf, where accumulated hydrogen-rich material from the companion eventually reaches temperatures and pressures sufficient to ignite thermonuclear fusion, producing a runaway reaction that blasts the outer layers into space while temporarily increasing the star's luminosity by enormous factors. And the much greater violence of this process explains why classical novae are so much more luminous than dwarf novae and why they occur much less frequently in any given system, since a substantial amount of material must accumulate before the conditions for ignition are met. Among the strangest members of the cataclysmic variable family are the recurrent novae, systems that have been observed to undergo multiple nova outbursts within historical times. And these objects posed a particular puzzle for astronomers because the intervals between their eruptions, while long by human standards, were far too short to be compatible with the standard picture of classical novae, which suggested that centuries or millennia should elapse between successive outbursts as material slowly accumulated on the white dwarf surface. And yet here were stars that had been seen to explode twice or even more times within a single human lifetime. The most famous recurrent nova is T Coronii Borealis, sometimes called the Blaze Star, which underwent recorded outbursts in 1866 and again in 1946, separated by an interval of 80 years. And in each case the star rose from its normal 10th magnitude to approximately 2nd magnitude, becoming one of the brightest stars in the northern constellation Corona Borealis, clearly visible to the unaided eye, before fading back over subsequent weeks to its quiescent state. And the 1946 outburst, occurring in an era of more advanced instrumentation, allowed astronomers to gather detailed spectroscopic and photometric data that revealed the remarkable complexity of this system. T Coronii Borealis is not a typical cataclysmic variable with a main sequence companion, but rather belongs to a subclass sometimes called symbiotic stars, in which the mass-donating companion is a red giant, a highly evolved star of large radius and relatively low surface temperature that loses mass readily through stellar winds, providing a copious supply of material for accretion onto the white dwarf. And this high rate of mass transfer helps explain the relatively short interval between outbursts, since the white dwarf can accumulate the necessary trigger mass in decades rather than millennia. Another well-known recurrent nova is Rs Cepheid, which has been observed in outburst in 1898, 1933, 1958, 1967, 1985, and again in 2006, though of course this last event falls outside our period of consideration, and the relatively frequent recurrence of these outbursts has made Rs Cepheid a valuable laboratory for studying the nova phenomenon, allowing astronomers to observe multiple eruptions with progressively improving instrumentation and to test theoretical predictions about how such systems should behave. The theoretical framework for understanding recurrent novae developed gradually through the 1930s and 1940s, building on the growing recognition that novae of all types involved binary stars and white dwarfs, and theorists realized that the recurrence time between nova outbursts should depend on several factors, including the mass of the white dwarf, the rate at which material is being transferred from the companion, and the composition of the accreted material, with more massive white dwarfs requiring less accumulated mass to reach ignition conditions and thus being capable of more frequent eruptions, and with higher mass transfer rates similarly shortening the interval between outbursts. The symbiotic stars, of which T Coronii Borealis is one example, represent a particularly interesting subgroup of interacting binary systems, characterized by spectra that combine features of cool red giant stars with indicators of much higher excitation, such as emission lines of highly ionized elements that require temperatures far exceeding anything a red giant could produce. And this puzzling combination of hot and cold signatures led to the name symbiotic, suggesting a kind of biological analogy in which two very different organisms live together in close association. Though of course the actual explanation is simply that we are seeing light from two very different sources, the cool red giant and the hot region surrounding its compact companion. One particularly remarkable symbiotic star is our Aquarii, which combines a Mira-type pulsating red giant with a hot companion, probably a white dwarf, and which has been known to show unusual variations since the 19th century, including episodes of brightening that may represent symbiotic nova outbursts. And what makes our Aquarii especially noteworthy is that photographic observations beginning in the 1940s revealed an extended structure of gaseous jets and nebulosity surrounding the central binary, apparently produced by episodic ejections of material from the system, making our Aquarii one of the first stellar systems in which such jet structures were clearly documented. The jets of our Aquarii, photographed with increasing clarity as photographic techniques improved through the mid-20th century, represented a phenomenon that would later be recognized as relatively common in accreting binary systems, where the combination of rotation, magnetic fields, and the dynamics of accretion disks can channel material into narrow outflows perpendicular to the disk plane, producing the elongated structures that modern observations have revealed in systems ranging from young stars still forming from their natal clouds to supermassive black holes at the centers of active galaxies. And our Aquarii thus provided an early glimpse of physical processes that would prove to have very broad applicability across many different types of astronomical objects. By the end of the period we are considering, roughly 1950, the basic picture of cataclysmic variables had begun to emerge, though many details remained to be worked out and some would require decades of additional observation and theoretical development. But astronomers had recognized that these dramatic variable stars were binary systems, that they involved white dwarfs secreting material from companion stars, that the outbursts arose from instabilities either in the accretion disk or in the accumulated material on the white dwarf surface, and that the spectacular diversity of cataclysmic variable behavior, from the mild frequent eruptions of dwarf novae to the violent rare explosions of classical novae to the puzzling intermediate cases of recurrent novae, could all be understood as variations on this single underlying theme, with the specific behavior of any particular system depending on the properties of its components and the rate at which mass was being transferred between them. This recognition of cataclysmic variables as interacting binary systems represented one of the great conceptual advances of 20th century stellar astronomy, connecting what had seemed to be separate and puzzling phenomena into a unified framework and demonstrating once again that the careful accumulation of observational data, combined with thoughtful theoretical analysis, could reveal the underlying simplicity hidden within apparent complexity. And the dwarf novae and symbiotic stars continue to be studied today, their behavior monitored by observers around the world, their physics probed by ever more sophisticated instruments, building on the foundation laid by those patient astronomers who first noticed these stars' changing brightness and who devoted their careers to understanding why. And so we come now to a particular family of variable stars, the Mira variables, named for their prototype, a star that has been watched and measured for more than 3 centuries, a star whose very name means wonderful in Latin, though its behavior, once you come to understand it, follows patterns that are more methodical than miraculous, more patient than astonishing, the slow breathing of an elderly star in the late stages of its long life. The prototype of this class, Mira itself, also designated Omicron Cephei, sits in the constellation of Cetus, the whale, and it was the first periodic variable star recognized as such in the historical record, observed by the Frisian astronomer Johannes Holwarder in 1638 and studied intermittently in the decades that followed, though it would take many generations of observers before the full character of its variation became clear, before the numbers accumulated into the kind of statistical picture that allows astronomers to speak with confidence about what such a star is doing and why. By the middle of the 20th century, after some 300 years of recorded observations, the behavior of Mira was well documented, and the numbers themselves are worth knowing, not because they are dramatic but because they are so characteristic of this entire class of stars, so representative of what happens when a red giant star pulsates over many months in a rhythm that is regular enough to be called periodic but variable enough to keep observers attentive and humble. The period of Mira, meaning the time from one maximum brightness to the next, averages approximately 332 days, which is to say nearly 11 months, so that if you see Mira at its brightest in January of one year, you might expect to see it bright again in December, and then in November of the following year, and so on, the maxima slowly drifting backward through the calendar, taking roughly a decade to complete a full cycle through all the seasons, a leisurely progression that rewards patient observers who return to the same star year after year. The magnitude range of Mira is considerable, varying from about 2.0 at its brightest to approximately 10.1 at its faintest, which represents a change of more than 8 magnitudes. And because the magnitude scale is logarithmic, this means that Mira becomes roughly 1,500 times brighter at maximum than at minimum, a range so large that when the star is bright it is easily visible to anyone looking up at the constellation of Cetus on a clear evening, one of the brighter stars in that part of the sky, and yet when it is faint it disappears entirely from unaided view, requiring binoculars or a small telescope to be seen at all. And this appearing and disappearing, this coming and going over the months, is what first attracted the attention of observers centuries ago and what continues to make Mira variables such satisfying objects for visual astronomers, who can follow the entire cycle without any equipment more sophisticated than their own eyes and a good star chart. The study of Mira variables accelerated greatly in the early 20th century through the organized efforts of amateur observers coordinated by professional astronomers, and in this collaboration the American Association of Variable Star Observers, founded in 1911, played a central role, collecting brightness estimates from observers across North America and eventually around the world, compiling these individual measurements into continuous light curves that spanned decades, far longer than any single professional observatory could dedicate to watching a single slowly varying star. At Harvard College Observatory, the astronomer Leon Campbell devoted much of his career to the analysis of these accumulated observations, working with records that numbered in the tens of thousands for individual stars, patient compilations of visual estimates made by hundreds of different observers under varying conditions, and from these somewhat heterogeneous data Campbell and his colleagues extracted the underlying patterns, averaging out the scatter introduced by different observers and different atmospheric conditions, revealing the true behavior of the stars beneath the noise. Campbell's work on Mira variables extended from the 1910s through the 1940s, and he became one of the world's leading authorities on these slowly pulsating red giants, publishing extensively on their periods, their light curve shapes, and the subtle changes that accumulated over many cycles. and his careful statistical treatment of the AAVSO data demonstrated that useful scientific conclusions could be drawn from amateur observations when those observations were numerous enough and systematic enough to overcome their individual limitations. One of the significant accomplishments concerning Mira variables by the mid-20th century was the establishment of a period-luminosity relation for these stars. Similar in principle to the relation that Henrietta Leavitt had discovered for Cepheid variables, but different in its details and applicable to a distinct population of stars at a different stage of stellar evolution. The period-luminosity relation for Cepheids, as you may recall from our earlier discussion, shows that Cepheids with longer periods are intrinsically more luminous. And this relation is tight enough and well calibrated enough to serve as a distance indicator for galaxies millions of light-years away, one of the foundational tools of extragalactic astronomy. But the Cepheid relation applies to relatively young, massive stars pulsating in a particular way, and it does not extend to the older, cooler, larger Mira variables. The period-luminosity relation for Miras was established through statistical methods applied to large samples of these stars. Using observations of Miras in globular clusters and in the Magellanic Clouds where all the stars in a given sample could be assumed to lie at roughly the same distance. And the relation that emerged showed that longer-period Miras are indeed more luminous on average, though the scatter around the relation is greater than for Cepheids, making Miras somewhat less precise as distance indicators but still useful, particularly for studying older stellar populations where Cepheids are absent. The infrared luminosity of Mira variables proved to be a better indicator than their visual brightness for calibrating this relation, because much of the light emitted by these cool red giants emerges at infrared wavelengths, and their visual brightness is strongly affected by molecular absorption bands that vary in strength as the star pulsates, making the visual light curve less directly connected to the star's total energy output than the infrared light curve. And this realization came somewhat later, as infrared astronomy developed in the second half of the 20th century. But the groundwork for the period-luminosity relation was laid in the earlier decades through careful visual observation and statistical analysis. Beyond their brightness variations, Mira variables display distinctive spectral characteristics that set them apart from other types of variable stars and that reveal the physical conditions in their extended, cool atmospheres. And these spectral peculiarities were studied intensively in the early 20th century as spectroscopic techniques improved and as astronomers sought to understand not merely how these stars varied but why. The most prominent spectral features of Mira variables are the strong absorption bands of titanium oxide, written in chemical notation as TO, dark bands that dominate the red and near-infrared portions of the spectrum and that indicate surface temperatures cool enough for this molecule to form and persist, temperatures typically between 2000 and 3000 Kelvin, far cooler than the Sun's surface temperature of about 5800 Kelvin, and these TO bands are what give Mira variables their characteristic deep red color, a color that becomes more pronounced as the star fades toward minimum and its temperature drops further. The American astronomer Alfred Harrison Joy, working at Mount Wilson Observatory in the 1920s, made detailed spectroscopic studies of Mira variables and discovered that these stars display emission lines in their spectra, bright lines indicating hot gas, that appear near the time of maximum light and fade away as the star dims, a finding that was initially puzzling because one might expect a star growing brighter to simply show stronger absorption features rather than emission, and yet the emission lines were unmistakable. Most notably the hydrogen-Balmer lines but also lines of various metals. Joy interpreted these emission features as evidence that shock waves were propagating through the extended atmospheres of Mira variables, generated by the pulsation of the underlying star, And as these shock waves moved outward through the cool atmospheric layers, they heated the gas locally to temperatures high enough to produce emission, creating a temporary zone of excited atoms that radiated brightly before cooling again. And this interpretation connected the spectroscopic observations to the physical mechanism of pulsation in a satisfying way, showing that Mira variables were not simply swelling and shrinking passively but were actively driving energy outward through their atmospheres in periodic pulses. The extended atmospheres of Mira variables are not merely zones of varying temperature and excitation, but are also regions of active mass loss, where material from the star is gradually shed into space, building up circumstellar shells of gas and dust that surround the star and that eventually dissipate into the interstellar medium, enriching it with the products of nuclear fusion that occurred in the stellar interior. This mass loss was inferred from various lines of evidence accumulating through the mid-20th century, including the presence of emission features that persisted even when the star was near minimum light, suggesting a permanent shell of excited gas beyond the photosphere, and the detection of infrared excess in the spectral energy distributions of many Mira variables, indicating the presence of warm dust grains surrounding the star and absorbing some of its light. And later, with the development of radio astronomy, the detection of molecular emission lines from circumstellar shells at considerable distances from the stellar surface. But these radio and infrared observations came largely after 1950 and so represent the continuation of a story whose foundations were laid in the earlier period of visual and photographic observation. The periods of Mira variables, while regular enough to be called periodic, are not fixed with the precision of a mechanical clock, and one of the interesting discoveries that emerged from the long-term monitoring of these stars was that their periods could change over time, sometimes gradually drifting in one direction or another, sometimes wandering back and forth in what came to be called period meandering, and these secular period changes provided clues about the internal structure and evolution of the stars themselves. The star Hydrae, a Mira variable in the constellation of Hydra the water snake, became a classic example of this phenomenon, having been observed since the late 17th century, making it one of the longest monitored variable stars known. And over the course of nearly 3 centuries its period was observed to decrease substantially, from approximately 495 days in the early records to about 390 days by the mid-20th century, a change of more than 100 days, more than 20%, a steady shrinkage that implied something was changing in the structure of the star, perhaps its radius or its mean density, though the exact physical mechanism remained a subject of investigation. Other Mira variables showed period increases rather than decreases, and still others showed irregular fluctuations that defied simple trends. And this variability in the periods themselves added a layer of complexity to the study of these stars, requiring that period determinations be continually updated and that predictions of future maxima be treated with appropriate caution. And it provided motivation for maintaining long-term monitoring programs that could track these slow changes over many decades. For visual observers, the changing periods of Mira variables presented a practical challenge, because predicting when a given star would reach maximum brightness required knowing its current period. And if that period was shifting by days or weeks from one cycle to the next, predictions made years in advance could be substantially in error, and observers had to remain flexible, watching for the beginning of a rise toward maximum rather than relying too heavily on predicted dates. And in this way the scientific uncertainty translated into observational alertness, keeping the observers engaged rather than merely mechanical. Beyond the true Mira variables with their reasonably well-defined periods, there exists a broader category of pulsating red giants known as semiregular variables. Stars that show brightness variations with characteristic timescales but without the regularity that would allow precise period determinations. Stars that seem to hesitate and wander in their cycles, sometimes brightening on schedule and sometimes not. And these semi-regular variables include some of the most famous and visually prominent red giant stars in the sky. Betelgeuse, the bright red star marking the shoulder of Orion, is perhaps the best known of these semi-regular variables. A red supergiant of immense size whose variations have been followed by observers for well over a century. And yet, despite all this observation, its behavior remains difficult to predict, with brightness changes that seem to follow multiple overlapping cycles of different lengths, around 400 days and around 2,100 days and perhaps others. Cycles that interfere with each other in complex ways, so that the light curve of Betelgeuse is never quite the same from one year to the next, and predictions of its brightness at any future date carry substantial uncertainty. The semi-regular variables as a class include stars of various luminosities and temperatures, not all of them as extreme as Betelgeuse, and their light curves range from nearly periodic to essentially irregular, forming a continuum of behavior rather than a sharply defined category. And astronomers in the early 20th century devoted considerable effort to classifying these stars and to searching for underlying regularities in their variations, with partial success, identifying subgroups with different typical periods and amplitudes, but never achieving the clean predictability that characterizes the Cepheids or even the true Miras. The physical explanation for the semi-regular behavior of these stars involves the same basic mechanism as for the Miras, the pulsation of an extended stellar envelope. But in the semi-regular variables, the pulsation seems to be less coherent, perhaps involving multiple modes of oscillation occurring simultaneously, or perhaps modulated by convective motions in the stellar atmosphere that introduce irregularity into what would otherwise be a regular pulsation. And disentangling these effects required theoretical models of stellar structure and pulsation that were still being developed in the mid-20th century and that would continue to be refined in subsequent decades. For the patient observer, whether professional or amateur, the Mira variables and their semi-regular cousins offered a particular kind of satisfaction, the pleasure of following a slow drama that unfolded over months and years. A drama without surprises in the theatrical sense but full of subtle variations and gradual changes. Stars that rewarded attention and punished inattention. Stars whose behavior could only be understood through the accumulation of many observations over long periods of time. The light curves that resulted from this patient accumulation, the graphs showing brightness plotted against time for individual stars over decades, became objects of scientific value in themselves, repositories of information about stellar pulsation and evolution that could be mined again and again as theoretical understanding advanced, as new questions were formulated, as new methods of analysis were developed. And the observers who contributed to these light curves, most of them amateurs working in their own backyards with modest equipment, became participants in a scientific enterprise larger and longer lasting than any individual career. By the middle of the 20th century, the accumulated knowledge of Mira-type variables represented one of the triumphs of systematic observational astronomy, a body of data built up through the cooperation of hundreds of observers over many decades, analyzed with increasingly sophisticated statistical methods, interpreted in terms of stellar pulsation theory that was itself being developed and refined, and applied to questions of stellar evolution and cosmic distance determination that reached far beyond the individual stars themselves. The breathing of these stellar giants, the slow expansion and contraction that drives their brightness variations, the shock waves propagating through their extended atmospheres, the mass loss carrying processed material out into space, All of this came gradually into focus through the patient work of observers and theorists working together. And the picture that emerged was not dramatic in the way that novae or eclipsing binaries might be dramatic, but it was deeply satisfying in its coherence, in the way that disparate observations came together to reveal a physical process operating on timescales far longer than a human lifetime. And so we might pause here for a moment, imagining one of these great red stars, Mira perhaps, hanging in the darkness of its constellation, surrounded by the faint shell of gas and dust that it has shed over the millennia, pulsating slowly in and out over the course of nearly a year, its surface temperature rising and falling by hundreds of degrees, its brightness waxing and waning by a factor of more than 1,000, doing all of this in silence, in the vacuum of space, watched over the centuries by generation after generation of observers who recorded its brightness in their notebooks and logbooks, who compared it to the nearby stars and estimated its magnitude, who sent their observations to central clearinghouses where the numbers were compiled and averaged and plotted, building up the long record that tells us what we know about these slowly breathing stellar giants. And so we turn our attention now to the southern half of our world, where different stars will overhead through the long hours of darkness, and where patient observers have contributed their own essential chapters to the history of variable star study. For much of the history of astronomy, the southern skies remained less thoroughly charted than their northern counterparts, simply because the great observatories of Europe and later North America were situated above the equator, and the stars that never rose above their horizons remained mysteries waiting to be catalogued and understood. The development of variable star observation in the southern hemisphere is a story of determination, of long journeys undertaken in the name of science, and of the gradual weaving together of observations from opposite ends of the Earth into a single coherent understanding of how stars behave across time. The night sky appears rather different when one stands in Peru or South Africa or Australia than it does from Massachusetts or Germany. The familiar constellations of the northern sky sink toward the horizon or disappear entirely, while new patterns rise into prominence, patterns that northern observers might never see at all. The Southern Cross turns about the south celestial pole, and the Magellanic Clouds hang like detached fragments of the Milky Way, visible to the unaided eye as pale luminous patches against the darkness. These southern treasures, as we shall see, would prove to contain variable stars of extraordinary importance, stars whose behavior would eventually reshape our understanding of the scale of the universe itself. But first, observatories had to be established, telescopes had to be mounted and aligned beneath unfamiliar skies, and the patient work of recording stellar brightnesses had to begin in earnest in lands far removed from the traditional centers of astronomical research. The Harvard College Observatory, under the energetic direction of Edward Charles Pickering, recognized early that a comprehensive survey of the heavens could not be accomplished from Cambridge, Massachusetts alone. The stars of the southern sky demanded their own systematic study, and so Pickering conceived of establishing a southern station that would extend Harvard's photographic survey to encompass the entire celestial sphere. After some initial experiments and expeditions, the observatory selected a site in Peru, in the high clear air near the city of Arequipa, where the seeing conditions were often remarkably steady and the altitude helped to reduce the blurring effects of the lower atmosphere. This southern outpost, known as Boyden Station, was established in 1889, and its direction was entrusted to Solan Irving Bailey, a careful and methodical astronomer whose work would prove invaluable to the study of variable stars in the decades that followed. Bailey arrived in Arequipa with the mission of photographing the southern skies and cataloguing the stars that could not be adequately studied from the northern hemisphere. The station was situated at an elevation of approximately 8,000 feet, and the conditions there, while excellent for observing, presented certain challenges of their own. The remoteness of the location meant that equipment had to be transported great distances, and communication with Cambridge required patience, as letters crossed the equator by ship and took weeks to arrive. Nevertheless, Bailey and his small staff set about their work with quiet determination, exposing photographic plates night after night and building up an archive of images that would eventually allow the brightness variations of countless southern stars to be detected and measured. It was through the systematic examination of these plates that Bailey made one of his most significant contributions to variable star astronomy. He undertook a comprehensive study of the globular clusters visible from the southern station, those ancient spherical gatherings of stars that orbit our galaxy like satellites. Within these clusters, Bailey discovered large numbers of variable stars, many of them belonging to the class now known as Lyrae variables after the prototype star in the northern constellation Lyra. These stars pulsate with periods typically less than a day, brightening and fading in regular cycles, and their presence in globular clusters by the hundreds provided important clues about the nature and distances of these remote stellar systems. Bailey's patient cataloguing of cluster variables demonstrated the value of the southern station and justified the considerable effort required to maintain such a distant outpost. The photographic plates accumulated in Arequipa were shipped back to Cambridge, where they joined the growing archive that would eventually be examined by Williamina Fleming, Annie Jump Cannon, Henrietta Leavitt, and the other women who formed the Harvard computing staff. It was from this mingling of northern and southern observations that a truly global picture of stellar variability began to emerge. The southern plates proved particularly rich in discoveries, for they captured regions of the sky that had received far less attention than the northern constellations, and variable stars that had escaped notice for centuries now revealed themselves through the comparison of plates taken on different nights. Boyden Station continued its work in Arequipa for nearly 4 decades, but changing circumstances eventually prompted a relocation. By the 1920s, the growth of the city and the increasing presence of artificial lighting had begun to compromise the darkness of the observing site, and the Harvard Observatory began to consider alternative locations. In 1927, the station was moved to South Africa, to a site near Bloemfontein that offered excellent conditions and continued access to the southern sky. There the work begun in Peru continued, with new generations of photographic plates capturing the slow and subtle changes of distant suns. Meanwhile, other institutions had been contributing to the study of southern variable stars from their own vantage points. The Royal Observatory at the Cape of Good Hope, established in 1820 under the direction of the British Admiralty, represented one of the earliest permanent astronomical installations in the Southern Hemisphere. Its primary mission was the determination of accurate stellar positions for the purposes of navigation, but the observatory also engaged in a wide variety of other astronomical work over the course of the 19th century, including contributions to the study of variable stars. The careful positional measurements made at the Cape provided essential reference data that allowed variable stars to be precisely identified and their locations recorded for future observers. The astronomers at the Cape undertook systematic surveys of the southern heavens and contributed to various cataloguing efforts that documented the positions and brightnesses of thousands of stars. While the Royal Observatory was not primarily dedicated to variable star research in the manner of some other institutions, its observations nevertheless formed part of the growing international effort to understand stellar variability. The brightness estimates made at the Cape over many years could be combined with observations from other stations to build up continuous records of variable star behavior, filling in gaps that would have existed had only northern observatories been consulted. In Australia, the development of astronomical observation proceeded along its own distinct path, shaped by the particular circumstances of a colony growing toward nationhood at the far edge of the British Empire. The Cygni Observatory, established in 1858, served multiple purposes in its early decades, providing time signals for the colony and conducting meteorological observations alongside its astronomical work. The observatory's contributions to variable star research were modest compared to those of larger institutions, but its presence represented the beginning of organized astronomical science on the Australian continent, and its staff participated in various international observing programs as opportunities arose. Rather more significant for variable star observation was the work conducted not at a government institution but at a private observatory established by a dedicated amateur, John Tebbutt, at his family property near Windsor in New South Wales. Tebbutt was a man of independent means and passionate astronomical interests, and he constructed and equipped his own observatory where he could pursue his studies without the constraints that sometimes limited government-funded institutions. His observing program was remarkably productive, yielding valuable observations of comets, double stars, and various other phenomena over a career spanning more than half a century. Tebbutt first came to international attention in 1861, when he independently discovered a great comet that would become one of the most spectacular of the 19th century. His observations of this comet, made from his Windsor Observatory and communicated to astronomical centers in Europe, demonstrated that valuable scientific work could be accomplished from the remote Australian colonies, and established Tebbutt's reputation as a careful and reliable observer. The comet of 1861, which is sometimes known as Tebbutt's comet, grew a magnificent tail that stretched across much of the sky and was visible to observers worldwide. But it was Tebbutt, working alone in New South Wales, who had first recognized it as a new object and tracked its motion against the background stars. In subsequent years, Tebbutt turned his attention to many different subjects, including the observation of variable stars. His isolated location meant that he could not easily participate in the kind of coordinated observing campaigns that were becoming common in Europe and North America, but his records nevertheless contributed to the growing body of knowledge about stellar variability. Tebbutt continued observing until quite late in his life, and his example helped to inspire later generations of Australian astronomers, demonstrating that significant contributions could be made even from the most distant corners of the world. The coordination of observations between the northern and southern hemispheres presented certain practical challenges that the international astronomical community worked gradually to overcome. A variable star visible from both hemispheres might be observed from European or American stations during part of the year and from southern stations during another part, as the tilt of the Earth's axis carried different portions of the sky into favorable positions for observation. By combining records from multiple sites, astronomers could construct more complete light curves showing how a star's brightness changed over time, filling in gaps that would have occurred had only one hemisphere's observations been available. The difficulties were not merely geometrical but also logistical and social. Communication between observatories on opposite sides of the equator was slow, limited by the speed of ships and later by the capacity of telegraphic cables. The standardization of methods and comparison sequences required careful negotiation between observers who might never meet in person, and the interpretation of observations made under different atmospheric conditions with different instruments demanded considerable skill. Nevertheless, the international astronomical community developed procedures for sharing data and reconciling measurements, creating networks of cooperation that spanned the globe. Among the variable stars of the southern sky, few captured the imagination of 19th-century astronomers quite like Eta Carinii, a remarkable object embedded within a glowing nebula in the constellation Carina. This star, invisible from most of Europe and North America, had been observed by southern navigators and astronomers since the early days of European exploration, and its brightness had been noted to vary considerably over the decades. But nothing in its prior behavior prepared observers for the dramatic outburst that occurred in the early 1840s, when Eta Carinii brightened enormously, eventually reaching a peak magnitude of approximately -0.8 in 1843. At this maximum brightness, Eta Carinii was the second brightest star in the entire sky, outshone only by Sirius, and yet it lay at an immense distance, far beyond the reach of parallax measurement with the instruments of the time. The nature of this outburst was deeply puzzling to contemporary astronomers, who had no framework for understanding how a star could suddenly pour forth such prodigious quantities of light. We know today that Eta Carinii is an extremely massive and unstable star, and that its 19th-century brightening was what astronomers now call a supernova imposter event, a violent eruption that expelled enormous quantities of material into space without completely destroying the star. The distinctive hourglass-shaped nebula surrounding Eta Carinii, visible in modern telescopic images, is composed largely of debris from this catastrophic event. The observations of Eta Carinii's great outburst were made primarily by astronomers at southern stations, including those at the Cape of Good Hope and various other locations where the star rose to sufficient altitude for accurate measurement. The records compiled during this period, however imperfect by modern standards, remain invaluable for understanding the behavior of this extraordinary object. Eta Carinii subsequently faded over the following decades, eventually becoming too dim to see without optical aid, though it has brightened somewhat again in recent years. Its story illustrates both the potential drama of stellar variability and the importance of maintaining continuous observation of unusual objects over extended periods of time. Of equal or perhaps even greater scientific significance were the variable stars discovered in the Magellanic Clouds, those two irregular dwarf galaxies that accompany our own Milky Way through space. Visible from the southern hemisphere as conspicuous patches of diffuse light, the large and small Magellanic Clouds contain billions of stars, and among those stars are numerous variables of various types. The photographic plates taken at Boyden Station and other southern observatories captured images of these star clouds, and when Henrietta Leavitt examined plates of the small Magellanic Cloud in the early 1900s, she found dozens of variable stars whose periods and brightnesses she could measure. The crucial insight that Leavitt derived from these southern Cepheids, as we have discussed earlier, was the relationship between their periods of variation and their intrinsic luminosities. Because all the stars in the small Magellanic Cloud lie at essentially the same distance from Earth, any differences in their apparent brightness must reflect genuine differences in their actual light output. This circumstance, unique to studies of external stellar systems, allowed Leavitt to disentangle the effects of distance and intrinsic brightness in a way that would have been impossible for stars scattered throughout our own galaxy at varying distances. The period-luminosity relation that emerged from this work would become one of the most important tools in the astronomer's kit for measuring cosmic distances, and it depended entirely upon observations made of southern variable stars in an external galaxy visible only from below the equator. The Magellanic Clouds served as a kind of natural laboratory for the study of variable stars, containing examples of many different types in sufficient numbers to allow statistical analysis of their properties. Later investigations would reveal populations of RR Lyrae variables, eclipsing binaries, long-period variables, and other classes within the clouds, each contributing to our understanding of stellar evolution and galactic structure. The southern location of these satellite galaxies meant that their study remained the province of southern observatories and expeditions throughout the 19th and early 20th centuries, adding particular weight to the contributions of astronomers working below the equator. As the 20th century progressed, the collaboration between northern and southern observatories became increasingly formalized and efficient. International organizations such as the International Astronomical Union, founded in 1919, provided frameworks for coordinating observations across national and hemispheric boundaries. Standard comparison sequences and agreed-upon methods helped to ensure that measurements made in South Africa could be directly combined with those made in Massachusetts or Germany, producing light curves of unprecedented completeness and accuracy. The variable star observing programs of the American Association of Variable Star Observers and similar organizations recruited participants from around the world, recognizing that the most complete picture of stellar variability required eyes watching the sky from every accessible vantage point. The establishment of permanent observatories in the southern hemisphere, while driven initially by the practical necessity of surveying the southern stars, ultimately enriched the science of variable star astronomy in ways that extended far beyond mere geographical coverage. The unique objects visible from southern latitudes, from Eta Carinii to the Cepheids of the Magellanic Clouds, proved to be of fundamental importance for understanding stellar physics and cosmic distances. The observers who worked at remote stations in Peru and South Africa and Australia, far from the great libraries and lecture halls of European civilization, contributed essential data without which our picture of the variable sky would be sadly incomplete. And the international networks of cooperation that grew up to connect northern and southern observers laid the groundwork for the global scientific community that continues to study the changing stars today. And so we come now to a quieter sort of discovery, one that happened not at telescope eyepieces in the cold hours before dawn, but rather at writing desks and chalkboards, in the warm light of study lamps, where patient minds worked through equations that would, in time, explain why certain stars behave as they do. For by the early decades of the 20th century, the accumulated observations of variable stars had grown into something vast and detailed, a treasury of light curves and period measurements and spectroscopic readings, all waiting for a theoretical framework that could make sense of what had been so carefully recorded. The numbers were there, you see. The patterns had been found, but the underlying physics, the deep reasons why a star might dim and brighten with such regularity, remained somewhat mysterious, like knowing the words to a song without quite understanding what the melody means. This understanding would come gradually, built up through the contributions of many thoughtful individuals working across different countries and different decades, each adding a piece to what would become a coherent picture of stellar behavior. And if we are to trace the development of this theoretical framework, we might reasonably begin with a book published in the year 1926, a substantial volume written by an English astronomer and physicist named Arthur Stanley Eddington, who had already made significant contributions to our understanding of how stars work. The book was titled The Internal Constitution of the Stars, and it represented, in many ways, the first comprehensive attempt to describe the physical processes occurring deep within stellar interiors, far below the visible surface that astronomers could actually observe. Eddington approached stars as a physicist would, treating them as spheres of gas held together by their own gravity, heated by some internal source of energy that was not yet fully understood, and maintaining themselves in a state of equilibrium where the outward pressure of hot gas balanced the inward pull of gravitational attraction. This might seem an obvious starting point now, but at the time it represented a significant step forward. A willingness to apply the laws of physics that worked so well in earthly laboratories to objects so distant and so different from anything that could be directly examined. And within this framework, Eddington was able to derive relationships between a star's mass, its luminosity, its temperature, and its internal structure, relationships that would prove remarkably accurate when tested against observations. One of the most important of these relationships, and one that would have direct bearing on our understanding of variable stars, was what came to be known as the mass-luminosity relation. Eddington showed, through careful mathematical analysis, that there exists a strong correlation between how massive a star is and how brightly it shines, with more massive stars being dramatically more luminous than their lighter counterparts. This relationship held true across a wide range of stellar types, and it provided astronomers with a powerful tool for estimating stellar masses even when direct measurement was impossible. For variable stars, and particularly for the Cepheids whose period-luminosity relation had already been established, this meant that knowing a star's luminosity also told you something about its mass. And knowing its mass told you something about its internal structure, and knowing its internal structure brought you closer to understanding why it pulsated. But Eddington went further still, and in his book and in subsequent papers, he developed the first physical theory of stellar pulsation, an explanation for why certain stars would expand and contract in such regular rhythms. He proposed that these pulsations were driven by a valve-like mechanism operating within the star's outer layers, where the opacity of the stellar material, meaning its ability to block the outward flow of radiation, varied with temperature in just the right way to amplify small disturbances into sustained oscillations. When the star contracted, the outer layers would heat up, but instead of becoming more transparent to radiation as most materials do when heated, certain ionizing layers would actually become more opaque, trapping energy that would then drive the star to expand again. And when the star expanded and cooled, these layers would become more transparent, releasing the trapped energy and allowing the star to fall back inward, beginning the cycle anew. This mechanism, which would later be refined and elaborated by other researchers, provided for the first time a physical explanation for the remarkable clockwork regularity of Cepheid and Lyrae variables. It was not simply that these stars happened to pulsate, but that the physics of their internal structure made pulsation inevitable under certain conditions. The star was not malfunctioning or behaving abnormally, but rather responding to the basic laws of thermodynamics and radiation transport in a way that could be calculated and predicted. And this understanding, though it would take decades to be fully developed, marked a turning point in how astronomers thought about variable stars, transforming them from curiosities into probes of stellar physics. Meanwhile, during the 1930s, a young Indian physicist named Subrahmanyam Chandrasekhar was working on problems that seemed at first to have little to do with variable stars, though his results would prove essential for understanding certain types of stellar variability. Chandrasekhar was interested in the structure of white dwarf stars, those peculiar objects that had been discovered in the 19th century and that seemed impossibly dense, packing roughly the mass of our Sun into a volume no larger than the Earth. Using the newly developed tools of quantum mechanics and special relativity, Chandrasekhar worked out the detailed physics of matter compressed to such extraordinary densities, where the electrons are squeezed so tightly together that quantum effects dominate their behavior. What Chandrasekhar found was both elegant and profound. He showed that there exists an upper limit to the mass that a white dwarf can have, a limit that depends on fundamental physical constants, and that works out to roughly 1.4 times the mass of our Sun. A white dwarf below this limit can support itself against gravitational collapse through the quantum mechanical pressure of its electrons, but a white dwarf above this limit cannot, and must collapse further into something even denser. This limiting mass, now known as the Chandrasekhar limit, would prove essential for understanding nova systems, those binary stars in which matter transfers from a normal star onto a white dwarf companion, sometimes triggering thermonuclear explosions on the white dwarf surface. The white dwarf structure, its density and temperature profile and gravitational field, determines how the accreted material accumulates and under what conditions it ignites. And Chandrasekhar's work provided the theoretical foundation for all such calculations. As the theoretical understanding of individual stars deepened, astronomers were also making progress in understanding how stars change over time, how they are born and age and eventually die. And here we must mention Martin Schwarzschild, the German-born astronomer who would become one of the leading figures in the theory of stellar evolution. Working through the 1940s and into the following decades, Schwarzschild and his collaborators developed detailed mathematical models showing how stars of different masses evolve through various stages, burning hydrogen in their cores, then helium, then heavier elements in succession, changing their size and temperature and luminosity as they age. What these models revealed was that stellar evolution is not a smooth and gradual process, but rather proceeds through distinct phases, some stable and long-lasting, others brief and turbulent. And importantly for our present subject, the models showed that stars pass through certain evolutionary phases during which they become unstable, during which their internal structure is such that pulsation becomes not just possible but inevitable. The helium ionization zone that Eddington had identified as crucial for driving pulsations exists at just the right depth below the surface only for stars within a certain range of temperatures. And stars move through this temperature range at particular points in their evolutionary histories. A star that has exhausted the hydrogen in its core and begun to expand into a giant, for instance, may cool to the point where it enters this instability region, beginning to pulsate as a Cepheid variable, then pass through and out the other side as it continues to evolve. This evolutionary perspective transformed the understanding of variable stars in a fundamental way. Rather than being rare oddities or damaged stars, variables came to be seen as normal stars passing through normal evolutionary phases, phases that happened to involve instability and pulsation. Every star of sufficient mass would, at some point in its life, become a variable, and the type of variability it exhibited would depend on its mass and evolutionary state. The Cepheids were massive stars in a particular post-main sequence phase. The Lyrae stars were older, lower-mass stars in a later evolutionary stage, and the long-period variables were stars even further along in their evolution, approaching the ends of their lives. Variability was not a disease but a life stage, as natural and predictable as any other phase of stellar existence. All of this theoretical work was greatly aided by a tool that had been developed over the preceding decades, a simple but powerful diagram that allowed astronomers to visualize the properties of stars and to trace their evolutionary paths. This was the diagram that plotted stellar luminosity against surface temperature, arranging stars according to their intrinsic brightness and color, and it came to be known as the Hertzsprung-Russell diagram after the two astronomers who had independently developed it in the early 1910s. Ejnar Hertzsprung in Denmark and Henry Norris Russell in America had both noticed that when stars were plotted in this way, they did not scatter randomly across the diagram but instead clustered along certain regions, forming patterns that suggested underlying physical relationships. The most prominent of these patterns was the main sequence, a diagonal band running from hot, bright blue stars in the upper left to cool, dim red stars in the lower right, along which most stars in any given sample would be found. But there were other patterns too, including the giant and supergiant branches extending above and to the right of the main sequence, and it was along these branches that most variable stars were located. And as theoretical understanding grew, astronomers identified a particular vertical band on the Hertzsprung-Russell diagram, crossing the giant branch at intermediate temperatures, where virtually all stars were variable. This band came to be called the instability strip, and it marked the region of temperature and luminosity where the conditions for pulsational instability were satisfied. The instability strip was not a single uniform zone but rather contained different types of variables at different luminosity levels. At the high luminosity end, where the strip crossed the supergiant region, lay the classical Cepheids, those luminous pulsating stars whose period-luminosity relation had proved so useful for measuring cosmic distances. Lower down, where the strip crossed the horizontal branch populated by old, low-mass stars, lay the Lyrae variables, pulsating with shorter periods and lower luminosities but following their own period-luminosity relation. And there were other types of variables scattered along the strip as well, the Delta Scuti stars and the SX Phoenicis stars and various other classes that would be identified and catalogued over the coming decades. The instability strip provided a framework for understanding all these different types of variables as manifestations of the same basic physical mechanism operating in stars of different masses and evolutionary states. And underneath all of this, providing the ultimate energy source that powered stellar luminosity and drove stellar evolution and made stellar pulsation possible, were the nuclear reactions occurring in stellar cores. For much of the early 20th century, the source of stellar energy had remained a puzzle, with various mechanisms proposed and rejected as incompatible with the known facts. It was not until the late 1930s that a satisfactory answer emerged, and it came through the work of several physicists working independently, among them the German-American Hans Bethe, who published his comprehensive treatment of stellar energy generation in 1938 and 1939. Bethe showed that stars like our Sun generate energy through nuclear fusion reactions, in which hydrogen nuclei are combined to form helium nuclei, releasing energy in the process according to Einstein's famous relation between mass and energy. He worked out the detailed nuclear physics of these reactions, identifying the specific sequences of particle collisions and transformations by which hydrogen is converted to helium in stellar interiors, and he calculated the rates at which these reactions proceed under the temperatures and densities found at stellar centers. There were two main pathways, he showed, one dominant in stars like the Sun and another dominant in more massive, hotter stars, but both achieved the same result: the steady conversion of hydrogen to helium with the release of enormous amounts of energy. This understanding of stellar energy generation completed the theoretical framework for understanding variable stars. The nuclear reactions in a star's core determined how much energy was produced and how that production changed over time as fuel was consumed. The transport of that energy outward through the star, by radiation and convection, determined the star's internal temperature structure. The opacity of the stellar material at various depths determined how easily radiation could flow and where energy might be temporarily trapped. And all of these factors together determined whether a star would pulsate and with what period and amplitude, connecting the deep nuclear physics at the stellar center to the variations in brightness that could be observed from Earth. By 1950, then, the theoretical understanding of variable stars had reached a relatively mature state. The basic physics of stellar structure and stellar pulsation was understood, at least in outline, even if many details remained to be worked out. The relationship between stellar variability and stellar evolution was becoming clear, showing that most types of variables represented normal evolutionary phases through which stars passed on their way from birth to death. The tools existed for calculating stellar models and predicting their behavior, and these predictions could be tested against the wealth of observational data that had been accumulated over the preceding centuries. The variable stars had been transformed from mysterious anomalies into valuable laboratories for studying stellar physics, objects whose behavior could be calculated from first principles and whose observations could be used to refine and improve the theoretical models. This was a profound shift in how astronomers viewed these flickering points of light. In the 17th century, the discovery that certain stars varied in brightness had seemed to challenge the ancient notion of celestial permanence and perfection. In the 18th and 19th centuries, variable stars had been catalogued and classified, their periods measured and their light curves drawn, but the underlying reasons for their behavior had remained obscure. And now, in the middle of the 20th century, those reasons were becoming clear, and the variable stars were taking their place within a coherent theoretical framework that described the birth, life, and death of stars in general. The pulsating variables were stars in unstable evolutionary phases. The eruptive variables were binary systems undergoing mass transfer and thermonuclear explosions, and each type of variability could be understood as the natural consequence of physical processes operating according to well-established laws. And perhaps most importantly, this theoretical understanding revealed that variable stars were not exceptional or peculiar objects, but rather ordinary stars caught at particular moments in their long evolutionary journeys. The Sun itself, that steady and reliable source of light and warmth, will one day expand into a giant and may well become a pulsating variable before finally shedding its outer layers and fading into a white dwarf. And similarly, the Cepheids and Lyrae stars and long-period variables that had been studied so carefully for so long were simply stars, not so different from countless others, that happened to be passing through phases of instability that made their variations visible across the vast distances of interstellar space. In understanding variable stars, astronomers had come to understand stars in general, and the universe had become, in some small way, a bit more comprehensible, a bit more predictable, a bit less mysterious, though no less wonderful for all that. And so we come now to consider the instruments themselves, those carefully crafted devices of glass and metal and wood that allowed patient observers to peer more deeply into the night sky and to measure, with increasing precision, the subtle changes in starlight that had so captured their curiosity, and we shall trace this gentle evolution of tools from the earliest telescopes of the 17th century through to the great observatories of the mid-20th century, taking our time as we go, for there is no hurry here, only the quiet accumulation of human ingenuity applied to the eternal task of understanding the stars. In the city of Danzig, which sits along the Baltic coast in what is now Poland. The astronomer Johannes Hevelius constructed during the middle decades of the 17th century an observatory of remarkable ambition. And it was here that much early work on variable stars would be conducted with instruments that seem almost impossibly delicate to our modern sensibilities, yet which represented the finest optical technology of their era. Hevelius was a wealthy brewer by trade, and he directed considerable personal resources toward the construction of telescopes of ever-increasing length. For in those early days of refractor design, it was understood that longer focal lengths produced clearer images with less of the troublesome color fringing that plagued shorter instruments. His observatory, built atop the connected roofs of 3 houses, eventually housed telescopes reaching 60 feet in length and more, great tubes of wood and brass that required elaborate systems of ropes and pulleys and supporting masts to maneuver toward different regions of the sky. These aerial telescopes, as they were sometimes called, swayed gently in the wind and demanded considerable patience to operate. Yet through them Hevelius conducted systematic surveys of the heavens and produced detailed star catalogues that would serve astronomers for generations. His observations of Mira, that remarkable long-period variable in the constellation Cetus, were made with instruments of this type, and though the precision of his measurements would seem crude by later standards, the careful methodology he developed for comparing the brightness of one star against another laid important groundwork for all variable star photometry that would follow. The fundamental limitation of these early refractors was the problem of chromatic aberration, which caused light of different colors to focus at slightly different distances from the lens, producing images surrounded by colored halos that degraded their sharpness and made precise measurements difficult. Astronomers attempted to minimize this effect by making their telescopes longer and longer, as the distortion becomes less pronounced when the ratio of focal length to aperture is increased. But this approach had practical limits that were reached by the great unwieldy instruments of Hevelius and his contemporaries. The solution to this problem came in 1758, when the English optician John Dolland developed and patented the achromatic refractor, which combined 2 lenses made from different types of glass, crown and flint, arranged so that the chromatic aberration of one was largely cancelled by that of the other. This innovation transformed telescope design almost overnight, for now it became possible to construct instruments that were both compact and sharp-sighted, refractors of manageable length that produced images far superior to the long aerial telescopes of the previous century. Variable star observers benefited greatly from this development, as the clearer images allowed more precise estimation of stellar brightness and made it easier to distinguish closely spaced comparison stars in crowded fields. The achromatic refractor would dominate astronomical observation for well over a century following Dolland's breakthrough, growing steadily larger and more refined as glassmakers learned to produce ever purer and more homogeneous blanks from which lenses could be ground. Throughout the 19th century, the construction of great refractors became something of a competitive endeavor among observatories and the wealthy patrons who funded them, with each new instrument surpassing its predecessors in the diameter of its objective lens and thus in its ability to gather light and resolve fine detail. For variable star observation, these larger apertures meant that fainter stars could be studied and that the comparison sequences available for estimating brightness were greatly expanded. The Lick Observatory, established on Mount Hamilton in California and funded through a bequest from the businessman James Lick, received in 1888 a refractor with an objective lens measuring 36 inches in diameter, which was at that time the largest in the world. This instrument, crafted by the optical firm of Alvan Clark and Sons, who had become the preeminent American makers of astronomical lenses, opened new possibilities for variable star research by reaching stars that had previously been too faint to observe with precision. The clear mountain air above Mount Hamilton, far from the smoke and lights of cities, provided seeing conditions that allowed the great refractor to perform near its theoretical limits on many nights. Then in 1897, an even larger refractor was completed for the Yerkes Observatory in Wisconsin, with an objective lens of 40 inches, and this instrument would remain the largest refractor ever constructed, for reasons we shall come to presently. These great refractors, with their long focal lengths and steady clock-driven mounts, became essential tools for the systematic study of variable stars during the late 19th and early 20th centuries, and many thousands of observations made through them would fill the archives that later researchers would draw upon. But even as the refractors grew larger, another approach to telescope design was being developed that would eventually prove more practical for instruments of the greatest size: the reflecting telescope, which uses a curved mirror rather than a lens to gather and focus light, had been known since the time of Isaac Newton, who constructed a small example in 1668. Yet for many decades reflectors remained inferior to refractors for serious astronomical work because the mirrors of that era, made from a metal alloy called speculum, tarnished quickly and required frequent repolishing. William Herschel, the German-born musician who became one of the most prolific astronomers of the 18th century after his discovery of the planet Uranus, pursued the construction of reflecting telescopes with tremendous dedication, casting and grinding speculum mirrors of increasing size at his home in England. In 1789, he completed a telescope with a mirror measuring 48 inches in diameter, which was the largest astronomical instrument of its time, though the mirror's reflectivity was never optimal and the telescope proved difficult to use effectively. Herschel's observations with his various reflectors contributed significantly to the early cataloguing of nebulae and double stars, though his work on variable stars was less extensive. The speculum mirror reflector reached its apotheosis with the Great Leviathan of Parsonstown, constructed by William Parsons, the 3rd Earl of Ross, in Ireland during the 1840s, with a mirror of 72 inches. Yet this instrument too suffered from the limitations of speculum, which reflected only about 60% of the light falling upon it and degraded further as tarnish accumulated. The development that made large reflectors truly practical for precision astronomical work was the introduction of glass mirrors with a thin coating of silver, deposited chemically upon their polished surfaces. These silver-on-glass mirrors reflected far more light than speculum, perhaps 90% or more when freshly coated, and when the silver tarnished it could be stripped away and replaced without disturbing the carefully figured glass surface beneath. This technology enabled a new generation of reflecting telescopes that would eventually surpass refractors in size and capability. The reasons for this shift relate to fundamental differences in how lenses and mirrors can be supported. A lens must be held only at its edges, allowing light to pass through its entire surface, and as lenses grow larger they begin to sag under their own weight, distorting the carefully figured curves upon which their performance depends. A mirror, by contrast, can be supported across its entire back surface, making it possible to construct mirrors of far greater diameter without comparable distortion. Additionally, a lens must be made from glass that is perfectly transparent and homogeneous throughout its entire thickness, while a mirror need only have a precisely shaped front surface, making the production of large mirrors considerably less demanding. For these reasons, the great observatories of the 20th century would turn increasingly to reflectors for their largest instruments. The Mount Wilson Observatory, established in the mountains above Pasadena in California, became the leading center for this new era of large reflector astronomy. In 1908, a reflecting telescope with a 60-inch mirror was completed there, and this instrument would be used extensively for variable star observation and other photometric work. The glass blank for this mirror had been cast in France and shipped to America, where it was figured to the required parabolic curve with painstaking care. A decade later, in 1917, an even larger reflector was completed at Mount Wilson, the 100-inch Hooker telescope, funded by a Los Angeles businessman named John Hooker and named in his honor. The glass blank for this great mirror had a troubled history, arriving from France with bubbles and imperfections that some feared would make it unusable. Yet careful testing revealed that the flaws were confined to interior regions of the glass that would not affect the precision of the reflecting surface. And so the work proceeded. This 100-inch telescope would become the instrument with which Edwin Hubble made his discoveries about the nature of the spiral nebulae and the expansion of the universe. But it was also used extensively for variable star photometry, and its light-gathering power allowed the study of faint variables in distant stellar systems that had previously been beyond reach. The mounting of these great telescopes required engineering of considerable sophistication, for the instruments needed to track the apparent motion of the stars across the sky with extreme precision if they were to be useful for serious observation. This tracking is accomplished through what is called a clock drive, a mechanism that rotates the telescope at exactly the same rate as the Earth turns, but in the opposite direction, so that a star once centered in the eyepiece or upon a photographic plate remains stationary despite the planet's rotation beneath it. The development of accurate clock drives was essential for variable star observation for several reasons. First, it allowed observers to concentrate fully on the task of estimating stellar brightness without the distraction of constantly adjusting the telescope's position. Second, and perhaps more importantly for later photographic work, it enabled long exposures during which faint starlight could accumulate upon sensitive plates to build up detectable images. Early clock drives were powered by falling weights, much like household clocks, with elaborate gear trains that required careful regulation to maintain the precise sidereal rate. Later drives employed electric motors with sophisticated control systems that could be adjusted based on the observer's assessment of tracking accuracy. The improvement of clock drives throughout the 19th and 20th centuries was a quiet but essential contribution to the precision of variable star photometry. For without steady tracking, neither visual estimation nor photographic measurement could achieve its full potential. The comparison star sequences that allowed observers to estimate variable star brightness were developed through painstaking effort over many decades. The fundamental challenge was to establish the relative brightness of ordinary stars, those not suspected of variability, with sufficient precision that they could serve as reliable standards against which the changing brightness of variable stars could be measured. Early observers simply estimated these values based on their own impressions, leading to considerable inconsistency between different workers. The Harvard College Observatory, under the direction of Edward Pickering beginning in the 1870s and continuing for several decades, undertook systematic efforts to establish standardized magnitude scales and to measure comparison star brightnesses with increasing precision. These efforts produced photometric atlases in which the magnitudes of comparison stars were carefully tabulated, allowing observers around the world to make measurements that could be meaningfully combined and compared. The North Polar Sequence, a set of stars near the North Celestial Pole whose brightnesses were determined with particular care, became an important reference standard that helped unify photometric systems. For variable star observers, these atlases and catalogues were essential reference materials. consulted constantly as they made their estimates and recorded their observations. The transition from visual to photographic observation of variable stars, which we touched upon earlier, brought with it new instruments designed specifically for measuring the images recorded on photographic plates. The human eye, for all its remarkable adaptability, is not well suited to comparing the absolute brightness of tiny spots on a glass plate, and so mechanical and optical devices were developed to make such comparisons more objective and precise. The iris photometer, which became widely used in the early 20th century, was one such instrument. It worked by projecting light through the photographic plate and allowing the observer to adjust a variable diaphragm, like the iris of a camera, until the transmitted light matched some standard source. The size of the diaphragm opening needed to achieve this match was related to the density of the stellar image, which in turn was related to the original brightness of the star. Though the relationship between image size and stellar magnitude was not perfectly linear and required careful calibration, the iris photometer allowed measurements to be made with a precision and reproducibility that surpassed what could be achieved through simple visual inspection of the plate. Variable star observers who worked with photographic plates came to rely heavily on instruments of this type, spending many hours at the measuring machines extracting brightness estimates from their accumulated collections of plates. A specialized instrument that proved invaluable for the discovery of variable stars, as well as asteroids and other objects that changed position or brightness over time, was the blink comparator, developed around 1904 by the German optical designer Carl Pulfrich and manufactured by the Zeiss company. This device allowed an observer to view two photographic plates of the same star field, taken at different times, in rapid alternation. The plates were carefully aligned so that the images of ordinary stars fell at exactly the same positions, and then an optical system switched the observer's view back and forth between the two plates several times per second. Stars that had not changed appeared perfectly steady under this examination, but any star that had varied in brightness, or any object that had moved from one position to another, would appear to blink or jump as the view alternated. This made such objects immediately conspicuous to the observer, who could then investigate further. The blink comparator greatly accelerated the process of searching for variable stars, which had previously required tedious comparison of plates by eye, examining thousands of stars one by one to detect those that had changed. With the blink comparator, a trained operator could scan a plate relatively quickly, with any variables literally catching the eye through their blinking. Many hundreds of variable stars were discovered through the systematic application of this technique to photographic surveys. The development of narrowband filters that transmitted only specific wavelengths of light opened new approaches to the study of certain types of variable stars, particularly those that exhibited emission lines in their spectra. When a star displays emission at a particular wavelength, such as the red hydrogen alpha line, a filter that passes only that wavelength will show the star relatively brighter compared to its neighbors than it appears in unfiltered light. By comparing observations made through such narrowband filters with those made through broader filters or no filter at all, astronomers could study how the emission line regions of a star varied independently of the underlying continuous spectrum. This technique was particularly valuable for studying certain irregular variables, including some symbiotic stars and objects with extensive gaseous envelopes, where the emission line variations told a different story than the variations in overall brightness. The manufacture of narrowband interference filters improved steadily through the early 20th century, making this specialized photometric technique increasingly accessible to observatories engaged in variable star research. And so we see how the tools available to variable star observers evolved over these 3 centuries. From the long, unwieldy refractors of Hevelius swaying in the Baltic wind, through the elegant achromatic instruments of the 19th century, to the great reflectors of Mount Wilson that opened the distant universe to human study. Alongside the telescopes themselves, the supporting technologies developed in parallel, the clock drives that enabled steady tracking, the comparison sequences that provided calibrated standards, the iris photometers and blink comparators that extracted information from photographic plates, the specialized filters that isolated particular components of stellar light. Each of these developments contributed to the ever-increasing precision with which the variable stars could be monitored and understood. The observers who used these instruments were patient people, content to spend night after night and year after year accumulating the measurements that would eventually reveal the nature of stellar variability. And the instruments served them faithfully, gathering starlight across the decades, recording on plates and in logbooks the gentle fluctuations that held such secrets about the physics of distant suns. And now we arrive at a quieter chapter, one concerned not so much with discoveries themselves but with the patient accumulation of observations, the careful preservation of starlight captured night after night across many decades, and the gradual construction of archives that would prove essential to everything that followed. For it is one thing to notice that a star varies in brightness, and quite another to record that variation faithfully, to preserve those records in a form that others might use, and to build systems for sharing and comparing observations made by different people in different places across the slowly turning years. This is the story of how 3 centuries of watching the heavens produced something more than scattered notes and isolated measurements, how the community of variable star observers created, almost without realizing the full magnitude of what they were building, a treasury of information that would support some of the most profound insights in 20th century astronomy. We might begin by considering what it means to observe a variable star, not once or twice but consistently over months and years and eventually decades. Each observation represents a small act of attention, a moment when someone looked at the sky, compared one star to another, and recorded what they saw. In the early centuries, this recording took the form of handwritten notes in journals and logbooks, descriptions that might say a star appeared as bright as this comparison star or perhaps slightly fainter than that one. These notes were personal documents, kept by individual observers and sometimes shared through correspondence or published in the proceedings of learned societies. But they were scattered across many places, held in private collections or the archives of universities and observatories, and there was no systematic effort to gather them together or ensure they would survive for future generations to consult. Much was lost through neglect or accident or the simple passage of time, and what remained was often difficult to locate and compare. The situation began to change in the 19th century as astronomy became more organized and as the value of long-term records became increasingly apparent. Observatories started keeping more systematic logs, and publications like the Astronomische Nachrichten, which had been founded in 1821, provided a venue where observations could be shared with the wider community. This German journal, with its sober pages of tables and brief reports, became something like a common notice board for astronomers across Europe and eventually around the world. An observer in England who noticed something unusual about a particular star could send a brief communication to the Nachrichten, and within a few weeks colleagues in Germany or Russia or Italy might read about it and add their own observations to the record. The pace was unhurried by modern standards, with mail taking days or weeks to cross borders and publication following its own measured schedule, but a network was forming, a community of people who understood that their individual observations gained meaning when combined with the observations of others. The Astrophysical Journal, founded in 1895, provided a similar venue for the growing American astronomical community, and together these publications and others like them created a permanent record of observations that anyone with access to a good library could consult. When a later researcher wanted to know what Mira had been doing in 1873, or how bright a particular eclipsing binary had appeared in 1912, they could search through the bound volumes of these journals and find the information waiting for them, preserved on acid-free paper in the quiet stacks of observatory libraries. This was archiving in its simplest form, the preservation of published observations through the ordinary processes of scientific communication, and it worked reasonably well for many decades. But the photographic revolution brought both new possibilities and new challenges. When Edward Pickering and his colleagues at Harvard began systematically photographing the sky in the 1880s, they created a new kind of record, one that captured the brightness of thousands of stars simultaneously and preserved that information on glass plates that could be examined and measured repeatedly. Each plate was a snapshot of a particular patch of sky at a particular moment, and as the years passed and the plates accumulated, the collection became something unprecedented in the history of astronomy, a visual archive of the heavens that spanned decades and recorded changes that no human eye, watching in real time, could have perceived. The Harvard College Observatory made a deliberate decision to preserve these plates and to continue adding to the collection year after year. This required physical space, for glass plates are not small or light, and by 1950 the collection had grown to exceed 500,000 individual plates, each one carefully stored in its own paper envelope, each envelope filed in wooden cabinets that filled room after room. The plates recorded not just the northern sky visible from Cambridge but also large portions of the southern sky, observed from a station in Peru that Harvard had established specifically to extend the survey into regions not visible from Massachusetts. Together these plates provided continuous coverage of much of the celestial sphere, a record stretching back to the 1880s that captured every star bright enough to register on the photographic emulsion. The value of this collection was not immediately obvious to everyone. Glass plates are fragile, and storing them requires space and careful climate control. There were times when the question arose whether it might be simpler to measure what could be measured and then discard the plates themselves, freeing the space for other purposes. But wiser heads prevailed, and the decision was made to preserve everything, to treat the collection as a permanent archive that future generations might consult for purposes not yet imagined. This decision would prove remarkably fortunate, for the plates recorded information that their makers could not fully extract with the technology of their time. Later researchers, equipped with better measuring devices and eventually with digital scanners, would return to these same plates and discover things that had been hiding in plain sight for decades. Parallel to the photographic archives, the American Association of Variable Star Observers was building a different kind of collection, one composed not of images but of numbers, the brightness estimates reported by visual observers around the world. By 1950, the AAVSO had accumulated millions of individual observations, each one representing a moment when someone had looked at a particular variable star and recorded its brightness. These observations arrived at the association's headquarters in the form of standardized reporting forms, carefully designed sheets that prompted observers to record not just the brightness estimate but also the date and time, the comparison stars used, the observing conditions, and any other relevant details. The forms imposed a discipline on the reporting process, ensuring that observations from different people could be meaningfully compared. Quality control was a constant concern, for visual observations are inherently subjective and different observers can arrive at different estimates even when looking at the same star on the same night. The AAVSO developed procedures for checking observations against one another, identifying observers whose estimates consistently differed from the consensus, and providing feedback to help people improve their technique. This was delicate work, for the observers were volunteers who gave their time freely, and no one wanted to discourage participation. But accuracy mattered, and the association learned to balance encouragement with gentle correction, building a community of observers whose collective work was more reliable than any individual contribution might be. The observations accumulated in filing cabinets, organized by star and by date, growing thicker year by year as more observers joined the network and more nights of watching added to the record. For the long-period variables like Mira and its many cousins, these records eventually spanned decades, providing material for studies of how the periods and brightness ranges of these stars changed over time. Small shifts that would be invisible in a few years of data became apparent when one could trace a star's behavior across half a century or more. The data revealed that some Mira variables were gradually changing their periods, growing longer or shorter by small amounts that accumulated over the years, while others maintained their rhythms with remarkable stability. These patterns held clues to what was happening inside the stars, to the slow processes of stellar evolution that played out over timescales far longer than any human life. The international exchange of data grew more organized as the century progressed. The Astronomische Nachrichten continued its role as a clearinghouse for observations, and specialist publications devoted specifically to variable stars appeared in several countries. The Soviet Union established its own extensive program of variable star observation, and despite the political tensions of the era, scientific information continued to flow across borders, albeit sometimes with delays and difficulties. Astronomers understood that variable star research was inherently an international enterprise, that no single country or observatory could monitor the entire sky continuously, and that the value of any individual contribution depended on its ability to be combined with the work of others. A landmark in the systematization of variable star knowledge came with the General Catalogue of Variable Stars, a project that aimed to list every known variable star and provide essential information about each one. The work began in the Soviet Union, where the tradition of comprehensive astronomical cataloging was strong, and it resulted in publications that brought together data scattered across thousands of papers and reports. For each star, the catalogue provided coordinates, brightness range, period if known, spectral type, and references to the literature where more detailed information could be found. This was not glamorous work, but it was essential, transforming a chaotic accumulation of discoveries into an organized reference that any researcher could consult. The catalogue grew with each new edition as more variables were discovered, and it became a standard tool in the field, a foundation on which more specialized investigations could build. The 1940s brought a quiet revolution in how astronomical data could be processed, as the techniques of punched card data processing began to find their way into observatory practice. These cards, with their rows of small holes representing numbers and codes, had been developed for business applications, for tracking inventory and processing payrolls. But astronomers recognized that similar methods could be applied to the manipulation of observational data. A large set of observations, once transcribed onto punched cards, could be sorted and tabulated and analyzed using machines that worked much faster than any human could manage with pencil and paper. The cards clattered through their readers, and totals emerged, and correlations appeared that would have taken weeks to compute by hand. This was not yet the electronic computer era, and the machines of the 1940s were limited in their capabilities, but they represented the beginning of a transformation that would accelerate dramatically in the decades that followed. Astronomers who had grown accustomed to laboriously calculating by hand began to see new possibilities, and the accumulated observations in the archives took on new significance as raw material for automated analysis. Data that had been gathered for one purpose might be reprocessed for another, and patterns that had been too subtle or too diffuse to detect through manual methods began to emerge from the mechanized calculations. All of this accumulation and preservation and systematization might seem rather dry, rather distant from the excitement of discovery, but it created something essential, an empirical foundation on which theoretical advances could stand. When a theorist proposed a new model of stellar pulsation or a new explanation for the period-luminosity relation, the test of that model came from the observations, from comparing its predictions against what the stars had actually been observed to do. And those observations, to be useful for such tests, had to be numerous and accurate and consistently recorded over long spans of time. The archives provided exactly this, a treasury of facts against which theories could be tried. The significance of this foundation became dramatically apparent in 1952, when the German-American astronomer Walter Bade announced a discovery that would transform our understanding of the universe's scale. Bade had been studying the stars in the Andromeda galaxy, taking advantage of the darkened skies over Mount Wilson during the wartime blackouts of Los Angeles, and he had noticed something puzzling about the Cepheid variables there. They seemed to be of two distinct types, belonging to what he called Population 1 and Population 2, and these two populations had different period-luminosity relationships. The Cepheids that Henrietta Leavitt had studied in the Magellanic Clouds, the ones that had established the original period-luminosity relation, belonged to one population, while the Cepheids used to calibrate the distance scale belonged to the other. When Bade worked through the implications, he found that the cosmic distance scale had been fundamentally wrong. The universe was not merely larger than previously thought. It was approximately twice as large, with galaxies sitting at distances far greater than anyone had realized. This was a profound revision, one that affected everything from estimates of the age of the universe to the understanding of galactic structure, and it emerged directly from careful attention to observational data, from the willingness to look closely at the Cepheid measurements and take seriously the subtle differences that appeared. But Bade's discovery was not conjured from nothing. It depended on decades of accumulated observations, on the photographic plates and the published measurements and the carefully maintained archives that preserved the record of what the Cepheids had actually been doing over the years. Without that observational foundation, there would have been nothing to reanalyze, no data to reveal the two populations, no basis for the dramatic revision of the distance scale. The patient work of countless observers, many of them now forgotten, had created the conditions for this breakthrough. And this pattern would repeat itself in the decades that followed. The revolutionary discoveries of the mid-20th century in stellar astrophysics, the understanding of stellar evolution, the explanation of elemental synthesis in stars, the recognition of different stellar populations and their significance for galactic history, all of these rested on the observational foundation that had been built up over the preceding centuries. The theorists who constructed these grand syntheses were working with data, with facts about how stars actually behaved. And those facts came from the observations preserved in the archives and the published records and the accumulated databases of organizations like the AAVSO. There is something quietly moving about this, about the way that individual acts of observation, each one seemingly small and unremarkable, accumulated into something of lasting value. The observer who stepped outside on a cold, clear night in 1923 and recorded the brightness of a few variable stars probably did not imagine that those observations would still be consulted decades later, would form part of a data set used to test theories not yet formulated. But that is how it worked, how it continues to work. The value of an observation often becomes apparent only in retrospect, only when it is combined with other observations made by other people at other times, only when someone asks a question that the original observer never thought to ask. The archives themselves became objects of care and attention, requiring ongoing effort to preserve and maintain. Glass plates can crack or fade. Paper can deteriorate. Filing systems can become disorganized. The people who tended these collections, the librarians and archivists and curators who kept the cabinets in order and the climate controlled and the catalogues up to date, contributed something essential even if their names rarely appeared in scientific papers. Without their quiet work, the record would have been lost or scattered or rendered unusable, and the foundation would have crumbled beneath the theories it was meant to support. By 1950, 3 centuries had passed since Holwader first noticed the strange behavior of Mira, and the field of variable star observation had grown from a curious anomaly into a mature discipline with its own institutions and methods and accumulated knowledge. The transition from visual to photographic observation had multiplied the power of each night's work, capturing thousands of stars simultaneously rather than studying them one at a time. The development of standardized reporting and quality control had made it possible to combine observations from different sources into coherent datasets. The international exchange of information through journals and catalogues had created a shared foundation that transcended national boundaries. And the first stirrings of automated data processing hinted at the computational revolution that would transform the field in the decades ahead. This was the inheritance that mid-20th century astronomers received from their predecessors, not merely a collection of facts about particular stars but a working system for gathering and preserving and sharing observations, a system that could be extended and improved as new technologies became available. The discoveries that lay ahead, the pulsars and the X-ray binaries and the gravitational wave sources, would require new instruments and new methods, but they would also depend on the traditions of careful observation and systematic record-keeping that had been established in the quieter centuries before. And so the accumulation continued, the plates filed and the observations recorded and the catalogues updated, building higher and higher the foundation on which the future would stand. This is the patient work that makes science possible, the gathering of evidence through countless small acts of attention, each one contributing its small portion to a structure larger than any individual could complete alone. It is work that continues still, though the methods have changed and the instruments have grown more powerful. The fundamental principle remains the same, that our understanding of the universe rests on the observations we have taken care to make and preserve.